Good morning.
Good morning, Ganas, please. Kalimera.
Yes, thank you. Kalimera.
Good morning.
Ohio gozaimasu, Toru-san. Your microphone is.
Good morning, professors.
Sensei, Ohio gozaimasu.
Thank you very much for your kind introduction.
Welcome, welcome everyone. Good morning, good afternoon, or even good evening in some places, I guess. Thank you for joining us, by the way. So we are about to start. I guess we have a couple of minutes. Good afternoon, Professor Sae. Good afternoon, Kashan Dai. All friends all around the world, thank you for joining us again. Good morning, Tatiana. And anyone else? Good morning, Tuna.
Hi everyone, good morning. Hocam merhaba.
Merhaba. So, all right. What time is it?
It's 9 hours.
Okay, so we can start it.
Distinguished guests, dear colleagues, good morning from Istanbul. I greet all of you and welcome you to the symposium. I would like to invite Vice Rector of Istanbul Technical University, Professor Bülent İnanç, for his opening speech. Thank you.
İsmail Bey, neler oluyor?
Bir saniye. Wait, I guess we have some. Okay, he's about to join us. Sorry for this situation.
Bu arada YouTube başlamadı.
Okay. All right. He's sorry. Okay, now he's coming. Good morning, Professor Inanç.
Good morning to everybody.
Okay, thank you for joining us today.
So, shall we start?
Yep, please.
Okay. Good morning to all, and I'm Bülent İnanç. I'm the Vice President of Istanbul Technical University, and I would like to welcome you all to this significant and important symposium. We came together at this international symposium organized by our Disaster Management Institute on the first anniversary of the 7 magnitude earthquake that took place in near the Aegean Sea, Samos Island on October 30th, 2020. And one of these devastating earthquakes occurred last year, this earthquake. A total of 119 deaths and 1,053 injuries occurred in the Samos earthquake. And the Samos earthquake was among the deadliest earthquakes in the world that occurred in 2020, as you know. Earthquakes of this magnitude are repeated for short periods in Turkey, where seismic activity is high and unfortunately cause loss of lives and properties. As you know, many buildings and facilities had been destroyed in Istanbul and Marmara region in 2 devastating earthquakes that were of magnitude of 7.4 and 7.2 on the North Anatolian Fault on August 17 and November 12th of 1999. Unfortunately, we had lost 19,218 of our citizens. We have lost their lives in these earthquakes, and many moderate and destructive earthquakes continued to occur in our country after this day. These earthquakes, as in the rest of the world, cause acceleration of studies in this field. And they also make way for different research activities and development of new technologies and products in our country. I would like to give some information about also our university, the Istanbul Technical University. Istanbul Technical ITU conducts intensive studies on earthquakes and scientifically leads institutions in our country. And many faculty members working in various faculties and institutes carry out theoretical and experimental studies in the fields of geology, seismology, seismotectonics, tsunami, geotechnical, structural, and earthquake engineering. I proudly state that ITU is one of the most significant institutions of our country that conduct research, produce information and technology, and provides training on understanding earthquake mechanisms and reducing earthquake damages. And recently we had been consulted with Istanbul Metropolitan Municipality about the hazards of earthquakes and the risk assessment, as Ercan Yüksel, Professor Yüksel has led the team for preparing a very significant report to the Metropolitan Municipality. The aim of this symposium, which is one of the interactive events organized by ITU Disaster Management Institute, is to bring together geoscience and structural and earthquake engineering experts, share current research and knowledge, make discussions over different disciplines, and seek solutions for the future. It should be emphasized here that it is very important to work with a multidisciplinary method and share knowledge from different fields, particularly on earthquakes. The latest situation in the agency, where seismic activity is intense, will be evaluated in this symposium. in the light of current international academic data. How Turkey and Greece will be especially affected by the earthquake hazard that exists in the agency will also be discussed in all aspects. I would like to thank Professor Ercan Yüksel, Director of Disaster Management Institutes, and Professor Tuncay Taymaz from Geophysical Engineering Department, and Professor Oğuz Cem Çelik from Department of Architecture for organizing this international symposium. At the same time, this symposium is dedicated to Professor Ibrahim Demir, the Secretary General of the former Secretary General of our university, whom we lost on May 6, 2021, this year, due to COVID-19 pandemic. I will make a short presentation on his background and his valuable services to our university. Professor Demir was born in 1959 in Kahramanmaraş city. He completed his undergraduate and graduate studies at the Department of Civil Engineering and Environmental Engineering of our university, respectively, and his doctorate at the Department of Environmental Engineering at Yıldız Technical University, which is also located in Istanbul. He continued his postdoctoral studies as a visiting scientist at Rutgers University, USA, for 2 years, and he became assistant professor in 1996, associate professor in 2007, and full professor in 2018 at ITU. In addition to his duties and academic studies in the Environmental Engineering Department, he held many administrative positions at different institutions, such as the head of the Istanbul Metropolitan Municipality, Environmental Protection and Control Department. He was the director of the ITU Disaster Management Application and Research Center, deputy director of the ITU Earthquake Engineering and Disaster Management Institute, and head of the Disaster and Emergency Management Department. Professor Demir held positions as executive researcher and consultant in many research and application projects, which were supported by different institutions. He was married with 3 children, and we lost a valuable academic, valued friend on May 6. We commemorate with respect and grace our esteemed academic, Brother Ibrahim, or we call him Ibrahim Abi, who has made great contribution to a huge number of students and academicians in this university. We are organizing this important symposium in his memory. Finally, I wish a successful symposium, and thank you all for your support and participation. Thank you.
Dear guests, as the director of Istanbul Technical University Disaster Management Institute, I greet all of you and welcome you to the symposium. We came together at this international symposium on the first anniversary of the Samos earthquake. Dear guests, the symposium is dedicated to Professor Dr. Ibrahim Demir, who was faculty member of Disaster Management Institute. We lost him on May 6, 2021 due to the COVID-19 pandemic. We remember him with respect and mercy. I will give some summary about the losses caused by the Samos earthquake in Izmir in 10 minutes. The Samos Island or agency earthquakes struck at 14 local time in Greece and Turkey, respectively, on 30 October 2020. It produced wide-ranging effects, including tsunami run-up, ground shaking with local zones of high intensity that led to collapse of structures. The earthquake was among the deadliest earthquakes in the world that occurred in 2020. And in Turkey, a total of 119 deaths and 1,053 injuries occurred in the Samos earthquake on October 30, 2020. There are several recordings, especially located around the city of Izmir. Actually, the maximum intensity or PGA values is around less than 200 Gal. And different types of soil conditions are existing in the city and vicinity of the Izmir. And the biggest damages are located in this location. This is the elastic acceleration spectrum recorded at the center of city. As you see, the components of east-west and north-south is relatively higher than the up-down components of the record. Depending on the type of soil, different effects on the structural systems has been recorded during the earthquake. On the left-hand side, a symbolic stiff soil, and on the right-hand side, you see the soft soil response of the earthquakes. As you see, for the longer period, attenuation has been recorded, especially larger than 1 second. And depending on the soil condition around the city, we observe this effect on the buildings. As you see, there are two important curves on the graphics, and the first one is 175 years return period, and the other one is 72-year return period design spectra, and especially around the 1.5 second period structures, the response is almost close to the design spectrum. In this city, there are different types of buildings. Some of them are low-rise and some of them is high-rise buildings, especially for the Bayraklı and Bostanlı district of the city. There are different ages of structures. For example, on the general buildings type on the left-hand side, and the modern buildings on the right-hand side on the figures. We observed different types of collapse mechanism, but the badly one is totally collapsed buildings. Probably 8 or 9 distinct buildings are observed this type of total collapse, and many of the live losses have been experienced in these buildings, unfortunately. And also we observed the partially collapsed buildings, as you see from the scene. Some part of the building and some story of the building has been disappeared during the earthquakes. Also, several common damages are observed during the earthquake, especially for the shear deformation on the shear walls or similar to shear walls columns. And also there are some member damages, especially for the short columns and other structural deficiencies. Also, there are some other problems, and during the quakes we observed already these are from the site visitings, especially for the very low quality of concrete, and the reinforcement details are very poor, especially for the total collapse of buildings. From the recordings, we can make some results from these figures, especially for the different part of the city, like Bayraklı, Bornova, Konak, and Karşıyaka. These are the places where we observed large damages on different types of buildings. And especially for the Bayraklı, its soil condition is relatively bad for comparing with the others. In that case, the number of buildings is relatively high compared with the other parts of the city. And also, building age is another important parameter for the observation of the damages, especially for from the 1990 to 2000, almost the last 10 years of the last century. We observed very large amount of damaged building constructed at this period. Also, number of stories is another important parameter for the structural systems, and we generally observe the damages for very small number of story buildings like 1 to 3, and also 7 to 10 story at mid-rise buildings. And unfortunately, the total collapsed buildings had 7 to 10 stories, and we observed these buildings, especially in Bayraklı region in the city. Just in a few words about one of the total collapsed buildings in this simple figure, there are many structural deficiencies in producing the structural system in this region, especially for the story plans. We don't see any regular frame, and the number of columns is seen quite enough, but unfortunately its lateral strength and stiffness is not enough to carry the lateral forces, and the number of, or the area of the shear walls is relatively low for these buildings. Let me give some few figures about the structural properties of these structural systems, especially the concrete quality in the projects is almost enough for the axial stress level on the columns, but unfortunately, in reality, the real concrete quality is quite lower than the project one. In that case, the axial stress level is relatively higher than the acceptable range. In that case, in some columns, the ratio goes up to 1. In that case, the columns are very brittle for lateral actions. On the right-hand side of the figure, in both directions of the structural system, you see the pushover curves. Actually, the blue curve shows or represents the lateral force top displacement relation, but the red rectangle shows us the shear failure of the columns and also shear walls on the structural systems. In that case, we don't have any lateral strength bigger than 10%. It shows the design level for this type of buildings. Because of this reason, probably some parts of the shear walls and some of the columns were collapsed in the early stages of the earthquake. On the left-hand side, you see that U-shaped shear wall, and P15 is a one arm of the shear wall. In that case, you see the shear capacity of the member is exceeded in the lower to upper stories. And finally, we made some observations on the side, and we see that the details, reinforcement details of the members is not good to carry this type of internal forces on the members. And also, we used a record just around the building. As you see, the intensity of the acceleration is relatively lower, almost 100 gal, but unfortunately, its effect on the member of the structure is quite larger. As you see on the right-hand side, the shear capacity of the shear walls again is exceeded by this intensity of acceleration. At the end of my speech, I want to thank you all for your support and participation in this important international symposium. I respectfully greet all of you. Thank you.
Okay, thank you, Professor Yüksel, for this very interesting talk. So I would like to, I'm Oğuz Cem Çelik. My last name is Çelik. I'm a professor of structural and earthquake engineering at ITU Department of Architecture. I teach architects about structural engineering issues, so which is very tough, you know very well. I hope the same thing is done by Professor Moretti in Greece, I guess. So this is a different life, I know that. So we have many common things actually in culture, food, and friendship, even in earthquakes in between Turkey and Greece, and earthquakes are one of them. So I would like to make a very short presentation about that. I mean, just to show you some observations regarding the this earthquake. I hope you are able to see that. Wait a minute. Yes. These are sort of structural observations, very quick in 5 or 7 minutes following the 7.0 Samos off the coast of Kuşadası earthquake of October. So I would like to express my sincere thanks first to ITU Presidential Office, ITU Disaster Management Institute, and of course invited well-known speakers and also YouTube followers of ITU for making this event happen. This is a very general map of seismic hazards in Europe, and this shows how Turkey and Greece actually have some problems with earthquakes. We expect some accelerations in excess of 0.5 G or more, right? Including Istanbul. This is the list of the current, I would say, last 3 decades earthquakes occurred in Turkey and resulted in many big problems, including some life losses, huge life losses, including the last earthquake in Samos Island. The problem is actually, we have some older buildings that were designed to older structural codes, and unfortunately, when compared with today's code, we have serious problems, especially for short period buildings, but in some cases, in case when we have some soil amplification like we had in Izmir area, so we may also have some problems in the long period buildings as well, okay? So fortunately, we have recently a current code, seismic code in Turkey, effective since January 1st, 2019. This is a new, completely restructured code with 17 chapters, including newly added ones as follows. For example, we have a new addition in terms of lightweight steel buildings, timber buildings, tall buildings, seismically isolated buildings. This is the first time we have in our code, and simplified design procedures for regular buildings. And also we have an updated probabilistic seismic hazard maps for Turkey as well. This is the web link. You could actually go there and see the seismic hazard map. This is a very well-known seismic hazard map showing also with the M7.0 earthquake in Samos area. So this is just a big picture. I mean, we have many guests all around the world. So this is the big picture, what we have in Turkey. These are the potential reasons for damaging buildings: poor material properties in concrete and reinforcing bars, irregular structural systems in plan and elevation, torsion as well. So pounding or hammering of buildings in series, inappropriate reinforcement arrangement in reinforced concrete members, of course, non-ductile detailing, sort of lack of confinement in reinforced concrete members, insufficient cross-sectional dimensions, both in beams, columns, as well as in shear walls, as Professor Yüksel mentioned about that. Short or captive columns, quite common, and which is the source of an architectural design project, as you know very well. Short beams, not as common as short columns, but we have also sort of short beams damaged in the previous earthquakes. Insufficient lateral stiffness resulting in excessive P delta effect. This is quite common. We have only moment frames up to 5, 7, 8 stories without shear walls. That is a big problem. Soft or weak stories, this is another big problem. And of course, local soil conditions like liquefaction or soil amplification, as we observed in Samos earthquake. And among these, many non-ductile reinforced concrete frame buildings without shear walls experienced heavy structural damage, or they collapsed during the past earthquakes. So this is just a map. I mean, this is not new. This has been prepared in around 2000, and also the website is available here. Although the report is in Turkish, but series soil amplification maps were prepared, but the problem is as always before the application of these information in the construction market. So that earthquake was a very big earthquake actually for the region, and unfortunately we had serious problems in our Izmir city, and the epicenter to Izmir distance was about 70 to 80 kilometers, and the PGA values were about 0.18 G maximum. Actually, if you look at the new code, you would expect a 0.45 G or so as a design value for those buildings, especially with some buildings up to 10 or 13 stories. I would say those are some mid-rise structural systems. And then what we have observed in this earthquake, we have only experienced 40% of the design acceleration in that area, okay? So these are some very quick, in 1 minute, images from the area. Some of them are shown by Professor Yüksel as well, so I don't want to go into details. For example, especially for architectural-based damages were quite interesting. So no frame action, for example, as shown here. Also, non-structural damage were also very common. And also, we have apps using everywhere, especially just after the earthquake, making an reconnaissance investigation. So those help you a lot, especially the maps to take information during the construction site, okay? So I would like to stop here. These are just images, and I would like to go into the session. This is an I2U building equipped with seismic energy dissipation braces. These are unbonded braces or buckling restraint braces. So I stop here my presentation. Okay, so the next speaker to keep up with the program, I would like to introduce Professor Fabio Biondini as the next speaker. Professor Biondini will be presenting life cycle seismic resilience of bridges and road networks. Professor Biondini is a professor of structural engineering in Department of Civil and Environmental Engineering in Politecnico di Milano. His research topics include computational structural analysis, structural reliability and optimization, earthquake engineering, life cycle engineering, and he's the recipient of many honors and awards, including very well-known institutions, for example, ASD Fellowship and similar. Yes, Professor Biondini.
So thank you. I'm going to share my...
Yes, you could share your, yeah.
Okay, great. Can you confirm that you can see my screen?
Yes, that's perfect. Thank you.
So thank you for a very kind introduction. So honorable authorities, Professor Yüksel, Professor Sam Salik, distinguished colleagues, ladies and gentlemen, good morning. First of all, let me thank Professor Yüksel and all organizers for kind invitation to deliver this speech. I'm extremely glad and honored to contribute this event in memory of Professor Ibrahim Demir. My presentation today deals with life cycle seismic resilience of bridges and bridge networks. This is, in my opinion, a subject of high relevance and topicality in our field and quake engineering in general. And with this presentation, I would like to inform about some related research activities ongoing at Politecnico di Milano. So in recent years, as you know, many studies and news raised alarms about the detrimental impact of aging, fatigue, and deterioration processes, and particularly on bridges and transportation infrastructure networks. So the detrimental effects of this phenomena can lead over time to unsatisfactory structural performance and the impact of these processes on structural safety can be very high. And this is particularly, as mentioned, for bridges and especially for concrete bridges. Now, this situation is quite dramatic because we experienced over the last year several bridge collapses associated or related in some way to aging and deterioration processes. And these collapses are occurring with increasing frequencies in several countries, including Italy. And so the scale of repair or replacement needs is particularly large and represents a key obstacle to sustainable development of countries. This is just an example for the United States. According to the report card for America's infrastructure that is issued by the American Society of Civil Engineers, 42% of the over 600,000 bridges across the United States are at least 50 years old, and over 46,000 of the nation's bridges are considered structurally deficient, with almost 180 million trips across these deficient bridges every day. The most recent estimate puts the nation's backlog of bridge rehabilitation needs at 125 billion. That is a huge amount. This situation is shared by most of the developed countries, even if on a different scale. And to face this need, the civil engineering is undergoing a profound transition toward a life cycle-oriented design philosophy, where the classical point-in-time design criteria are revised and extended to account for more comprehensive time-variant performance indicator. And this is over the entire service life of the system. In addition, we need to take into account the several uncertainties that are involved in the problem. And also, it is not sufficient to perform the life cycle assessment at the level of individual bridges, but we need to have a wider vision, and we need to afford the problem at the infrastructure scale, taking into account the impact also on indirect consequences at the infrastructure level. Now, this is particularly important when we look at transportation infrastructure networks that are the backbone of our society, and they play an important role, particularly in the emergency response to seismic events and related hazards. As the most vulnerable components of road networks, the damage of bridges may involve, as mentioned, direct economic losses due to repair interventions and maintenance, as well as indirect losses due to traffic delay and network downtime. And we need to take this into account. So one of the concepts that is more efficiently capturing all these aspects is, as we know, resilience. Resilience can be regarded as the ability of a system to withstand the effect of disruption event and to recover promptly and efficiently the pre-event functionality. So if we have a certain event at a given time instant, the functionality of the system, for example, looking at road transportation networks, this could be the traffic capacity, this will suffer a sudden drop. And this drop of functionality is depending on the robustness of the system. Then after a certain idle time, we have a recovery process that, if feasible, will bring the system to the original functionality level. And the area under the recovery curve associated with this functionality diagram is generally regarded as a measure of resilience. So in this way, resilience can be quantified. Now, how to approach the problem for infrastructure transportation networks? So we need to, of course, build a framework that is capable to integrate the seismic assessment of individual structure and the post-event analysis of the network functionality in terms of traffic capacity. And this has to be evaluated in order to quantify seismic resilience under uncertainties. So we have basically three different steps into the process. We need to evaluate the individual bridges by means of probabilistic approach in order to account the uncertainties involved in the problem. And so we need to perform a bridge seismic assessment. And The second step is moving at the infrastructure level, and we need to quantify the road network functionality. And after we have the road network functionality based on the hazard analysis, we can evaluate the impact of hazard event, and in association with repair activities, recovery processes, we can perform in the third step the seismic resilience assessment. So when we look at this problem, we should not forget that a seismic hazard is, of course, interacting with several other hazards, particularly the environmental hazard. And this is making resilience time dependent, because this very simple example here, you have the comparison between non-deteriorating system on the left side, for which only seismic hazard is considered, right side, the deteriorating system under deterioration processes. For example, in the application, we will focus on concrete bridges under corrosion. If you have non-deteriorating system and you have a certain seismic event occurring at two different time instants, the same event will produce the same loss of functionality. And if you apply the same recovery process, you will get the same level of resilience. But when you look at deteriorating system, because of the effect of damage, the same event occurring at different time instant will have a different impact, and also the recovery process is expected to be different. And this makes, as mentioned, resilience depending on the time of occurrence of the seismic event. And this has to be considered into the assessment. So how to incorporate this interaction between seismic and environmental hazard in the resilience assessment? Let's look a little bit more in detail to each step into the process. So we start with the analysis, with the assessment at the level of the individual bridge, and we need to compare the expected intensity measure, intensity level for the hazard. In our case, we are considering seismic events, and in terms of damage induced in the system. So comparing an intensity measure with a damage measure, we can identify different damage states and evaluate the probability of exceedance of a certain intensity level associated to that states. Here you have an example of bridge assessment. This can be performed using different methodologies. One of the most efficient is incremental dynamic analysis, where we can build this type of capacity curves, having the seismic intensity versus a damage measure. For example, for bridges, we can look at the pier drift as a damage measure. And if you incorporate the uncertainties involved in the problem and you perform a simulation, you can have a sample of outcomes as it is shown here of capacity curves. And by probabilistic processing of this data, you can build the probabilistic distribution of the seismic intensities associated with different damage states. For example, in terms of drift level. Here, as an example, you have 4 damage states associated with slight damage, moderate damage, extensive damage, and structural collapse. Slight damage associated with the occurrence of yielding in the most damaged component, and the other damage state to yielding and a certain percentage of plastic strains, always in terms of drift. And if you elaborate probabilistically this result, you can build fragility curves as those are presented here below for each damage state. And these fragility curves obviously is representing the probability of exceedance of a certain intensity level in relation to the considered limit states. Now, when you incorporate also the effect of deterioration, the fragility curves will evolve in time. And this evolution in time is also depending on the damage level. For example, here you have a comparison for the slight damage and the structural collapse, and it is expected that, for example, structural deterioration, if this is the time variant deterioration process that we consider, is making an impact that is more severe for the structural collapse rather than the slight damage. After you have the assessment of individual structure, you need to evaluate the functionality at the infrastructure level. And so you need to relate the damage state of individual bridges to decision variables that are associated with traffic restrictions. For example, when you look at the impact of a certain traffic restriction on the infrastructural level, you need to evaluate the functionality. And the functionality can be assessed in terms of traffic capacity. So it is important to understand which is the type of restriction for having the corresponding impact on the traffic flow over each individual bridges. For example, depending on the damage state, we may have different traffic restriction. We may have a weight restriction under slight damage. We can have one lane open only under moderate damage, emergency access only if you achieve extensive damage, or you may need to close the bridge if a structural collapse limit state is attained. And depending on the type of traffic restriction, you have an impact in terms of traffic capacity, the traffic flow over the single bridge, and the entire traffic capacity at the infrastructure level. So the next step into the process is looking at the functionality assessment and resilience quantification depending on the recovery processes. So the traffic functionality could be evaluated in terms of total travel time, that is the minimum time that is necessary to get a certain destination from a given origin within the network. And this functionality can be evaluated in a normalized way, in a dimensionless form, as it is shown here. This functionality Q is taken as the ratio of the total travel time of the undamaged system over the same quantity associated with the damaged system. So depending on the traffic restriction, you may have for increasing level of damage, you may have an increasing loss of functionality according to a stepwise function as it is shown here. And you, of course, need to plan a certain repair activity after damage occur. And the type of recovery is depending also on the level and the type of damage. So we may have different recovery processes and the recovery curves for each type of, for each level of damage for each limit state. So you can see here different examples for the damage states that we considered before, slight damage to structural collapse. And of course, as the damage level increase, the rapidity of recovery will decrease. And this has to be taken into account when you formulate the recovery curves depending on the type of damage. After you have the recovery model also established, you can assess the seismic resilience, and the resilience is given by the integral over the functionality profile over a certain time horizon of the functionality diagram. And since the traffic restriction will be associated with some drop of functionality, this integral can be also easily computed as a sum, because we have, as we have shown before, a constant stepwise relationship. And this leads also to constant stepwise diagrams for the functionality over the recovery period. And according to the model that we presented before, associated with the integral of the functionality profile, we can establish a measure for the resilience for each level of damage. This level of resiliences that you can get into this way are characteristic of the system. We are still not considering which is the probability of having a certain damage state. So in order to get resilience measure that is also associated with the type of hazard to which the system is exposed, we can evaluate the resilience by weighting the resilience level associated to each limit state by using as weights the probability of damage for each level. So let me show very simple example at the beginning. This is an academic example, but it's very effective to show which is the role of the different aspect of the problem. And in particular, we are considering here only an highway network with only one bridge unit consisting of a single bridge or more bridges in series. And this bridge unit is located on the main highway, and we can consider an isolated highway or an highway with a detour, or an highway with a detour and a re-entry link. And these three different network architecture are of the same type, but characterized by a different distance of the re-entry link from the bridge unit. And this also plays an important role in the resilience quantification. Here you have just the traffic parameters associated with the problem. And these are for each type of branch into the network, the highway road, the secondary road, and the re-entry link in terms of length, number of lanes, speed factors, and also the traffic flow associated to each different type of user. So light vehicles, heavy vehicles, and emergency vehicle. The bridge considered here is a reinforced concrete continuous girder bridge. You can see here the cross-section of the girder. The three piers are characterized by a circular cross-section. The bridge is has a total length of 200 meters, four span with 50 meters each, and the bridge pier are 14 meters tall. The bridge is considered exposed to chloride ingress and corrosion processes over time. And so the seismic assessment is performed in time by using incremental dynamic analysis, taking into account the uncertainties involved in the problem. So here you have the probabilistic model that is summarized in terms of earthquake action that are simulated by using artificial accelerograms in a large sample in order to account for the uncertainties into the seismic hazard. And we have also in this table summarized the random variables that are considered to take into account the uncertainties in the geometrical and mechanical factors that are associated with the problem, and including also the uncertainties into the damage processes in terms of diffusivity of chlorides, corrosion rate, and also other factors. Here you have the results of the fragility analysis at the initial time when the system is intact, and top left you have the result of the incremental dynamic analysis in terms of capacity curve for a sample of 8,000 simulation. And for the 4 limit states that were introduced before, you can see how they are distributed over the capacity curves, and they are also elaborated in order to get the fragility function. This is at the initial time, but of course, when you are looking at the problem in time, you need to take into account the effect of corrosion, and the fragility curves are evolving, for example, for the extensive damage limit state as shown into this diagram. In the table, you have the same type of evolution for the different limit states for discrete time instance. So you can see that the impact of deterioration can be extremely relevant, and this may impact seriously the traffic functionality under the occurrence of seismic event, and in turn the resilience. Here you have the recovery processes that have been considered for these examples, from slide damage to structural collapse. These recovery processes have been established in order to incorporate the main features of the recovery process associated with the type of recovery, the resources that are available, the expected time necessary for the repair to be completed, and so on. And under this recovery process, you can get the functionality profiles for each one of the network that is investigated here from N1 to N5. And for each network, you have the functionality profile associated to the 4 different limit states. It is obvious that if you consider an isolated network, when the bridge is suffering even slight damage, you have a complete loss of functionality. The recovery will be quite quick, so the resilience is not affected very much, but it is quite important this short period under no functionality of the entire system. So the impact in this case also of slight damage is may be extremely important. Of course, as the damage level will increase, you have the same type of problem with the entire loss of functionality, but also with higher impact in terms of resilience over the time horizon. Here, considered of 1 year. And when you move to the other networks that are involving the tour, of course, even under the structural collapse limit state, you will not lose entirely the functionality because you have the detour that is always possible, but the detour only is not ensuring a suitable level of resilience under extensive damage or structural collapse damage level. And in order to improve resilience, re-entry link can be very effective. And as you can see here, as the link is becoming closer and closer to the bridge, you can increase the functionality and resilience. And this is showing how the network architecture can play an important role in ensuring a suitable level of resilience. So we have to look not only to individual structure, but also to the role of each individual structure into the entire system. Here you have the assessment of the resilience as mentioned.
Professor, sorry, Professor Biondini, is it possible to wrap up everything?
Of course, of course.
Okay, thank you.
This slide is showing the resilience assessment. As mentioned, we have the different resilience level, and we can evaluate in the resilience in probabilistic terms by weighting the different levels using the damage level associated to the different states, and the damage probabilities can be computed by difference of the fragility functions. Of course, in time, we have the evolution of the fragility function, and therefore the damage probability that are time variant are also affecting the resilience that is evolving in time as it is shown here. Just a comment on this diagram that is for the network N2. You can see that the impact of deterioration is reducing significant resilience, but the presence of the detour is leading to have a minimum threshold of resilience that is always guaranteed because of the redundancy of the system. Of course, similar consideration can be done for the other networks. I'm going quick to the conclusion. And I'm going to skip these other examples that I prepared. Perhaps I prepared too many slides here. And so in conclusion, we have seen that aging and structural deterioration may reduce over time significantly both seismic capacity of bridges and the functionality of road networks. So the combined effect of seismic environmental hazard makes seismic resilience depending on the time of occurrence of the seismic event. So the impact of environmental exposure depends on the earthquake scenario, and related seismic exposure of the most important bridges in the network should be taken into account. I didn't show the example that I prepared for this aspect, but of course, when you have more than one bridge into the network and you extend this kind of evaluation to complex network, the interaction between the damage states of different bridges into the system is very, very important, and also the spatial variability of the seismic hazard has to be incorporated into the assessment. And the effect of deterioration can be reduced by also considering road network upgradings, not only the upgrading and repair of individual bridges, but you can also upgrade the network. Now, the results show the importance of a multi-hazard, life cycle oriented approach to seismic design of resilient structure and infrastructures, considering when possible, also network upgrading, to limit the effects of aging and deterioration and establish effective and rapid post-event recovery procedures. So with this, I close my speech, and thank you for the attention.
Okay, thank you so much, Professor Biondini, for this very thorough talk on very popular topic of resilience. We have seen that the quantification of resilience is very difficult for years. You know, we have made some work on that for non-deteriorating and deteriorating systems. Thank you so much for this presentation.
Thank you.
Do we have any questions from YouTube? We have some friends. I guess we don't have this, but maybe you could actually talk a few words about quantification. Do you have any addition to that?
Oh, yeah, quantification, of course, is possible as it has been shown into the application. And of course, one important aspect is the available information on both the individual bridges and the entire network. And so this sometimes requires that resilience assessment is also developed at different stages. So you can first evaluate resilience in a simplified way based only on available information that allow to make a simplified bridge prioritization. Just let me mention that, for example, we have this project that was recently established in the North Italy with the Lombardy region, where we made a risk assessment of a sample of about 400 bridges. And we also selected a number of pilot bridges, namely 9 bridges, to design and implement monitoring system in order to also support the risk assessment procedure. And this was developed only on a documentary basis, because the available information at the initial time was quite limited. And but also with this limited information, we have been able to perform a network analysis, a traffic analysis, also to investigate the impact of possible failures of the bridges into the network on the effects in terms of monetary losses, and also the effects at the societal level. And this allowed to make a bridge prioritization into the system. Of course, this kind of assessment can be brought to a higher level as more information become available, and you can of course move toward more and more refined seismic assessment of individual bridges as in the procedure that presented using incremental dynamic analysis. So we are here at 2 different state of the system, because we have in this case an assessment made only on a documentary basis. In the examples that I presented, that we assume full information on the system. So the available information is absolutely the key point in order to make the resilience quantifiable, and also to provide accuracy to this type of assessment.
Okay, thank you so much again for this very interesting presentation. And now we need to move on to the next speaker. Thank you, Professor.
Thank you once again.
Okay, thank you. So the next speaker is Professor Toru Takeuchi of Tokyo Institute of Technology. And Professor Biondini, would you please stop your All right, thank you. So Professor Takeuchi is a professor of Department of Architecture and Building Engineering at Tokyo Tech. His research focuses on steel structures, response-controlled structures, and structural design. So he is the recipient of many awards, especially in Japan and internationally. He's the co-author of a very recent book of buckling restraint braces and applications. Also, he's one of the founders of buckling restraint braces in the world. And he's a member of Science Council of Japan. He's been the vice president of Architectural Institute of Japan in between 2018 and 2020, and he's the Director of General Affairs and also the Chair of Managing Committee on Chelan Spatial Structures. Yes, Professor Takeuchi.
Thank you very much.
Thank you for joining us again.
Yeah, can you see my screen?
Yes, perfect.
Okay.
Go ahead.
So my topic is a little bit broader view for the building structure design securing a continuous occupancy. So probably all of you know that Japan is a kind of a department store in natural hazards. We have facing a big earthquake every 10 years and the big typhoon in every year, and the volcano exploding in probably the once in 100 years, and sometimes tsunami is occurs in the following the big earthquakes. And also we are expecting a big Nankai Trough earthquake. That is a maximum intensity will be a magnitude 9, and that we will expect it to a big tsunami of the 10 meters to 20 meters widely to covering the west part of Japan. And also that is expecting 70 to 80% probability into 30 years. That is a very fair. And also the climate changes increasing the number of the size of the typhoon hitting Japan every year. And we are facing every year's flooding in some cities in western part of the Japan. So how to dealing with these ones? Of course, we need to reduce CO2 emission. And this report says in last year, we had facing the pandemic of the COVID-19 and temporarily reducing CO2 emission that 100 million tons per day in the world is reduced by 20%, mainly because of the lockdown by the China and the US and India. These three countries cover the more than half of the world the CO2 emission. But now it's going back to the ordinary ranges. So it's not easy to reduce CO2 emission. So, and also after the big disaster, we are facing on a big amount of the disaster debris or waste. Great Hanshin earthquake produced 15 million tons of debris, and the Great Tohoku earthquake is a double of this. And the expected Nankai Trough earthquake is 10 times, 3,150 million tons of debris or waste will be expected. So of course, with these the debris, it's very hard to reconstruct the cities or the cleanup and the rebuilding. It takes like 10 years for the people to keep evacuated to the temporary houses in left side. So now we think we must all strive to reduce our CO2 emissions. However, we must also be prepared for the potentially unstoppable increase in natural disaster risk associated with a changing environment. And there is a nice need to be built cities that do not need to be evacuated, consisting of robust and resilient facilities that guarantee continuous use or continuous occupancy against multiple hazards such as earthquake, typhoons, and floods. So that is similar to the previous talk. And also the COVID-19 pandemic has the potential to accelerate the changes in the way of living, working, and education using the digital tools that we are now using. These are facilities as houses and the offices and the universities need to be designed to be flexible and robust against these changing social demands. So in the structural design wise, I'm proposing to using kind of a grid skin structure we call that, providing the seismic resistant the element on the outside of the building in the facade. That is a very rational way for the structural demand that less bending loss comparing from the providing these braces in the core area. And that is more robust, and also the architecturally free internal space that is changeable for the function of the building after the completion. And but we need to design the building facade deeply collaborated with the architect designers. So in my the universities, I have worked in many facilities, like this is a library in our university. The building's library in the underground, but the superstructure is designed for the student for the perimeter structures, grid skin structure, to allowing the internal spaces free. And also we are doing some research laboratory offices covered by the solar cells of the 4,050. It can generate their own electricity in sunny days. And we provide seismic elements, seismic energy dissipation braces around the buildings and keeping the internal space free. And also to keeping the main structure supporting the each floor in elastic even for the large earthquakes, for the to proving continuous occupancy. For the same, the concept was applied for the concrete structure. We had to design to the perimeter zone is covered by the shear wall is a checker pattern that working as a bracing action. But this is a little bit fragile system. So even after this shear wall is collapsed, we to introduce to ductile moment frame backwards of the shear wall, and they're keeping the floor system even after the collapse of the shear wall, and keeping the internal space open as possible for into keeping multiple functionality. And also we have to take care about the damage concentration of the caused by the earthquake. So we remember that in the Great Hanshin earthquake occurred, causes many mid-level collapse of the buildings. That is the structural the characteristic and the seismic function is seismic energy tend to be to concentrate on weakened stories that easily to lead to the story collapse to the P delta effect of typical damages stories. So we need to prevent such kind of a collapse. So we worked with United States researchers for the introducing kind of a control locking frame system, including a spine frames to distributing the damage to all the floors, and also to give a function of self-centering by the PTY or energy dissipation fuse for the dissipating energy. So this system was applied to the one of the buildings designed by us. That is a 5-story building, but we introducing elastic spine frame inside the center of the buildings, and that is all the locking and the dissipating energy for the vertical or backward restraint clamp. So this is the one of the concepts that is stable to avoiding story collapse. Also, this grid scheme, the concept is applicable for the retrofit of existing structures. The buildings, I'm now sitting on the 4th floor of these buildings, used to be very old, 50 years old buildings, and there is a damage, collapse risk of second story. So we are to apply the energy dissipation braces, buckling restraint brace, to the south face of the buildings, and together with new skins to control the environmental impact. So that we call the integrated hazard design, to applying the part of the design, not only architectural and not only structural, but also architectural and environmental design. So we are now recently working with Professor Cherik that how to retrofit the concrete old buildings into using energy dissipation braces. So energy dissipation braces is advantageous to comparing from the ordinary strength-based design because they can dissipate the energy. Also, the reaction forces is moderate than strength-based design. So, but the connection between, for example, BRB, buckling restraint braces to the concrete core is, concrete frame is not easy. So we introduced an elastic steel frame that is securing self-centering function. Also, the working for the damage for the moderate damage for the existing frames. And also the composite actions between steel and the concrete is need to be evaluated easily. So we are recently working for the to estimate using a very precise model, so modeling connection zone, and compared with the mock-up test carried out by the Professor Cherik's the groups, and the red line is proposed analysis. That is basically very much well matched. And then using this, we have proposed easy evaluation method for the composite effect. This line is simply added steel and concrete, and the complete composite is in the horizontal line, 7 times of the additional the function. But actually, the actual the composite action is smaller than that. That is a vertical axis, almost 3 or 4 times of simple addition. So this rule can be to propose for the evaluate easily for the estimate the exact the composite effect. So these are energy dissipation based seismic retrofit to add the additional equivalent damping of 20%, and also the effective to reduce the residual drift angle after the earthquake, rather than just adding energy dissipation process. So to achieve immediate occupancy after earthquake, minimize uncertainty of collapse mechanism, and concentrate input seismic energy to replaceable fuses and keep self-weight supporting system undamaged. That is very important because most of the building is damaged, collapsed by their self-weight and releasing potential energy of self-weight. So if they can keep the self-weight supporting functions, they are never to collapse. And they also establish a reliable energy dissipation fuses. Probably for the areas where the flood or tsunami is expected, we need to introduce concrete buildings, concrete frames for the lower areas expecting flood or tsunami, and upper ones, middle level isolation can be introduced for the preventing upper layers if you introduce steel or wooden frames above that. And also we are now to try to introducing algorithmic design into these designs. So this is an example for the grid skin structure covered by the concentric braces that is replaced by the BRB for the given object function using the computer algorithm. So we are using island genetic algorithm using a generalized response spectral analysis that is much shorter time than the time history analysis. And then they are to selecting the optimize the layout of the BRB the position using to truing many types of many cycles of the mutation. And some example is minimizing a story drift angle. They can distribute the BRB in evenly distributed along the height, like left. And if we set a minimizing a buckling risk of the concentric braces, they can provide the BRB in concentrated on some level, like a mid-level isolation. Instead, the story drift angle is increasing. So another function is it's the controlling. It's interesting in the left down. It causes minimizing buckling risk, lead to base isolation, and right top is minimizing drift with buckling penalties. We can to lead to kind of spine frame, locking frame between BRB is connected to locking frames. So that is interesting. And this algorithmic design is applied to actual building for the concert hall, 20,000 seats planned in Yokohama area. They covering a very huge steel roof is supported by the supporting structure. We need to provide 350 BRBs that can be reduced using this kind of algorithm. And we are firstly selected the position of the bracing position. Then to change it where we can use a BRB, where we can use concentric braces without buckling. So and minimizing the number of the buckling restraint braces and keeping their functionality. So as a result is obtained like this. And the mainly the BRB was concentrated at the middle level of the supporting structure. So the number of the 350 of the BRB is reduced almost to the half, and the optimized solution was cost was reduced, and also keeping the solid drift angle around 1% against the rare earthquake, that is a design earthquake level. And now the construction is going on as it is and completing early next year. And we are also applying this technique to the planning high-rise buildings. Right side is 400-meter height, huge office buildings planned in Tokyo area. That we expect is the highest buildings in Japan. And we are planning to make a suite for this the grid skin structure and inserting the damping devices between them. So the depth of the suite and also amount of the damping devices is we can seek for the optimized conditions using same algorithmic studies. Okay, and also we are detailing with the design of the BRBs, especially for the long ones, is to keeping to reading the fracture model, and also the timber BRBs testing is investigated. So finally, I'd like to introduce, we recently opened the MOOC program for the, to introduce Japanese architecture and structural design. And the studies in these half years, we are listeners of 3,000 people listened from 140 the countries. So please to see the promotion video. Okay. Oh.
Have you ever wondered how tall yet beautiful buildings and lightweight yet stable roofs are realized in areas with a high seismic hazard? In this course, we will look at the evolution of structural design and architecture in Japan. This story starts with the incombustible Tokyo city after the Meiji Revolution before moving on to the precast structures of the metabolism movement, the emergence of shell structures, and concludes with the contemporary transparent architecture. We will then delve into the structural design and retrofit of several unique Tokyo-Tech campus buildings. We will learn how these structures were made earthquake resilient using technologies like the buckling restraint braces, locking frames, and seismic isolation, while incorporating sustainability and aesthetic considerations using concepts like the integrated facade engineering and grid scheme structures.
Thank you very much for your kind attention.
Okay, thank you so much, Professor Takeuchi, for this excellent presentation about damage-controlled structures. And it's always been a great pleasure to work with you. in projects. We have actually a very strong relationship with Tokyo Tech as ITU, with the leadership of Professor Takeuchi, and we are doing some research together. So especially, I'm just checking if we have any questions from, at the same time, we have a YouTube broadcast, you know, that not only the Zoom participants, but I'm just checking if we have any questions from the audience. No, if not, I was just curious about the future of buckling restraint braces. Do you want to add more on that? A few minutes.
Mm-hmm. Okay. For the recently, we have to study for the longer BRBs, and I'll show you the text. Okay, so recently the BRB's application is increasing, and there is a longer and longer. So we are a little bit worrying about what occurs for the very long BRBs, like a 10 meter or 20 meter. So because of the friction between core and the restrainers, it's a control like 0.1 to 0.2, even though there is some the effect of the slope of the axial forces around the core area. So that leads to pounding at the end, because in the compression is exceeded at the end, and also the tension is exceeded the center. So comparing from ordinary short BRBs, it tended to be decided by the fracture by necking at the center of the BRB. So this report is presented in WCEE, 17 WCEE last month, and probably you can find my name. The detailed study was available. Still, the video is ongoing. So if you're interested in, please see.
Okay, thank you so much. Again, before going into the next speaker, I would like to mention that Professor Takeuchi also had a leadership to publish a very interesting book on Tokyo structural design map. That is a perfect, really, guidance for especially architects and engineers. Thank you for your contribution again, Professor Takeuchi. Okay, the next speaker is Professor Ke-Chuyan Tsai. And Professor Tsai is a professor of civil engineering of National Taiwan University. He will be presenting seismic design and testing of shear panel dampers using common structural steel plates. I would like to tell a little bit on Professor Tsai. Professor Tsai's achievements include a patent for steel triangular plate energy absorbing device named as TADAS device. And he is also the recipient of Excellent Research Award of National Science Council Taiwan, International Excellence Award, James Lincoln Arc Welding Foundation. And recently, Professor Tsai received the American Institute of Steel Construction's Special Achievement Award, which is a very important award as well. And Professor Tsai is being recognized for his extensive work with US and international researchers to conduct large-scale system-level testing of structural steel seismic force resisting systems, leading to system-level verification of many of the AIAC's 341 provisions. By the way, that Special Achievement Award recognizes individuals who have demonstrated notable achievements in structural steel design, construction, research, or education. So it's a great pleasure to have Professor Tsai here. And also I would like to thank, on behalf of the Disaster Management Institute, to have him here as one of the presenters. Thank you, Professor Tsai.
Can you see my slide?
Yes, Professor Tsai.
Okay. First of all, I'd like to thank Professor Celik for inviting me to attend this very important meeting.
Our pleasure.
And I'd like to present something being implemented in Taiwan. And before this presentation, I of course like to send my sincere condolence to the losses during the earthquakes in the past, not just in Turkey, probably worldwide. Here from this map, you can see the location of Taiwan and Turkey. I think we are 5 hours apart. Using the beauty of internet, there's almost no distance between us. From this slide, you can also see the skyline of Taipei. But underneath this skyline, we have this serious seismicity in Taiwan. And this slide, of course, is not updated. You can find this shows only 110 years earthquakes occurred near the island. And you can see some of the red dots are representing magnitude greater than 7 indeed occurred on the island. And therefore, seismic engineering for buildings, it's an important issue for engineers, for educators, for researchers. So from this floor framing plan, the typical column to column spacing may be 9 meters, 10 meters. And from the floor framing plan, you can see they are adding stud columns. The termination of stud columns actually because these stud columns cannot go to the ground floor or to the basement, foundation, and therefore they have to stop these added structural members, at certain floors. So we call these stud columns, and these stud columns, of course, can enhance the lateral stiffness and the lateral strength of the system, given specific architectural requirements. And so also given the fact that this sub-column cannot go all the way down to the foundation. And therefore, you may even see there are small dots near the beam end, and also small dots near the top and bottom ends of these stud columns. And this stud column means they are not continuous. They are interrupted by the girders. So in reality, these stud columns may not be in the center of the girders. They could be offset a little bit because the architectural requirement. But some of the engineers even apply reduced beam sections, try to avoid the possible fracture of the stud column to the boundary beam connections. And that's perhaps quite understandable. And however, I think the issue of fracturing the stud column to the girder connection can be avoided if we adopt the so-called 3-segment shear panel dampers. So the presentation today is pretty much about how we like to engineer, know about this possibility, and how we conduct the test and the design and the analysis of this type of structural members. And obviously, the difference and the similarity between the stud columns and the shear panel dampers is that both enhance the strength and stiffness of a given moment frame. And however, both two type of elements, stud column or shear panel damper, they will increase the fractural demand on the boundary beam. And in the same time, it's likely if the beam size is increased, then the boundary column may have to be increased because the requirements of strong column, weak girder design philosophy. And however, if shear panel damper is adopted, there is a possibility to decouple the stiffness and the strength of this particular type of element. And assuming that this shear panel damper is resisting the lateral force, and it's likely that the bending moment distribution is like shown here, and the shear will be constant. So it's possible to design this member using a thinner or weaker inelastic core here, because it's 3 segment. So we would call, perhaps, let me use next slide. So the top and bottom can be designed to remain elastic, and then the center portion can be designed to go into inelastic range under the lateral imposed force or displacement. And therefore, the distribution of shear and the distribution of bending moment can be easily calculated. And therefore, it's possible to make the inelastic core IC weaker, and then conveniently design the elastic joint to remain elastic, by just assuming certain material overstrengths and the strain hardening effects of the inelastic core. So the proposal of fabricating the shear panel damper using common steel plates is using very common SN400 steel for the inelastic core, and for the web of the elastic joint, and for the flange of the entire SPD, SN490 can be applied. And then for the inelastic core web, one needs to apply stiffeners, and these stiffeners can be either SN400 or SN490. And of course, connecting the elastic joints to the boundary beams becomes much easier, because it will remain elastic. So either bolted or welded connections can be implemented. And of course, the welded type, although could be more expensive to adopt in the job site, in the construction site. However, the loss of stiffness may be much smaller comparing with the bolted joint. And so the strength of material approach is considered here. Here includes the use of the shear yield stress 0.6 Fy, and the shear area, assuming the whole depth of the Y flange section and the thickness of the inelastic core web, and multiply this shear yield stress, and then considering additional possible material overstrengths and strain hardening when large inelastic deformation are developed in the inelastic core. So this Vmax should be a pretty good and pretty conservative estimate of the peak shear possibly developed in the SPD. And having this maximum possible shear strength, the capacity design principle can then be applied to check to design the elastic joint. And here, this equation simply shows that in the elastic joint, you should check the shear strength versus the demand, and you should check the moment capacity of the elastic joint against the demand, and considering the maximum possible shear developed in the web, in the elastic core. However, one must check the moment capacity, moment demand versus the moment capacity at this elevation dotted here, because here the web may be undergoing large inelastic deformation, and therefore in computing the bending capacity at this particular elevation, the moment capacity actually is not as the moment capacity shown here. So you have two moment capacity you have to check at the end of the inelastic core and at the end at the boundary between the elastic joint and the boundary beam. So you have two elevations to check this bending capacity versus demand. And shear panel damper can even be fabricated by making a continuous long wavelength members, and this member, of course, can be a roll shape if it's properly chosen, and it could be a build-up section, of course, and then just cut to fit. Maybe for typical buildings, this SPD should be less than 3 meters tall, and then one can then build up end stiffeners, and then could strengthen the elastic joint by using double plates. And then, of course, inelastic web stiffeners must be devised. So recently, of course, we have applied this fabrication scheme using double plates. Here is just to show that the various steel plate used for the web, for the double plates, and for the flange and the stiffeners. And in the past, we have been able to conveniently test a number of SPDs because we have this multi-axial testing system in Ankara. These various pictures shows the features of the mats, and we could, of course, use this setup to apply lateral force and the fixed end translations. And so this member, of course, in plane has 3 degrees of freedom, and using 4 actuator, it's because we want to have a little bit larger lateral force. So we use 2 horizontal actuators, but another 2 vertical actuators. So actually only 3 degrees of freedom. We need only 3 if the capacity of the actuator are big enough. So the typical specimen in the past, among about 20s, it varies the height of inelastic core, varies the details of the stiffeners, and of course vary the strength of the inelastic core. Sometimes we use low yield strength steel for the inelastic core web also. A typical height of the SPD is 2.6, considering a typical story height of a building maybe 3.4 meters. So 2.6 has been pretty much the common height for the SPD specimen we have tested. In this particular example, it shows 2L1T, means 2 longitudinal stiffeners and 1 transverse stiffeners. And this shows the thickness of the elastic joint web and the thickness of the inelastic core web, and it is steel grade here. And this particular specimen, of course, are pretty much identical, except there is no transverse stiffness. So it's 2L and 0T. And I'm using these 2 examples. We're using very standard loading displacement recommended in the AISC 341. Pretty much following the protocol adopted for the welded moment connection test. And this shows a typical test using the mats. Clearly shows the design of the specimen has allowed the inelastic displacement completely developed. And you can also notice the stiffened T on the top and bottom end. That's because we need to distribute the force from the specimen to the top and bottom fixtures, and that's why we use these T-shaped stiffeners to distribute the load, because the anchor bolt location is not that suitable. And this is just to compare the difference between these 2 particular specimens without transverse and with 1 transverse. And the difference, of course, is there, but actually judging the peak, the core rotations, they are very much similar, about 11% radians. So you can see the typical failure of the specimen, of course, started from a slight buckling of the stiffened inelastic core web, and the tearing of the stiffener, between tearing of the base metal of the inelastic core web near the juncture of stiffener welds. And this is to show that these type of hysteresis response from the test can be nicely simulated using finite element analysis. And of course, you need to use quite a number of shell elements in this particular case. And then, of course, the fracture is not captured by the finite element analysis. And in addition, some general purpose nonlinear frame structural analysis software like PISA 3D, if the element is able to catch the shear hinge, the shear yielding, then the SPD can be represented by using 3 beam column elements. And each of them has their bending and the shear hinge properties. And then, of course, using such kind of general purpose program, one needs to specify the shear area of each segment and the moment of inertia of each segment. So this is to show that the calculated stiffness is based on this equation, considering the top and bottom are free to rotate, but only translate. So it includes the shear deformation and the bending deformation of each of the 3 segments. And then clearly shows general purpose nonlinear frame analysis program can simulate such kind of 3-segment steel panel damper if shear hinge and bending hinge are properly implemented in the element. In addition, of course, the material model must be able to simulate the kinematic. I combine the isotropic and the kinematic hardening property of the inelastic core. And then for practical purposes, maybe the 3-segment may not be so desirable, and therefore, actually, the 3-segment member, the 3-segment SPD can be further represented using just one element, just one section. And of course, you need to find equivalent sectional properties that include equivalent moment of inertia by using this Q factor. And this Q factor, of course, is a function of the height ratio, the alpha, the value of alpha. This alpha can be 1/3 or 1/4, whatever. And then the moment of inertia of the elastic joint and the inelastic joint. So you have this beta. Beta, of course, is greater than 1 because the elastic joint is stronger than the inelastic core in terms of moment of inertia. And in terms of shear, you have similar transformation. You can transform the effective shear area by using these Q factors. And this Q factor is a function of the height ratio alpha and the shear area ratio beta. So in fact, this member has 6 Q values, 2 bending and 2 shear in each strong and weak direction, and then 1 axial and then 1 torsion, twisting of the member. So you have 6 Qs. So it's not very difficult to calculate using this equivalent transformation. Okay, anyway, so after the transformation, you can get this so-called one section effective stiffness using these Q factors. So these Q factors simply allows you to do some parametric study here. The final effective stiffness is represented using this inelastic core, moment of inertia, inelastic core shear area times the Q. And then you can perform this parametric study. This parametric study shows that if you keep the SPD strength unchanged, means you can now decouple the stiffness and the strength. You keep the strength unchanged. But if you change the beta value, beta V, for example, you increase the shear area of the of the elastic joint with respect to the inelastic core, you get a increase of the stiffness. The stiffness increase is represented by the actual stiffness of the 3-segment SPD against if the pore height has no, it's just 1 segment. Okay, so you can see for the height ratio ranging from 0.2 to 0.6. Of course, the shorter the inelastic core, the bigger the bigger elastic effective stiffness. And this is just to show you by changing the shear area, namely the web thickness of the elastic joint, you get the increase of the effects of stiffness increase. So using this one section representation, you can easily perform this parametric study. But one must know that you have to make the inelastic core height reasonably long, not too short, because of course the shorter, the bigger the stiffness. But when you have a very short inelastic core, you are likely to increase the deformational demand under a given story drift. So I think we are recommending this high ratio of 0.3, between 0.3 to 0.5, because this possible amplification. So to implement such SPD to a moment receiving frame, for example, in this example, 6-story building, we of course suggest if in the transverse direction, the stiffness and the strength is desired to increase, and then the best location of SPD probably here, because it has less tributary gravity load also, and noted that the location of the SPD should be laterally braced. So of course you need to proportion the inelastic web according another depth according to the shear strength, and then determine the elastic joint web and the flange thickness using the capillary design principle we just discussed. And then, of course, in selecting the elastic joint webs and the flange, you need to consider the width to thickness ratio per seismic standards. And then you have to design the inelastic web stiffness based on the story drift demand. And here, I think we should give the credit to the AIJ and the AISC provisions. They have very good recommendations on the stiffeners. In the AISC provisions, we can conveniently apply the stiffeners for the shear link in the eccentrically braced frame. And then you need to apply the capillary design on the boundary beams and the panel zones, and then make sure the lateral torsional buckling of the SPD is not an issue. And then make sure you may have to increase the beam size because the demand coming from the SPD. And then make sure a boundary column and a boundary beam are properly proportioned based on strong column with beam scenario. But I should wrap up.
Yeah, would you please conclude one?
Yes, I'll wrap up.
Okay.
Okay. Thank you. Yeah. So this is just to show capacity design can be applied to find the demand on the beam, and then check the possible location of hinging. And using the gradient, you can check possible shear yielding and make sure capacity design is all met. And then you should check the panel zone using the maximum force coming from it. And then you get all these beam sizes and SPD sizes. And actually, you can actually perform optimization because you have all these members. And then you know the flexibility coming from the panel zone, coming from the SPD, coming from the beam. And so you have all these deformations. So stiffen the SPD is not necessarily the only way, because if you have a very flexible beam, and then the drift control may be an issue. So you can perform optimization, and you can know, the result, assuming the beam is 9 meters, and the various shear strengths of the SPD give you these boundary beam sizes, and the web of the beam, and then shows you varying the strengths of these SPD, actually you get a solid drift when the shear strength Vy of the SPD is reached. You have this solid drift ratio. And you can see if you want to increase the stiffness using the optimization, you could increase the stiffness by reducing the drift by almost 100%, but increasing the weight only 15%. Okay, I need to close. Test shows the clear design method for the SPD it's okay. The difference between the two specimens introduced are minimum. And the one element model can be applied for critical parametric study. And finite element analysis, of course, can capture, but only the issue is the buckling. And the three-segment stiffness, the three-segment SPD strength and stiffness can be decoupled. And therefore, it's a convenient member for use. And credit should be given to AIJ and IIC provisions. And under IC Webster inference. And optimization can be useful to get the minimum weight of the SPD versus and the boundary beam. And this SPD has been implemented in some buildings. I think it depends on if the engineers it's diligent enough to read some of our publications. Okay, thank you for your patience and your attention.
Okay, thank you for this great presentation, Professor Tsai. We have seen a lot of information about steel panel systems and their testing. Actually, they are really very nice. Do you have any questions from the Zoom audience participants or from YouTube? You can directly write on the chat box, or you can directly send me a message to me if you want to ask anything to Professor Tsai. Okay, so I have, maybe you may want to add a few words on ANCRE testing facility in Taiwan. Do you want to add something else? So as far as I know, there's a new addition to the building.
Yes.
Okay.
Yes,
Would you like to add more? Yeah.
Yeah, just to make it short, it's a public lab. So
yes.
It's welcoming people from all over the places and nationally and internationally, and therefore the facility sometimes is fully booked. So we have been lucky to be able to build another facility in southern Taiwan.
As far as I know.
Yeah.
Yeah, as far as I know, that there are numerous publications from that lab also with your leadership as well. Okay, yeah, that one. Yeah, okay, Professor Yüksel. Sen okuyabilirsin hocam. Professor Tsai, there's a question and Professor Yüksel will be reading it. Yes.
Actually, the question is this: can we estimate a behavior factor or R for buildings with SPDS?
Okay, currently we are suggesting the use of same R factor for the moment resisting frame because the nature of this member is flexural, although we are talking about shear yielding here, but it's not changing the moment resisting frame not too much. It's not changing the fundamental period not too much because the places that allows you to implement this SPD are limited in the building.
Okay, then thank you so much, Professor Sae. Then we need to move to the next speaker. But before that, we have a question for Professor Takeuchi from Professor Moretti. And she will be asking about a cost estimation of the replaceable fuses for a building if they are damaged. Professor Takeuchi, you want to?
Yes, there is a kind of two categories of replaceable fuses. For the smaller ones, it needs to be frequently replaced, but easily to move by the elevator, so not costly for the replacing. For the big large BRB or oil damper, it's actually hard to replace. But in such kind of energy efficient place, have a much larger cumulative displacement capacity than the frame itself. So actually, no need to be replaced. So in the case of the BRB, if there is a residual drift is remained, we are just changing to releasing the connection at the splice plate and making a splice plate. That's all. So in our experience, we had some the BRBs. The frames was damaged or yielded after the 211 earthquake. But in that case, the residual drift has not remained. Still, the cumulative deformation capacity was only 6% of their capacity. So just to continuously use this. So actually not replaced. so I think in many cases it's not costly actually. Yes. Is that can be an answer?
Yeah. Why not? Thank you so much for Professor Sae and Professor Takeuchi for answering the questions as well. So now we need to move on to the next speaker, Professor. We have the Professor Ioannis Psikaris here. All right, he will be talking about how can we use toppled objects to draw conclusions on the lower threshold of the ground acceleration in places where there are no recording. I guess this is going to be a very interesting topic as well. Professor Psikaris is a professor of earthquake engineering in Department of Structural Engineering, School of Civil Engineering in National Technical University of Athens, NTUA, and his research areas are seismic response and design of modern structures, historical buildings, and classical monuments, analytically and experimentally, and repairing and strengthening of structures, seismic isolation, innovative methods in seismic design, soil structure interaction, and engineering seismology. He's been the Vice President of Earthquake Planning and Protection Organization since 2014 to date. And he was also the head of the Department of Structural Engineering in his university. He's been the chairman of the Scientific Committee of Greek Annex of the European Center for Prevention and Forecasting of Earthquakes. And also he's been the chairman of the Committee for the Seismic Protection of Bridges, Hellenic Earthquake Planning and Protection Organization. Yes, Professor Psikaris, it's a very pleasure to have you here. Thank you.
Thank you, Professor Celik, and I would also like to thank the rest of the organizers for inviting me in this very interesting workshop. So my talk today will be on how we can use toppled or objects that have overturned during earthquakes in order to draw conclusions on the intensity of the ground shaking. The problem is that in many earthquakes, we do not have recordings at all places which we would like to have. Therefore, but there are several cases in which there are objects that have fallen down, like especially in cemeteries in Greece and other countries, you can find such objects. So the question is, can we use this information in order to draw conclusions for the intensity of the ground motion? Of course, the overturning of this object happens due to intense rocking during the earthquake. So let me start with the rocking problem for those of you that you are not familiar with it. So here I show you a rocking block. And as you see, I have two pictures. The left picture corresponds to positive angle of rotation, and the right one is for negative angles of rotation. And the reason that I am showing separately these two cases is because, as you see here in the equation of motion, the sign of the rocking angle inserts into the right-hand side of the equation, which means that you have a different equation if phi is positive or phi is negative. And this means, of course, nonlinearity. Another important issue of the rocking block is that you have a negative stiffness, as you can see here. So this is a very, although it seems simple, it is a very complicated and very difficult problem, the rocking problem. One of the features is that due to the nonlinearity, there is not a constant period of vibration, but the period of vibration is amplitude dependent. For example, if you have a block and you tilt it with an initial angle phi 0 and then you let it rock, the period of rocking depends on this value of the initial tilt. This is the graph that Hausner produced in 1963. Hausner was the first to tackle this problem. And you see that it depends on the value of phi, the period of the vibration. Another important issue is that every time that the block hits the base, there is an impact, which means dissipation of energy. For example, if you have a block that rocks around point O and hits the ground at this point, and the next instant it starts rocking about point O prime, as you see here. This means that there is a different velocity at the center of mass, and Hausner calculated that due to this change, the sudden change of the velocity, there is a dissipation of energy, and the new angular velocity is smaller than the previous one, and this factor, of constitution, how would you say, due to this impact, can be calculated mathematically, and this is the Hausner formula. It depends on the dimensions of the block. Due to this dissipation, if you have a block that rocks and has many times hits the base, then each time that hits the base there is dissipation, so the amplitude is constantly decreasing, and this is the graph that Hausner produced for how the amplitude decreases with the number of impacts. So if we come now to the overturning of these blocks during the earthquake, some of the main features are the following. First of all, due to the nonlinearity, it is possible that the block topples, overturns under a certain level of ground motion and does not overturn under the same ground motion scaled up to a larger peak ground acceleration. Let me show this analytically. Let's assume that we have this block and we have a base excitation of the El Centro 94th earthquake, which we scale up to several values of the maximum acceleration. So if we scale this earthquake motion to 0.60 g, then this is the response that we get solving the equation of motion. And you see that this is angle of rotation versus time. If you increase the the same excitation, the same earthquake, but you increase it to 0.70 G, then you get overturning at this time, about 4 seconds. If you increase more at 0.8 G, then you get a gate overturning, but at a later time and on the opposite side. And if you increase it more to 0.90 G, then the response is stable again. So you see that the phenomenon is highly nonlinear. Another feature is that the rocking response is extremely sensitive to the parameters. And this is very important because when you do analysis with rocking blocks, you should be very careful in the values that you use for the parameters that concern especially the rocking interface. For example, the coefficient of restitution that I was talking before. Okay, let's see it again in the same example. We have the same block here under the epicenter earthquake, scaled to 0.5 G. And this is the response that you get at 0.5 G if you use the Hausner formula for the coefficient of restitution. However, it has been proven from experiments that in reality, the dissipation of energy does not follow exactly the Hausner formula. And so the dissipation might be different, might be larger or smaller depending on the materials. So if you assume that instead of 0.85, which Hausner calculated mathematically, you have 0.87, then you get a very similar response with this smaller, larger response at about 5 seconds. But see what happens if you increase this to 0.88, just slightly. Then the response you get is this one. So you see that very slight differences in the parameters can change the response very much, and this is the so-called sensitivity of the response. Another feature is that whether overturning of rigid blocks will happen under a certain earthquake depends not only on the aspect ratio, height over the height of the base, but also on the absolute size of the block. In other words, this phenomenon is size dependent, and smaller blocks are less stable than larger ones. Here is an example of this. This is the two blocks of similar size. The aspect ratio is 3 to 1 in both cases. However, the right one is 3 times larger than the left one, and the excitation was the same in both cases. However, you see that the small block overturns, the larger block is stable. Also, the rocking response and the risk of overturning is depends also on the predominant period of the base excitation. The larger is the predominant period, the larger is the risk of overturning. And for this reason, the ground motion that will be selected for analysis in case of rocking blocks should be compatible with the real ground motion so that can occur. You do not have to consider only the peak ground acceleration, but the frequency content of the ground motion is very important. And to show you, these are results of blocks of overturning curves. They show the safe area in this part and the overturn area in this part. These are results that correspond to harmonic excitations. And on the horizontal axis, it's the frequency of the excitation divided by a characteristic frequency that depends on the size of the block. This R here is the distance of the center of gravity with respect to the pole of rotation. And on the vertical axis is the maximum acceleration of the harmonic excitation divided by the acceleration which is required for rocking to start, to initiate rocking. So here you see that for small blocks and long period excitations, you are in this area here, which means that if you have an acceleration slightly larger than the one that is necessary to start overturning, then to start rocking, then you also get overturning. However, if you are here in this area, which corresponds to large blocks or short period excitation, high frequency excitations, then you see here that in order to overturn the block, you need a maximum acceleration, which can be 10 or 12 times larger than the one that is needed to initiate rocking. Some important results. Since the base motion characteristics significantly affect the rocking response, the earthquake motions that will be used in the analysis for the determination of the ground intensity required to overturn certain objects should be carefully selected in order to comply with the relevant seismotectonic environment. You should be very careful in which record you select. Another one is that the analysis for the determination of the ground intensity which is required to overturn rigid bodies cannot lead to an estimation of the actual acceleration, maximum acceleration that occurred, but to a lower threshold. Because what you can find with this analysis is the minimum acceleration that is required to overturn the block. However, the real acceleration could be larger than that. It could be it cannot be smaller, but it could be larger than that. So you do not get the actual acceleration, but the minimum threshold of this acceleration, of the ground acceleration. In this sense, it is evident that the more objects you have and to use in your analysis, then more closer you will be to the actual acceleration. And in any case, you must have in mind that due to the highly nonlinear nature of the rocking response and the sensitivity that I was talking before about, the procedure is not straightforward nor leads to unique and 100% safe results. There is always an ambiguity in the results that you have to know. Okay. Let's apply this. Unfortunately, we did not do this analysis for Samos earthquake, but we did for the Thessaly earthquake, which occurred in 2021 in Thessaly in Greece. You see here a map of the epicenters. The main shock was this one. The epicenter was here, and it was a magnitude 6.3. And the next day there was a serious aftershock of magnitude 6 at this point here. We did not have any records in these areas. The closest record we have is in Larissa, which is about 22 kilometers away from the epicenter of the main shock. So we did analysis for some objects that had overturned in cemeteries in Tyrnavos, Mesochori, Vlachogeni, and Zarkos. The objects that we consider in Tyrnavos was this small column you see here that has fallen down. This was the initial base, and it has fallen down. In Mesochori, we used this plate. There was a plate with two shoes here that has also fallen down. On the right bottom side, you see the mathematical model that we used for the analysis. In Vlachogeni, we used this column, which was a thin column that fell down during the earthquake. And in Zarkos, we had two small columns again, one here and one here, from which one of them fell down during the earthquake. So we used these objects, and for ground motions, we did not have enough information, especially at the time of the analysis. So we decided to use the records that were recorded in Larissa and in another city in Karditsa, which is a little bit further away, in order to have the same, assuming that they contain the same, the principal frequency content of the earthquakes, the ground motion at the epicentral region as well. So we used these three records, two at Larissa and one in Karditsa. Of course, these were of smaller peak ground acceleration. They were in the order of 10% of G, and in Karditsa even smaller, because they were in a quite large distance from the epicenter. However, we scaled them up gradually up to the point where overturning of the objects occurred. And the results we got are given here for the 4 objects and the 4 cities, and for each of the 3 records, what was the scaled acceleration that we had to use in order to overturn them. You see here that the maximum acceleration that we got, the minimum required to overturn the blocks is at Zarkos. This does not necessarily mean that in Zarkos the acceleration was larger than in other cities, but the object at Zarkos was falling down, was overturning more, there was needed more acceleration to overturn than the objects in the other cities. That's why I said before that what you get is the minimum value, not the actual value of the peak ground acceleration. So, if you use the result at Zarkos, which are the most, the ones with the maximum base acceleration, these are the 3 records scaled up to the minimum value required to overturn the object at Zarkos. And these are the spectra of these records compared to the Eurocode spectrum that corresponds to this area, and you see that the actual acceleration, the actual ground motion was much more intense than what Eurocode predicts. One important thing that gives us some confidence in our results is that, as I said before, in Zarkos, there were 2 columns, small columns, and only one of them have fallen down. And the analysis we did also shows this, that from these are the results, the final results from the 3 records. And you see that in all cases, only one of the column falls down and not both of them. Okay. In order to compare these results with other methods of estimating the ground acceleration, for example, we used the ground motion prediction models. Ground motion prediction models have been developed by several researchers in order to predict the ground motion parameters based on the characteristics of the fault and the distance. So there were some analysis based on this, and these analyses were using 2 such models. One of them is the Burentar 2021, which is proposed for Greece specifically, and depends on the John-Bourg distance. And the other one was the Chewing-Yang model, which depends on the rupture distance. The results for the 4 cities that we considered, for the Bohr model are this, and for the Chewing-Yang's model are this one here. And these are the results that we got as the minimum acceleration depending on the overturned blocks. So you see that in the 3 cities, Tyrnavos, Mesochor, Vlachogianni, where we got relatively low values because the blocks that we considered were overturning easily. this model gives larger acceleration, which is normal, which is expected. But in Zarkos, you see that this model gives quite small values of acceleration, while we calculated that the minimum required to overturn the block should be in the order of 35% of G, while this model gives about 20% of G. So this shows that maybe this GMPM models do not work very well in the case of Zarkos. We also did a comparison with stochastic fault models. These were some analysis performed by some colleagues, seismologist colleagues, and in this case they found that at Zarkos the acceleration could be as much as 45% of G, which is closer to the minimum value of 35% of G that we calculated. So in conclusion, objects that overturn during earthquakes may provide useful information on the intensity and the characteristics of the ground motion at places where no recordings are available. To this end, analysis of the rocking response of each object under various scenarios of base excitation are needed in order to define the minimum ground motion intensity necessary to overturn each block. Since the base motion characteristics significantly affect the rocking response of rigid blocks, the earthquake motions that will be used in such analysis should be carefully selected in order to comply with the relevant seismotectonic environment. Such analysis cannot lead to the estimation of the actual value of the peak ground acceleration, but to the lower threshold which is required to overturn the objects, and the real ground acceleration can be larger than the one that you calculate. Therefore, the more objects are used, the better the real PGA can be reached. And finally, it should be emphasized that due to the high nonlinear nature of the rocking response and the sensitivity of the phenomenon, even to trivial changes of the parameters, and there are a lot of parameters which are not known. For example, the coefficient of restitution during impacts, it's not known, so you have to guess it. This procedure is not straightforward and does not lead always to unique 100% safe results. Thank you very much.
Okay, Professor Psikaris, thank you for this very, very interesting topic you have covered very nicely. So it's very interesting to understand behavior of overturning blocks with your analysis approach, I believe. So, you know, in Istanbul also we have the obelisk of Theodosius at Sultanahmet, and we are also wondering what was the maximum accelerations in the past in that area as well. Do we have any questions?
Yes, I can.
Okay, Professor Ripsa.
Professor Psiaris, it's very nice to see you again after a couple of years. Thank you for your
nice to meet you again too.
I wanted to know, do you have any experimental test results, especially performed on the shake table, related with this topic? This is the first question or comments. And the second one is is it possible to use this formulation for the rigid furnitures in our at homes during the understand the response of our furnitures in real earthquakes? What do you think about it?
Yes. Okay. For the experimental experiments, we have done several experiments in the lab in the Sankey table, which concern mainly more complicated structures, which are ancient monuments. Ancient monuments as columns. If you know, there are constructed from several blocks which are put one on top of the other without any other connecting material, only friction. So there we have rocking. So it's a much more complicated problem than the single rigid block. We had performed several such experiments with columns, and we compare them with the numerical results we get. We saw that we can, although these sensitivities and these nonlinearities, if you use reasonable values of parameters, you can predict the response quite reasonably. Although there is an ambiguity, but there is these results show that you can predict them quite well. So yes, we have checked our models and we have checked our analysis with not only simple cases such as single blocks, but also in more complicated cases of many blocks one on top of the other. Now, concerning the furniture and all these things, yes, of course, any rigid block, any block, actually the block does not have to be rigid, but typically the flexibility is not so important because all the motion is taking place at the interface. So that's what we are talking about, rigid blocks. Of course, you can apply this in any object, even in furniture or whatever you want. Actually, lately we had done a lot of research through a PhD for analytical expressions, which so we attacked this problem analytically, assuming that at the interface there can also be some, due to the impacts, you have a flexible base, and you can also have plastic deformations there. So this problem has been solved analytically. Now we think that we have the full equations of motion and the full solution, and we have sent it to OpenSys, and I guess that it has been incorporated into OpenSys. So you can use OpenSys for this case, and you can solve any problem you want with OpenSys, taking under consideration this rocking block.
Okay, thank you so much.
You're welcome.
Okay, thank you again, Professor Psikaris.
You're welcome.
For your joining us. We need to move to the next speaker. The next speaker is Professor Hong-Ying Dong. She will be presenting seismic behavior of full-scale steel reinforced recycled concrete columns under high axial compression ratio, which is very rarely investigated in this area. So the Professor Dong is a professor of College of Architecture and Civil Engineering at Beijing University of Technology, China. So Professor Dong worked as a visiting scholar at University of Minnesota some time ago. She was appointed as the Secretary General of the Comprehensive Disaster Prevention Committee of Green Buildings in Villages and Towns of the Architectural Society of China. She has been also a licensed professional engineer. Her research expertise is centered on the fields of reinforced concrete structures, steel concrete composite structures, mason structures, seismic resistant design, recycled concrete structures, as well as seismic study on masonry buildings in villages and towns. Professor Dong has published numerous technical papers during her academic career and holds 16 invention patents in China. Yes, Professor Dong, thank you for joining us and accepting our invitation. Can you hear us, Professor Dong? Hello. Huh?
Hello, can you hear me?
Okay. Yeah. Yes. Now I can hear you. Welcome.
Okay. Good morning, everyone. It's my pleasure to be here and to talk about my research. And thanks very much for the invitation from Professor Celik. My topic is seismic behavior of full-scale steel reinforced recycled concrete columns on the high axial compression ratio. I will talk 3 different columns. The first one is steel reinforced recycled concrete column. And second one is reinforced recycled concrete column. And third one is recycled aggregate concrete filled steel tube columns. As you know, with the construction with the increasing of construction demolition waste and the demand for construction materials, especially concrete aggregates, we can use recycled concrete. And especially after Wenchuan earthquake in 2008, many Chinese researchers have done a lot of research on these fields. The first picture is the on-site disposal of construction demolition waste. And also we can produce a recycled coarse aggregate at a plant. And also some other researchers in the world, they have done the studies like Limba-Chia, and from his paper, up to 30% of recycled coarse aggregate had no effect on the concrete strength in high strength recycled concrete. Thereafter, the concrete strength gradually decreased as the RCA content increased. From paper of Andrew intersection, when RCA was produced from natural concrete with a compressive strength of 60 MPa or more, considering mechanical properties, a 100% RCA replacement ratio could be used, considering durability property, up to 50% could be used. So we consider the high strength recycled concrete and to use as a structure member in projects, especially in columns. This is the first column we consider. This is a steel reinforced concrete column. From this picture, you can see this column has H-typed steel, the red one, and then the yellow one is stirrup. And from this picture, you can see the green one. Green one is the concrete. For the normal SRC column, this is the normal concrete. We consider to use recycled concrete instead of the normal concrete. Because in the world, a lot of buildings use the SRC, steel reinforced concrete column in the buildings. At first, we designed 6 columns, including 3 SRRC columns and 3 RRC columns. RRC is reinforced recycled column. So from this, the picture here, the first one is SRRC column. You can see from this picture, the green one is H-shaped steel. It's H390 by 300 by 10 by 16 for this steel. And the second one, RRC column, is the normal column, just we use recycled concrete here. And the parameters here is RCA RCA means recycled coarse aggregate. Replacement ratio as 0, 50%, or 100%. From here, you can see. And the first 3 specimens use H-shaped steel. We did the experiments at our university. We have 40,000 kilonewton compression at the laboratory. We use this displacement control here, and before 1/150, we use 900, 1/900. This is a test setup. This is the filial photos. From here, you can see at the end of loading compared to this 3-1, SRRC S-bit, larger displacement, tighter cracks, more serious concrete cover spalling, more obvious shear phenomena. This is the load displacement hysteretic response. This is the skeleton curve of the 6 columns. The yield load, peak load, and ductility coefficient of SRRC specimens are obviously higher than those of RRC specimens. This is a stiffness degradation. For the SRRC specimens has 3 stages. For the RRC specimen just has 2 stages. From here, you can see. For SRRC specimens, after a drift ratio of 3%, the stiffness degradation was slower, indicating that the addition of inner steel can effectively delay the rate of stiffness degradation and slow down the failure process. This is the energy dissipation capacity. The first one, graph is cumulative energy consumption, and second one with the blue one is at the drift ratio of 2.5%, the cumulative energy consumption, and the black one is 1.5% drift ratio. The steel reinforced can effectively improve the energy dissipation capacity. RCA replacement ratio had a negative influence on the energy dissipation capacity. I will use this graph to analyze the force mechanism. It has 3 areas. The first one is the blue one, very close to the steel. It is called highly confined concrete. And second one is very close to it. The red one, partially confined concrete. And the outer one is unconfined concrete. And we put the left one to the right one to make it clear and simplicity. And you can see from here, this graph, this is the stress-strain relationship for the 3 different areas. The normal concrete, according to Chinese code, and the recycled concrete, we use the one proposed by Mr. Xiao, and the confined concrete we used proposed by Mender. This is section stress balance and the moment balance equation at crack load, at yield load, and at peak load. At the end, you can see here, the average ratio is about 1. And we publish a paper here. And the second kind of columns is RRC. It means reinforced recycled concrete columns. We design 5 RRC columns. The shear span ratio here is 2.92. It's longer than the one, the last one. So you can see here, this is the reinforcement details. The 5 specimens, we use RCA displacement ratio 0, 50%, 100%, and the axial compression ratio is 0.4 and 0.35. We just want to know the axial compression ratio, the influence to the seismic performance of the column. We did the experiment at the same laboratory, and we use displacement control. This is failure characteristics of the 5 columns. Compared to reinforced concrete specimens, cracks were more sparsely distributed and occurred earlier on RCA specimens. And compared to specimens with lower ACR, more oblique and vertical cracks appeared, and the cracks appeared later on specimens with higher ACR. This is a load displacement hysteretic response. From this skeleton curve, as the RCA displacement ratio increased, both the bearing capacity and ductility decreased. The RCA replacement ratio had a greater influence on the bearing capacity and ductility when ACR is lower. And this is a stiffness degradation for the specimens with higher ACR, like 0.54, it has 2 stages. And for the specimen with lower ACR, it has 3 stages. And this is the energy dissipation capacity. The RCA replacement ratio had a negative influence on the energy dissipation capacity of RRC columns. High and low ACR specimens showed similar energy dissipation at the same drift ratio. A 3-fold skeleton model was constructed. The peak load is calculated according to Chinese code. And this is the loading and unloading rules. The comparison between the established and experimental hysteretic loop, they agreed very well. The third column, the third kind of column is concrete filled steel tube column, but we use a recycled aggregates instead of normal concrete. Cornell first suggested the use of a steel tube to constrain the recycled aggregate concrete to expand its application. The strong constraint effect of the external steel tube on the internal RCA can improve its mechanical properties. Yang and Ham further studied the concept of restraint and proposed the concept of RAC filled steel tube columns. Here we use RACFST. Because the steel has very high strength, so it needs the concrete to be higher strength. So this time we use the concrete recycled concrete over 60 MPa. This specimen has two different heights. The one 675, the shear span ratio is 2.06, and the second one is 3.06. We designed 7 square columns. This is specimens. The parameters is the RCA replacement ratio and shear span ratio and axial compression ratio. We use displacement control at our laboratory. This is the failure characteristics. A specimen with a small shear span ratio, a local buckling occurred earlier. A specimen with a low axial compression ratio, local buckling was significantly slight, and the failure process was slow. This is a low displacement heuristic response. This is the bearing capacity ductility and stiffness degradation. And also we analyze the energy dissipation capacity. And also we construct a 3 broken line model and hysteretic rules for the restoring force model. And this is a comparison with the calculated one and the test one. And also we did fiber element model in OpenSeas. This is a verification. And then we analyze the RCA replacement ratio, the influence to the seismic performance of a column. And also we analyze diameter to thickness ratio and the influence of axial compression ratio, and also the influence of shear span ratio, the influence of steel yield strength. This part of work have published on structures this year. So in conclusion, for SRRC column under a high axial compression ratio, RCA replacement ratio has no significant effect on the bearing capacity and ductility of SRRC columns. For RRC column, for high ACR, the RCA replacement ratio had less effect on the bearing capacity, ductility, energy consumption, and other column properties compared with the low ACR specimens. For RACFST columns, the bearing capacity of high-strength RACFST columns decreased limitedly with increasing RCA replacement ratio. The ductility of specimens with RAC containing 50% and 100% RCA higher than that of specimens with NCR. This research project is sponsored by National Natural Science Foundation of China, and my research team members are Wanling Cao, Yan Nali. They are my master students. Thanks for their work. Thanks for your attention.
Okay, Professor Dong, thank you for this perfect timing, just in 20 minutes. And I would like to ask if anyone from the Zoom participants or YouTube would like to ask anything to Professor Dong. Any questions? Still waiting. Well, I had been to Beijing University of Technology several times, and I have witnessed actually the huge capacity of their laboratory, structural laboratory, and they are testing full-scale concrete field, steel concrete field composite columns. It's a very versatile lab, I would say. Professor Dong, I have a very quick question. Is there any building, with recycled aggregate concrete filled columns in China? Is there any application of this, or this is just in the phase of research?
For my part, just the research, but there are some buildings with, they use very large size recycled concrete. They put them in the concrete filled steel tube. We have that kind of building. Okay,
thank you so much. Then, if there is no other questions, so I guess everyone is quite tired right now because the program is very, very thorough program, and every speaker is following another one. So we need to give a break, but this time break will be a little bit short because we are a little bit behind the schedule. So let's give 5 minutes break. Then we will continue with Professor Moretti, Marina Moretti. Then we will be going up to the lunch session, okay? Okay, thank you again, Professor Dong, being with us and for your contribution. And now it's break time.
Thank you very much.
You're most welcome. Okay, you could actually, yeah.
I don't know how to close my.
Okay.
Can you do it?
You could stop sharing.
Stop.
Stop sharing. There's a share screen.
I found that.
Okay.
I found that.
Okay, perfect. Okay, thank you so much again, Professor Dong.
Thank you.
For being with us. Okay. Yes. Yes. Professor Moretti, wait a minute. Okay, now we continue. I hope you hear me, right? Okay. We have right now Professor Marina Moretti of National Technical University of Athens again. She's an associate professor in School of Architecture. Her research areas are reinforced concrete, seismic design, earthquake engineering, building codes, masonry structures, seismic retrofits, structural application of advanced composites, post-earthquake assessment of building damage, modeling of reinforced concrete members. Professor Moretti has published numerous technical papers in the field of structural and earthquake engineering, and she will be presenting contribution of infills to the seismic performance of substandard reinforced concrete frames. Yes, Professor Moretti. Your voice, would you please turn your voice on? Okay, you're muted, Marina. Please unmute yourself. Okay. All
Is
right.
it now?
Yeah, that's perfect. Thank you.
Okay, thank you.
Thank you for joining us. Yeah.
Thank you. Thank you for kindly inviting me in this important symposium in honor of and the memory of Ibrahim Demir. So in my presentation, I would like to summarize several issues on the seismic contribution of infills and how this contribution can be modeled, and whether code provisions provide respective accurate provisions. So the presentation will focus mainly in infills made of masonry and of reinforced concrete, especially in case especially for strengthening existing buildings. For both types of infills, in order to accurately assess the behavior, the seismic response against lateral loads, we need to know to determine the capacity and the stiffness. So in Greece, modern codes were introduced in the beginning of 1990. So therefore, the buildings before this period have low engineered earthquake resistance and are considered as substandard. A typical inadequacy of these buildings is the absence of reinforced concrete structural shear walls. They are basically reinforced concrete frame force resisting systems. Therefore, they have low lateral stiffness, which results in high story drift. High story drift has a consequence leads to collapse of the ground story, especially for open ground stories, and may also result in considerable damage of short columns, captive columns, which also may result in collapse, and also to extensive damage of masonry infills. Another inadequacy, very essential for the behavior of those buildings, is that they have very few stirrups and are, as a result, very low shear resistance, which may result in brittle failure of columns. And this is one of the major causes of collapse of buildings in Greece, older buildings during earthquakes. Just to show the strong inadequacy of shear reinforcement, here is a typical reinforcement of columns built before 1985. More specifically, only one stirrup at the outer perimeter of the section and very sparsely spaced stirrups. Well, this is the modern practice for shear reinforcement. So this is inherently that older buildings have very low shear force. Among other major codes, Eurocode 8, Part 1, recognizes the beneficial effect of on seismic performance of infills. They increase in-plane shear stiffness and in-plane shear strength. So this is what the older structures need. However, the codes for the design of new structures do not encourage the designer to the reduced earthquake resistance of a new structure by taking into account the beneficial effects on masonry infills. On the other hand, the codes for the assessment and retrofit design of existing buildings do encourage the designer to take into account the participation of infills, usually because if this participation is not taken into account, the older buildings cannot possibly meet the requirements of the modern codes. But they do not include provisions on how to assess the contribution of masonry infills. Here is a very schematic and informative figure from Sugano in Japan, 1996, in which the effectiveness of different infills is shown comparatively. Here's a bare frame without infill, very low strength and low stiffness. On the top is monolithic connection of reinforced concrete wall, very high stiffness and very high strength, and infill not monolithic, RC infill not monolithically connected to the frame, and a masonry infill. The experimental and analytical research regarding masonry infill frames has started in early 1960s. The available design models for infill frame originate from masonry infill frames, and in fact, the same models are generally applied also to describe the behavior of RC infill frames against lateral loads. But the fact is that masonry and RC infill frames behave differently. FEMA 306 includes very detailed provisions regarding the design of infilled frames. FEMA provides separate equations for each type of identified possible failure of the infills. And although these equations were derived from masonry infills, they are applicable. The recommendation is that they could be applied also for reinforced concrete infills. The idea is that different types of possible failures should be identified, and for each type of failure, failure load or lateral resistance is to be calculated according to the FEMA equations. And the minimum calculated, the type of failure that results in the minimum lateral load, this is the critical one, and this is the lateral resistance of the infill frame. However, it should be noted that if the equations offered by FEMA are compared to experimental results, it is found that the type of failure estimated by FEMA does not match the actual one. This is the types of typical types of failure for reinforced concrete infill frames. And it is noted that in contrast to masonry infills, RC infills fail only and are damaged, not fail practically, because they never fail. They are damaged, they are cracked only when, in case a very strong connection exists between the infill and the frame, and also when we have a strong frame and a relatively weaker infill. In case of substandard RC frames, on the other hand, a typical mode of failure is that the frame members fail because they have low shear resistance, either the joint or the column or the beam that converge to the joint. So first conclusion is that masonry infills and reinforced concrete infills do not behave in the same way. Now, for the most often applied design model for the to depict the behavior of infill frames is a model of a strut, concrete strut. Different types of struts have been proposed by different researchers and in different codes. There's a broad variety of struts. And the point is that a different strut results in different overall behavior of the infill and also in different forces transferred from the infill to the frame members. And it should be noted that the choice of the strut model, also the type of the strut, and also the strut width of the strut width affect considerably the results of the analysis. Now here is a inclined strut that is not along the main diagonal. It was proposed by Zarnic and Tomasevic, and this strut models the fact that several times the failure of the masonry infill results in failure of the adjacent RC column, as the case is here from a picture in from an earthquake in Greece in 1986. Now, several design models and the strats were evaluated from according to different codes, and they were compared. The results were applied on a broad experimental database, and in order to identify which strat better compares, better predicts the actual behavior of the tests. So it was found that for RC walls, which are a very effective method for strengthening substandard buildings, RC walls are better modeled by using a single strat with pins at the ends. Now, the basic parameter in this case is the width of the strat. The higher the strat width, the more increased the activation of the infill and vice versa. So the estimation, the calculation of this strat width to be introduced in the analytical model is very important for the accuracy of the design model. It has been observed from tests that a higher activation of RC infill is obtained when there is a stronger connection between the infill and the frame, which means more dense, more dowels with a longer abandonment length. It is noted that this fact, the type of connection between RC infill and surrounding frame, is not considered by the codes. Further on, more activation of the infill is obtained when where the infill is encased by a very strong frame, columns and beams. The relative stiffness between the effect of the relative stiffness between infill and frame members is in fact considered in calculating the width, the strat width, in ASC code and Canadian code. It is noted that this idea was first proposed by Stafford and Smith in 1966. Another issue is that the activation of the strat width is not the same during the beginning of the loading and during the ultimate state, because for low lateral force, the infill and the frame behave as monolithical because no damage has occurred, while for higher lateral forces, in case of RC frame, a detachment between infill and frame is observed. In masonry infills, cracking of the infill is observed. So for higher lateral loads, the effectiveness, the contribution of the infill becomes less. And this was Park and Polley, in order to address this, they suggested that for maximum load, a 50% stiffness of the strat should be calculated. Another issue is that that is important in the actual behavior of RC infills is that as the loading proceeds, sliding is observed between the RC infill and the frame members. And due to this sliding, we have a pinching effect, a very low capacity of energy dissipation, and loss of the effectiveness of the infill. The critical value of the sliding displacement is not easy to determine, however. So from this comparative research we made in order to identify a reliable model to depict the experimental behavior, we considered that we found that the models that take into account when they calculate the strat width, the relative stiffness of the frame are more effective. The Canadian code results in a higher strat width compared to FEMA and ASCE. So it was found that for early loading, approximately lower than 50% of ultimate lateral strength, the higher strut width should be used because the infill participates more. On the contrary, when for higher load, a smaller strut width should be applied. And this is very important for the stiffness of the infill frame, which is important in analyzing, in assessing the seismic capacity of a structure. But another issue is which is the value of maximum load. Here are two tests we conducted in 1/3 scale specimens, infilled frames. The first frame, this frame was not connected to the surrounding frame. This was strongly connected with dowels on all four sides. We can see that when we have a connection, actually, the frame does participate more, so obviously dissipates more energy. According to FEMA 306 guidelines, both infill frames should fail, or were expected to fail in compression and diagonal tension. However, none of those types of failure was observed. On the contrary, the specimens failed in shear in this part of the section of the upper part of the column. Although in these two specimens, the frames the columns were strengthened by means of a jacket. So the conclusions are that the infill frames are very essential for the seismic resistance of substandard buildings, and especially when no damping devices are used. This is the case in Greece. We don't use damping devices or energy dissipation systems. So in order to assess the capacity of existing buildings for retrofit design schemes, we need to accurately consider the available capacity, lateral capacity of buildings. So we need to consider the contribution of the infills. And codes for retrofit design do encourage towards this direction, but however, they do not provide, it seems that they do not provide provisions because no reliable provisions are readily available. So what I would like to indicate that is that the results of a seismic capacity assessment of existing substandard buildings can be very strongly affected by the design model which is used to simulate the contribution of infilled frames. And this is the end of my presentation. Thank you for your kind attention.
Okay, thank you, Professor Moretti. And that has been a very interesting topic, which is a very common issue both in Greece and Turkey, whether or not to include the infill walls in design or not. Anyway, so very interesting topic internationally. So do we have any questions for this?
Yes, I can.
Okay, Professor Yüksel.
Dr. Moretti, thanks for your presentation. Actually, in the previous years, we have completed some tests in the laboratory, especially with the substandard frames infilled with bricks. And generally, the damages observed is very suitable with your slide 17 at C, shear failure at column tops and the beam column connection. Because in practice, generally, in the uncontrolled structural systems, generally, there is no reinforcement arrangement, lateral reinforcement arrangement at the end of the columns and also even in the beam column joint. Because of this reason, the common problem related with the infill frames generally arose from the shear failure at column top and joints. What do you think about this phenomena, and what kind of retrofitting techniques is or can be applied for this type of systems in your country?
Thank you for your question. It's interesting to see that the same problems, you have the same problems as we have. We don't, the code we have for retrofit design does not offer any provision. I think that there should be a local strengthening, perhaps by using fiber reinforced polymer jackets in order to increase it. But the main issue is how to determine the strength and the behavior of these RC infield frames in order to put them into the model. So the answer is we don't have a practice. We don't. I don't know what you do in your country if you have some practice to strengthen these types of substandard joints.
Thank you, Dr. Moretti. Actually, from the YouTube, we have two questions. One is related directly with your topic, and the other one is general. Probably the answer of the second question will be answered at the afternoon sessions. And again, the question is this. Thank you for your presentation. Have you considered the lack of transverse reinforcement in the joints of substandard building models? And this question is very similar to my question. And also, you made some explanation about the retrofitting, especially for the retrofitting of polymers, glass or carbon type polymers to retrofit of this type of systems. And also one new question from Dr. Özkaynak, and he asked us, thank you for your presentation, why Professor Marina specially states that infield walls are essential when no damping device is used, at least page of her presentation.
I'm sorry, I will start from the last one, no damping devices, because in I think that damping devices are very promising method for substandard buildings, because this, as I said, we cannot increase shear strength considerably, so damping devices would be the solution. However, I don't know, we don't produce damping devices, they are expensive. I don't know the reason why the practice yet, but I think this is the future, damping devices, but we don't practice that. About shear strength of joints, I didn't present it. We have suggested, and it's published in EACE journal, an idea that how this the frame joint how the capacity of a substandard frame joint may be calculated, but there is no provisions in the codes. Regarding FRP practice jackets, it can be applied, but we know that for FRP jackets are very effective in round cross sections. If you have a circular, square cross section or a rectangle cross section, they cannot be very effective in providing confinement. Thank you again.
Okay, thank you so much.
Okay, Professor Moretti, since the topic is very, interesting, so everyone needs to ask some questions. Thank you for your contributions again. Perfect timing. So I would like to move on to the next speaker, Professor Tatiana Isakovich. Professor Isakovich is a professor of Civil Engineering and Geodetic Engineering, the Faculty of Civil Engineering and Geodetic Engineering at the University of Ljubljana. Also, she takes some duties in Institute of Structural Engineering, Earthquake Engineering and Construction, named İKPER. Her research fields of interest are civil engineering structures, seismic engineering, computer-aided design of structures, design of bridges in seismic areas, reinforced concrete structures, precast concrete structures, Also, she has been involved in the introduction of new Eurocode 8 standards into design practice. And also she is the member of Slovenian Association for Earthquake Engineering and other some international institutions. And she will be presenting seismic response of reinforced concrete walls. Yes, Tatiana, welcome.
Thank you, Mr. Chairman. First, I would like to thank the organizer to invite me to this really great event. So I'm going to present some research that was performed at the University of Ljubljana, which is dealing with reinforced concrete walls. These walls are typical for Slovene practice. The characteristics are that they are relatively thin. The thickness is between 20 and 30 centimeters. And it is typical in our buildings that there are relatively large number of walls. The total area of the walls is about 1.5% of the total area of the floor. These are the typical numbers. These walls are reinforced typically by 2 layers of welded meshes from each side of the wall. And on the boundary areas, there is additional vertical reinforcement, vertical bars, which are sometimes surrounded by confinement reinforcement, sometimes not. In newer structures, we are following the requirements of the Eurocode, and we have closed stirrups. In older practice, these stirrups were not closed. So I'm going to present some experimental studies that were performed at our institute, as well as analytical studies that were performed, first of all, with a goal to improve the design practice, including the Eurocodes. And we already submitted several comments to the currently available, currently used Eurocode 8. Many of them were now included into the new version of the Eurocode 8, which will be included in the second generation of the Eurocode, which will be available in a few years. So probably the most important contribution of our research is the estimation of the shear demand in reinforced concrete walls in the nonlinear range, and in particularly this coefficient which counts for the effect of the higher modes. So as I mentioned, first I will show some experimental studies that we designed, and these experiments were performed on the shake tables, one at Elnek in Portugal, the other one in Isis in Northern Macedonia. This first experiment is a shake table experiment of non-planar 2 wall piers connected by the slab and the coupling beams. The dimensions were typical for the Slovene practice, but the purpose of this study was to evaluate the influence of different confining reinforcement in the boundary regions of the wall. What was interesting also that the tests were biaxial. So this specimen was designed according to different recommendations in the literature, and it was intended to get the damage in beams and slabs, but the response was completely different. Actually, we were surprised. What was happened here, the strength and the stiffness of this floor system of beams and slab was much, much higher than it was estimated before the experiment. And these two wall piers were very strongly coupled, and the demand was completely different than it was estimated before the experiment. And that is why a brittle failure of the walls occurred here in this experiment. So following the conclusions of the previous experiment, we performed another one also on the shaking table. This was performed recently within the SERA-ATA project at ISIS. And here we tested 4 relatively slender walls, which were coupled only by slabs without coupling beams. Why we decided to exclude the coupling beams? Because there were several experimental evidences that the only slab can couple the wall piers very importantly. In the design practice, such a walls would be considered as cantilever walls because it is typically assumed that the coupling provided only by the slab is not very significant. And the basic response mechanism to the overturning moment induced by the seismic load is this flexural behavior of wall piers. But in this particular case, we obtained quite strong coupling, and the response mechanism was completely different. Actually, in the walls, since the slab was quite strong, this induces quite important axial forces in wall piers. And as I said, the response was completely different as the response of coupled walls. What was the main reason? The main reason was a very large effective width of the slab. Actually, the whole width of the slab was activated. Because of that, the stiffness and the strength was quite large. And this quite a large frame effect was visible also from the cracks which were, or the damage which was observed in the wall piers. In the beginning, the cracks were opened only on the outer edge of the wall piers, and then it was extended when the seismic excitation was increased. This damage was extended toward the inner edges. This crack pattern is completely different than the crack pattern which is typical for cantilever walls. It is cross-shaped, and you can see that this is importantly different. And also the evidence of quite large axial forces was the buckling of the longitudinal reinforcement, which was observed at the outer edges of wall piers. So this is we also performed some optical measurements, and this is the response of two piers at one moment. We can see here on the left side where quite a large axial forces were induced by the seismic load. There were quite large cracks, these orange areas, while this pier, which was subjected to compression, behaved completely different. So also the displacement envelopes are the evidence of strong coupling. We can see that here along the wall, the maximum displacement, the displacement envelope is completely different of that which is typical for cantilever wall. After the analysis, we came to the conclusion that here 50% coupling was occurred in this case. So as I mentioned, we also performed the analytical studies, but our analytical studies are not limited only to these experiments. We successfully participated in different blind predictions in the past. Probably the most successful was the blind prediction of the response of this well-known 7-story reinforced concrete wall tested in a full scale at the University of San Diego. And we made a very good prediction. Actually, it was the best from all the research groups that participated. And here is the displacement envelopes along the wall for relatively weak seismic excitation, and the last strongest one, we can see that it was quite good. And what we are using for these analytical studies, it is a special multiple vertical line element, which was originally developed by Japanese researcher, but then it was modified at our institute. What is the basic feature of this model? That the cross-section of the wall is divided to certain segments. Each segment is represented by one spring. These springs are rigidly connected to be able to follow the Bernoulli hypothesis. But what is the difference between this model and the original one? That the behavior of these springs is defined by hysteretic loops defined in terms of forces and displacement instead of stresses and strains. So that's the main difference. This element was first developed for 2D cases, and then it was extended to 3D version, included to our local OpenSys version. And recently, we extended it also to be able to analyze axial shear flexural interaction in the nonlinear range, where this shear is represented also by a certain number of springs. The properties of which are defined following the basic contributions of different mechanisms, aggregate interlock, Dowell effect, and the contribution of the shear reinforcement. This element was evaluated recently in the frame of the Virtual Wall Institute organized by University of California in Los Angeles. And this is an example of a wall where the shear was very important in the nonlinear range and caused a quite rapid degradation of the strength. This is the comparison between the experimental results, the red lines, and the black lines represent the analysis. This is the overall response, but we actually were able to catch quite good also the contributions of the flexural and the shear response. This is one of the rare elements which could do that. The results of these studies are presented in the special issue of the Bulletin of Earthquake Engineering, which was recently published, in fact, in 2019. Well, we continue to evaluate, to use this element. This is the current project that we are working on. We are included to the analysis of 10-story building, which was in a full-scale tested at the E-Defense Center in Japan. And here in one direction, the structure was dual, consisting of reinforced concrete walls, columns connected by slabs and beams. And these are the results of some results of analytical studies, the comparison of hysteretic response at the different floor levels registered during the experiment. The red lines and the blue lines represent the analysis which was performed with a model which included the MVLM element. So instead of the conclusions, I will just list the research topic that we are working currently on them, and which should be still solved. We are working on the design procedures especially for the coupling walls. And we, based on the experiment that was performed on the shake tables, we now perform the analysis of floor-to-wall interaction. And of course, this demand also the improvements of the analytical models. Thank you very much. That is all that I prepared.
Okay, Professor Isakovic, thank you for this excellent presentation. Also, the timing is very good. Do we have any questions from the Zoom participants or YouTube participants? Any questions? We just need to wait for seconds because we have sometimes receive some questions from the audience. So maybe I should add a few things. These systems, I guess, are widely used in Slovenia, right?
Yes.
So did you have any significant damage in previous earthquakes in such systems? And also,
well, in Slovenia, luckily, we didn't have a strong earthquake for a long time. Okay. But I can say something about the similar systems are used in Chile. They have similar structures, and in 1980, there was a strong earthquake, and such systems behaved very well. That is why the engineering community was very surprised with the heavy damage in the last earthquake in Chile.
Okay.
And it was typical that some shear failure occurred, and also the problem of confinement was observed. We believe that it is a problem in this interaction between slabs, beams, and walls. Particularly, I mentioned that our experiment, we tested very slender walls, and in Chile, it was typical that this damage was observed in high-rise buildings. So we believe that this is the problem, that we first of all don't know what is the effective width of the slabs, and we don't know how to estimate the strength of this system, including the beams, particularly with the diagonal reinforcement.
Okay.
That is why we decided to study such a system.
Okay, perfect. So we have a very quick question then. So Professor Sadık Can Girgin asks that, thank you for your presentation. Have you observed out-of-plane deformations during the tests? Also, can we model these effects in NVLM-LEM model?
Actually, we didn't observe any out-of-plane deformations. I mentioned that these walls are reinforced with 2 layers of mesh reinforcement. So we have at both sides one mesh. So this mesh is enough to prevent such a damage, at least at seismic excitations that are expected in Slovenia. In NVLM, yeah, it is possible to model these walls with the 3D model. So the model included then also the behavior out of plane.
All right. Thanks again, Professor
Isakovic. Thank you
for your very kind contributions to our online event. Thanks. So the next speaker is Kaushan Dai. Professor Dai is a professor and chair of Department of Civil Engineering of Sichuan University in Chengdu area. So Professor Dai obtained his PhD from University of North Carolina, Charlotte, in the United States. He worked as the Department of Civil and Environmental Engineering at the same school after graduation. He also has short-time working experiences in a risk management company at ImageCat in California. And Dr. Dai joined Tongji University, Shanghai, as an associate professor. He worked in the College of Civil Engineering at Tongji University, and he also contributed to the State Key Laboratory of Disaster Reduction in Civil Engineering at this university for 7 years before he joined Sichuan University. He's now professor and chair of the department. He also put some efforts to promote earthquake research at Institute for Disaster Management and Reconstruction. His research interests include critical infrastructure resilience, application of sensing techniques for civil structure inspection or monitoring, structural dynamics and vibration control, built environment, sustainability, and post-disaster evaluation. Yes, Professor Dai.
Thank you. Can you hear me?
Yes, Kaushan, go ahead.
Thank you. Thank you for the introduction, and thank you for the invitation from the organizer. And I'm going to talk a little bit about the power electric infrastructure. And I have been working in this field for like 20 years. And today I will share 2 infrastructure, one wind turbine tower and power plant building with the audience about the research. So first of all, some background, and then the 2 research and project we did for 2 different structures. And as everybody, you know, now we cannot live without electricity. And I think everybody uses cell phones every day, and we drive the cars and electric cars, and it's more and more popular. And now we use our computer, and also we need electricity. So it's one of the key elements for our modern society. So how to make sure the infrastructure to generate the electricity is safe enough for us to live without lose the electricity is the research of my team. So today I'm going to share first of all the renewable energy, wind energy supporting structure. We call it a wind turbine tower. The reason I start this research after I came back to China from US is I noticed China is push very hard for renewable energy, and today China is has the largest wind power installation in the world, no matter onshore and offshore. So this kind of structure as for our civil engineer is kind of simple. It's like a cantilever beam, but the loading is very complicated because they have the working machine on the top of this tower. And of course, currently most of the tower is like a steel tubular structure. But in China, we have very different loading environment compared to where this technology was developed in Europe, like northern part of Europe. Because in China, we have, for the onshore wind farm, we are prone to earthquakes as a topic of today. And also for the offshore wind farm, we have typhoon and strong wind. So that's, for this reason, this kind of structure, we observe, several failure cases, and during earthquake or due to typhoon, or even because of this blade rotation induced vibration. So that's one of the reason I worked with my student at the beginning in 2011, when I came back to China, and then I tried to monitor or get to know the vibration behavior of this tall, flexible structure. I installed some sensors on the tower. I tried to monitor and some data and get their diameter parameters. And that's a picture in the year of 2012 when I climbed up to the top of the tower to install the sensor. And I also use some laser Doppler vibrometer or radar to get its vibration from remotely. And after we have enough of data, I try to analyze and to get some, natural frequency and damping ratio of this special structure in China. And we found, what we use in our buildings or bridges to try to identify the dynamic parameter, the measure is not, perfectly valid and for this type of structure, because we have a rotation of a machine or blade on the top of the structure. So we have interface. And considering this, we developed what we call the modified and SSI method, and try to identify both the structural vibration and also the rotation frequency. And we did that, and we use our method. You can see from this slide, we can successfully identify both the structure mode and the rotation, period of the blade. And after get to know its behavior, I try to, did some numerical simulation to see how this tower fell during strong earthquake or strong wind. And of course, even during the earthquake, sometimes the machine itself is still rotation because earthquake, when earthquake comes, the wind turbine tower may still, work. So considering this, we use some software try to, put together, and we considering both the wind load And that means the rotation of the blade. And also we try to see how it felt during strong ground motion. And this is the whole process, how the tower collapsed during the strong motion, ground motion. This first, this one, and this one, and that one. This three picture is the failure process, or the collapse process of the tower during different ground motions. That means at a different earthquake, probably it fell at different part of the structure. Because we have a different frequency content of the ground motion. This very left bottom, right bottom picture is what the wind caused its fail. It's always at the bottom of the tower. So it's different for the earthquake and the wind-induced collapse. As I said, the reason is because this is the first mode of the structure of the wind turbine. This is second mode. And at a different, earthquake probably triggers the participation of the mode, the second mode will be different. That's why you can see it's a different part of the tower. It's the start of the fail. But for the wind, it's always the first mode dominant. That's why you can see it's always the bottom of the structure. So after know this, we try to develop some vibration control technology for the tower, and we'll want to depress its vibration either due to the working of the tower or the wind, or we try to see if can reduce the risk of seismic induced or earthquake induced failure. So we started with a tower at very close to the sea. So we need to consider the soil structure interaction. And we developed the TMD design method, and with the consideration of the soil structure interaction. And we also did some very small scale down chicken table test, try to validate our method. And then considering the tower itself is very tall, flexible, and also it's kind of lightweight compared to our high-rise building. So I try to use the inertia damper to reduce the mass where we put at the top of the tower. So additional mass, we can reduce at least, we can use half percent, 50% of the weight of the traditional TMD to realize the same vibration reduction factor by using our inertia damper TMD, tuned TMD, okay? And because all the tuned mass damper is very efficient for wind load, but it's sometimes doubtful for the earthquake. And then I considering, in the bridge and also in our buildings, we use this whisk damper. How can we input or install the whisk damper into the tower? That's the research I work with another, my master student. And because this is the flexural deformation compared to our buildings, most of the buildings are shear deformation dominant. So I try to design different configurations and to put our whisk damper work for control the vibration, either the earthquake or the wind, okay? Both work very well. And after that, currently we are also working on the semi-active or active vibration system for the tower itself. I think this will be one of the very beautiful work for the future, because the tower itself generates electricity. We can use that electricity and try to realize our semi-active or active, dampers. It's not like our bridge or buildings. We need to supply additional power to the damper because the wind turbine generates electricity itself. So we can use that electricity to our dampers. So this is work is still ongoing. I'll present the result probably in the future, near future. And this is one of the very interesting research we did for our group recently for wind turbine tower structure. And we also did something for the power plant buildings, because for the large power plant buildings, it's a very complicated structure. And usually the main building is a very important, structure to support the generator or different, electricity generation process or inside of this building. So it's also very critical for the entire power supply system. But as we can see from this picture of the real building, and it for our seismic design course, like I teach for the student here, I always say for the conceptual design, we want regular structure. That means stiffness regular, but mass regular. But this kind of structure is just to the another opposite way. The stiffness is irregular, like you can see here. They only have one breast, and it's one side. Another one is took off because they want to have some pipeline go inside, and that's a stiffness. The mass is also irregularity we have, because at the top of the tower usually they have very heavy machine, and then along the structure at the height, the stiffness and the mass, all irregularity were made. And at that time, when I worked with my student, we thought whether we can use the best either isolation or damping device, try to reduce the earthquake-induced force for this structure design. So we try to include both isolation technology and energy dissipation technology into this very complicated structure. For the isolation structure, we put it at the bottom of heavy machine. And in this way, we try to tune the heavy mass as a two-mass damper in this way. And also we put some BRB as some, presentation just now introduced, as some of the ordinary, breasts to replace them with the BRB, because we try to increase its stiffness. The reason is we want to use the damper there, and we use the magnetic yielding damper with BRB try to dissipate energy. We use the lead rubber bearing and try to put under the heavy machine to tune the heavy machine as the two mass damper. So through this way, we design our, this is a very heavy, we call it a coal scuttle. And we put the rubber bearing, bearing at the bottom of this support. And we do some optimization analysis, try to design the damper parameter to realize the tune mass for this all the heavy coal scuttle, and then we put some BRB in combination with the metallic yielding damper and try to dissipate the energy induced by the earthquake. And in combination of this, we try to see whether this works. We use some numerical simulation, first of all, try to simulate the structure nonlinearly, and we validate all the model, and then we try to see, well, it's worked well, and by using our, we call it resilient system with the isolation and also energy dissipation device. And then we, after this, we try to see we need to some physical tests to validate our idea. And we did some chicken table tests. We scaled down at, 1 1/10. And we have the model is still very big, and its length will be almost 10 meter, and the wide will be 5 meter, 5.4, almost 6 meter. Also the tall, the height of the model is over 6 meters. And then we have 3 different models. The third one is what they usually design the structure. And the second one is we put an energy dissipation device. And the first one, we put both the isolation and energy dissipation system. And then we did the test, and on the shaking table, and one of the interesting thing I try to mention here in the picture is for that very small scale down model and the bearing and the damper and also BRB, we'll need to redesign very detailedly and very carefully, because the stroke of all this damper is very small. It's like a millimeter scale, and then it should work or it should yield it. And so it's very difficult to do that. We repeat several times, and finally we realized the very scaled down dampers and the bearing. And then we did the test. You can see from here, this is the model. We try to put on the shaking table. And it's still very big, as I said. It's 6 meters and then 9 meters long and almost 6 meters wide. And this is the gray damper is the BRB. This is here is the yielding damper, and all this bearings put under the very heavy, bucket. And we put a lot of many sensors, try to collect vibration data of this model. And this is earthquake. We try to input either at one direction and 2 direction. And we did the PGA is almost to 1.4 G and try to damage the structure finally. And this is one of the table video, shaking table test video. Still, kind of rigid here, but the upper part of the structure is the vibration and also the 2 mass work. So this is compared to the Model 3, that's a traditional design. Our Model 1 and Model 2 all reduce the vibration. And this is inter-story drifts on the one of the ground motion on the table. And we can see the Model 1 is where we use both isolation and also energy dissipation device work better, work the best among the 3 models, okay? And we also try to see if the isolation work well for our, we call the high elevation isolation technology. And this is what we collected. The red one is what we got from the bunker, and this blue one is from the floor. We can see the isolation reduced, but the displacement enlarged. Okay, but we can see from the picture or the video, and it did work. And we tune the mass, try to use as the 2 mass damper for the entire structure to reduce the ground core vibration. So as I said, we increase the ground shaking to a very large scale, and we try to damage the isolation and the damper to see how the the behavior of this, bearings and the dampers. You can see it's a very large ground motion. It's almost they damage this, and I think it's almost 1.2 G. It's beyond 1.3 G is already beyond our design. So we did the test until like 1.4 G, and we see all the dampers and bearings are totally damaged by our test. And for the Model 3, the traditional design, the final failure of the structure is the breast buckling and the start of the buckling. That's what's the traditional design. If they don't have the bearings and energy dissipation device, that's what they look like during our test. So as I said, electricity is we need every day in our model study society. And I introduced our research in two of critical electricity generation device. One renewable energy, we call wind turbine tower supporting structure. And also we developed a seismic resilient system for the power plant building. Both of them work well during earthquake and also some working induced vibration. So that's my presentation. Thank you so much.
Okay, Professor Dai, thank you for this excellent presentation, from modeling to experimental testing, including shake table testing of a modeled scaled down specimen having some energy dissipation devices. Thank you so much. Do we have any questions?
I have a question.
Okay, Professor.
Dr. Dai, thank you for your excellent presentation. I wanted to learn what sort of dampers do you use at the bottom section of the wind turbine? Could you make some more explanation about it?
We work on the different type of dampers. And one of the type of damper we use most often and is we call it tune mass damper, and is like here. We use the tune mass damper on the top of the tower because most of the time the tower is a wind-induced vibration. This tune mass damper or tune type of damper work well. But the key for the wind turbine tune type of damper is we try to reduce the mass of this additional mass. And then we use what we call inertial mass damper. Try to reduce the additional mass. This is one of the group of the damper we are studying. Another group of damper we are trying to use, we call, is still we use for earthquake, for buildings. We try to, borrow these dampers into the vibration control of the wind turbine tower. But for here, the key is the tower itself is a flexible deformation. It's kind of different compared to our buildings, the shear deformation. I put different scheme and try to put this viscous damper inside of the tower. And during both earthquake and wind, you can see it's work well. So generally it's two types of damper. One is a tune type of damper, tune mass damper. Another is energy dissipation like a viscous damper. Yeah.
Okay, thank you very much.
Okay, Professor Dai, thank you again for your contribution to this online event and hope to see you soon.
Thank you.
In person.
Yeah.
Okay, thank you.
Thank you. Yeah.
Bye. Now, the next presentation will be done by Professor Mettupalayam Sivaselvan. He's the professor of Department of Civil Structural and Environmental Engineering at University of Buffalo. And also he's the director of Structural Engineering and Earthquake Simulation Laboratory. His research areas include computational mechanics, nonlinear dynamics, numerical methods, optimization techniques, control systems for dynamic hybrid testing. And he has some numerous honors and awards, actually, a few of them nominated by students in 2 consecutive years for an innovation in education award at University of Colorado at Boulder. And he was the Young Researcher Award of the Department of Civil Environment and Architectural Engineering of University of Colorado, again at Boulder. And he is the recipient of 2009 National Science Foundation Career Award. Yes, Professor Siva. Welcome again. It's a pleasure to have you here. Thank you for your contributions. Can you hear me? I can't hear you.
Thank you for the introduction, and thank you very much for the opportunity to present.
You're welcome.
So I'm going to talk today about some work we've done on seismic interaction of interconnected equipment in electrical substations. And I want to acknowledge that this work is with my PhD students, Yushan Fu and Vidhi Solanki, as well as our staff, Mark, Scott, and Bob at the Structural Engineering Earthquake Simulation Lab. So I'll go through some background and motivation, and then some basic concepts related to nonlinear dynamics of conductors, and some dynamic characteristics of interconnected systems, and then finally summarize some of our key findings. Substations are collections of electrical equipment that are used for voltage transformations in the electrical grid. They consist of different kinds of equipment. The main piece in a substation is a transformer, but there are lots of supporting equipment like circuit breakers and disconnect switches, surge arresters, and things like this. And these equipment are connected by conductors, and often these conductors are flexible conductors, as we can see here and here. There are a couple of IEEE standards that have to do with the seismic safety of substation equipment. And these standards provide certain recommendations for how to account for interaction of equipment through these flexible conductors. So these equipment are qualified as standalone equipment, but there are some provisions to account for how they interact when they're interconnected through flexible conductors. So the standards are concerned about relative displacements between the equipment becoming large, resulting in conductors becoming slack, very taut abruptly, and the forces generated by such tautness causing significant additional moments in the equipment. And there are therefore provisions to provide enough slack and to account for these additional moments that may occur due to the excess terminal forces because of the conductors becoming taut. But our experiments suggest that contrary to this kind of thinking, such effects aren't probably very significant. So if the essential mechanics of interaction can be understood well, then maybe some of these provisions can be made a little more practical and not as conservative. So that's the motivation for our work. We started out looking at the dynamics of individual conductors. So what the picture shown here is shows the cross-section of different kinds of conductors. And what we did was we fixed one end of the conductor on one end, and then on the other end, we applied a displacement of different amplitudes and different frequencies, exciting different forms of dynamics in the conductor to understand how it behaves. We also designed this very special kind of multi-axis load cell, which is essentially a truss of single-axis load cells. There are 6 of them. And so we can measure axial forces and bending moments, shear forces with high sensitivity. And we have one of these load cells at one end and another at the other. So that's our mode of excitation. One end is fixed, the other end is driven, and we are changing the amplitude and frequency. And this video shows different kinds of dynamics. So over here, we see that the conductor is essentially moving in the plane. This is at a different amplitude and frequency. We see that the conductor is bouncing back and forth out of plane. And roughly we can see that the frequency at which the out of plane motion occurs is about 1/2 of the frequency of the in-plane excitation. Yet another kind of behavior is, at a different slack level, different amplitude frequency, you can see that the motion is periodic, but the period is very different from the period of the excitation. And then finally, even though the excitation is periodic, the motion of the conductor is not periodic and quite chaotic and violent. So all this can be understood as a transition from the conductor having the same frequency as the excitation to having half the frequency of the excitation to having several subharmonic frequencies, so several fractions of the excitation frequency, and then finally transitioning to chaos. So we see chaotic response of the conductor. And experimentally, we can determine boundaries where the conductor transitions from regular behavior to highly chaotic behavior. And when the behavior becomes chaotic, there's significant additional forces in the terminal. And this occurs for all the different kinds of conductors. The phenomenon can be understood by a very simple representation, where the conductor here is represented conceptually by just 2 bars. And the out-of-plane motion of the conductor can be thought of like a pendulum. And we see that when the conductor is excited in plane, that actually changes the length of the pendulum. Because as we change the slack, the sag of the conductor is changed also. And that constitutes a kind of parametric excitation, which leads to nonlinear response and chaos. So this kind of behavior has been observed, for example, in a ship when the up and down motion of the ship can result in instability in the form of rocking. And so when designing ships, they have to be careful to account for this kind of coupling between the vertical motion and the rocking. And then, in a more humorous note, Professor Keller wrote a paper about how when a jogger runs, the vertical motion, the swinging motion of the ponytail is 1/2 the frequency of the vertical motion. So the same kind of effect we see in the conductor occurs in other contexts. So now we interconnect structures with the conductor. So this is a 230 kV transformer bushing. And here is a representation of a 230 kV surge arrestor. And we have the conductor connected in between. And we also have our specialized force measurement devices installed up top here on the shake table. Here's an example of the conductor response and corresponding model, computational model, to understand what kind of response we see. Just to give a qualitative feel for the type of dynamics that are. But for small excitations, we can look at modes and frequencies and damping ratios of how the interaction occurs. So here we're looking at different modes of the interconnected system for different levels of slack in the conductor. And we see that there are 5 predominant modes. The lowest frequency mode is one in which the structures move in directions that are opposing each other. We call this an in and out mode. And we see that the frequency of this mode actually decreases a little bit with decreasing slack. And that's because of the rate at which the vertical mass of the conductor is engaged. Part of the reasoning of how the standards think, and also how some other people who have looked at this kind of response think, is they think of the conductor response as relatively static because it's pretty light, but that's not the case. Engaging even the small mass of the conductor reduces the frequency with decreasing slack here. And we also see that the damping ratio of this mode in which the structures oppose each other increases very substantially with decreasing slack. This means that this mode is not really very influential in the seismic response. So the thinking in the code that in the standards that somehow the structures opposing each other will cause the conductor to become taut and therefore induce big forces and moments in the equipment may not be so accurate, because when we include the dynamics of the conductor itself, this effect is not very predominant. The second mode, the next higher frequency is one in which the structures move together. This is the mode that is most active or participates the highest in the seismic response. And contrary to intuition, the mode in which the structures move together has higher frequency than the mode in which the structures oppose each other. And that's again because of the engagement of the conductor mass. The other modes are out of plane modes of the equipment. The conductor is relatively flexible in the transverse direction. So the modes in the transverse direction are relatively uncoupled. And then for transformers, there is also a mode in which the bushing moves in the vertical direction. There is also nonlinear dynamic effects in the interconnected system. One effect is interesting. When the frequency of vertical oscillation of the transformer bushing is approximately twice the frequency of the rocking motion of the bushing, the same kind of parametric excitation we talked about in the conductor happens, in the transformer bushing also. So we get this 2-to-1 resonance, which substantially increases the bushing response. And when a conductor is interconnected, that substantially increases terminal forces, as we'll see shortly. Another kind of parametric resonance that occurs is when the frequency of the swinging of the conductor in the transverse direction, like a pendulum, is 1/2 the frequency of the mode in which the structures move in opposite directions. And when that happens, there's also a nonlinear effect in the interaction system, interconnected system as a whole. So when there's parametric resonance between the pendulum swinging of the conductor and the mode of the interconnected system in which they oppose each other, we see some nonlinear effects. But when there's both nonlinear effects, so the bushing parametric resonance as well as the pendulum swinging of the conductor, we see these enormous forces. So we see, forces in the range of a couple of 100 pounds. But when this nonlinear effect, these nonlinear effects cascade, we see forces as large as 3 times that. So based on all of this logic, we're able to build a framework for how nonlinear effects occur in interconnected equipment. So the worst case situation is when there are parametric resonances, both in the support structure and between the interconnected structure and the conductor swinging. This is just a quick overview, but these studies have helped establish the exact mechanisms through which substation equipment interact through flexible conductors. We understand what the different kinds of system modes are. We also see that the inertia and damping of the conductor contribute significantly to the dynamics, and the possibility of the conductor becoming taut because of relative displacement is mitigated by these effects. However, there are nonlinear dynamics in interaction, and we'll have to design systems in such a way that frequencies don't lie in this critical ratios. So we now have a rational means of accounting for interaction through flexible conductors when we do seismic qualification of equipment, and we are working on based on this kind of reasoning. We're working on proposing updates to the corresponding IEEE standards. That's the end of my presentation, and thank you again for the opportunity, and I'll be happy to take any questions.
Okay, thank you, Professor Sivasalvan. So it was a very interesting talk, including shake level testing as well. So do we have any questions from the... Yeah.
Can I ask a question?
Sure, absolutely.
Oh, okay, Arjun, yeah.
Hello, Siva. How are you?
Good to see you.
It's been a long time.
Doing well.
Good to see you again.
Yeah.
Siva, my question is related with the level of slack. Is an obligation or a seasonal effect, like ice located on the cables? Do you give some reasons what sort of slack level is used in this study? The total length, I think, 133 inch. How about the intensity of the?
Right. So you're right that the total the span is about 140, 130 something inches. We consider different levels of slack, all the way from 9 inches to no slack at all. So what this means is the span is 133 inches. 9 inches slack means the actual length of the conductor is 133 plus 9, 142 inches. So we have that extra length. That's what we call slack. So we're considering different levels of slack. The excitation, the ground motion excitation is as high as 1G. And it's a 3D excitation. I'm not sure if I'm answering your question, John.
Yes. Also, can you assume that the basement of your busher is fixed, or there's a flexibility under the busher, depending on your support condition?
So the bushing is mounted on a cover plate, and in fact, all the flexibility comes from the cover plate. The bushing, the porcelain structure of the bushing itself is relatively stiff compared to the flexibility of the cover plate.
I see.
So all the flexibility is really at the base.
I see. Okay, thank you, Siva.
Okay, thank you, Professor Sivaselvan, for this excellent work and presentation, and hope to see you soon in person as well. And so the next speaker is Professor Jerome Hajar. Jerry, are you there?
Yes.
Okay, perfect. Good morning, very early good morning to you, I guess, in the United States. Thank you for joining us. And Professor Hajar is a professor of Department of Civil and Environmental Engineering in Northeastern University. He's the C.D.M. Smith Professor and chair of the department. He served as the chair of the Structures Faculty as Deputy Director of the National Sciences Foundation Mid-America Earthquake Center at the University of Illinois at Urbana-Champaign some time ago, and was a professor at the University of Minnesota and an associate at Skidmore, Owings and Merrill some time ago. Again, Jerry serves on AISC's Committee on Specifications on Chairs, Task Committee 5 on Composite Construction, and also he was the ASC Minnesota Section President some time ago again. So Dr. Hajar was made a fellow of SEI in 2013 and ASC's in 2007, and he was awarded ASC's MOSEF award, and including many awards. I would tell AISC's Higgins Lectureship Award as well. Also, he got ASC's Normal Medal for his research on steel and composite structures, and he's a registered professional engineer. Yeah, welcome, and thank you for accepting our invitation and for joining us.
Thank you very much, and thanks to the organizers for the invitation. Are you able to see my screen?
Yes, go ahead.
All right, very good. I'm going to speak today about some work we've been doing over the last 10 years or so on seismic collapse assessment of steel and composite structures. And of course, as we all know, we consider, sorry, I'm having trouble with my screen. Are you still able to see the presentation?
Yes.
All right, very good.
But you should, I guess, pass to screen mode.
Yeah, I am having trouble with that. Let me try this once more.
All right.
You know, I am sorry, I'm having trouble sharing my screen.
It's okay. It's okay. We have some time.
I might need to reboot or perhaps send you the presentation.
Wait. You are allowed to share your screen, I believe. There's no problem with that, right?
Yeah, I am allowed. It's not behaving. Hold on, let me try once more.
It's okay.
Yeah, it's not going to let me do it.
I don't know why.
Yeah, I'm just having trouble with my computer. It's on my end.
Okay. And
my suggestion is, I think I need to reboot.
Okay. Okay, go ahead. Then how much time does it need to get back to?
It'll be quick. Let's
All
see
right.
if it works.
All right.
I'm sorry.
It's okay. It's okay. By the way, in the afternoon sessions, we will continue without any break, I guess, because we are pretty much behind the schedule. So we will have Earth Sciences, Seismology, Seismotectonics, Neotectonics, Geodynamics, and Tsunamis will be led by Professor Tuncay Taymaz. And we have also many international experts actually to talk about these issues as well. Yeah. Also, we have a structural engineering presentation in the afternoon session by Michel Bruno of University at Buffalo. That is the only presentation by that discipline. Okay, and Jerry is connecting to us again. All right, you are back.
I am. Apologies, everyone. Let's see if this works.
Okay. Now you're a co-host.
Yeah. I'm sorry, my
okay.
computer
can you send me, Jerry, would you please send me your presentation and we can run from here if it is possible.
Yep.
And you can join later if you want.
Yes.
I guess that is the only solution. Do you have anything in your mind?
No, I think that's the best solution right now. Something is wrong with my computer about sharing on Zoom.
It's okay. It's okay. We could do that, I guess. So how can you send it to us? Do you have any?
Yeah, working on that now.
All right.
I just sent you a link.
Okay. Wait a minute. Did you send it to my email?
I did.
All right. All right. Let me check my email then.
The wonders of a virtual world.
Wait. I'm checking my email. Not yet. And there's a delay between the servers. So okay, I got it. Okay, now there's a Dropbox. All right. Direct download. I'm downloading.
Thank you.
10 seconds. Done. Let me open it up. Okay, let me share my screen. Wait a minute. Share. Here is your presentation. Okay.
There it is.
Wait. Let me. Can you see it? Jay?
Yes.
All right, perfect. Go ahead. Just tell me when you need it.
Thank you. My apologies. As I was saying, I'll be speaking about seismic collapse assessment of steel and composite structures. Next slide, please.
Yeah.
And of course, we think about collapse of structures. You can advance through the animation here for a variety of reasons. In our structural design codes, we're thinking about collapse prevention indirectly. Next, please. For validation of new systems, I'll be talking today about a procedure FEMA P695, which is geared very much towards going through a lot of work just to try to think about collapse. Next, please. When we do regional simulations, we're using fragility curves that are addressing collapse prevention. Next, please. But in many of these approaches, we don't actually model collapse directly. And so I'd like to talk about that some today. First project is some work I've done with Roberto Leone on looking at seismic performance factors for composite construction. Next slide, please. And in this work, we were looking at composite frame structures, moment frames, and brace frames that have concrete-filled steel tubes or steel-reinforced concrete as the columns in the structures, and steel girders, steel braces. And in particular, we're looking at 3 seismic performance factors that are relevant in the United States. These are the R factor, seismic response factor, omega factor, the overstrength factor, and C sub D, the deflection amplification factor. And in the lower left, there's a graphical representation of these. The R factor relates to the ductility of the system, whereby we take the nominal seismic load and divide it by R to get the load we use for design. So an R of 8 would be a highly ductile system, and you're reducing your load significantly, which of course means you can design a lighter structure. And then that would reduce down towards an R of 1 for structures that are less ductile. The overstrength factor speaks about how strong the system is above the design load after you divide by R. You could see the omega naught in the figure. And C sub D relates to how much displacement it gets due to material nonlinearity beyond elastic displacement. These factors, which you could see on the lower right for composite special moment frames and composite special concentrically braced frames, had been determined many years ago without really significant assessment of the performance. And that's what we're looking at. Next slide, please. So we've developed a mixed finite element beam formulation to do the frame analyses here. This is a total Lagrangian co-rotational formulation for the geometric nonlinearity and a distributed plasticity fiber formulation for the material nonlinearity, where we're tracking the uniaxial stress and strain at each fiber in a cross section, and then at several cross sections along the length. We have implemented this in the OpenSeis framework. Next slide, please. So we've developed both steel and concrete constitutive formulations for this. The steel is based on some work from Shen, and we've made modifications here to account for local buckling in the steel tubes of concrete-filled tubes to account for the residual stresses from cold forming. In the concrete, we've augmented the work of Cheng and Mander to account for confinement like we see in concrete-filled tubes. Next slide, please.
It's 14 hours.
And we have validated this against probably over.
You're muted.
Yeah, sorry. Validated this against over 100 experiments, pure axial load, pure flexure, proportionally loaded beam columns, non-proportionally loaded beam columns, cyclic beam columns like you see on the right. For both concrete-filled tubes and steel-reinforced concrete columns. Next slide, please. And the procedure that's laid out by the Federal Emergency Management Agency, FEMA P695, has an approach that we're using now to assess the behavior of structures and to determine these seismic performance factors. And so in this approach, we develop a series of archetype structures. You see plan and elevation views here, moment frames on the left, brace frames on the right. And this table here lays out the different parameters that we have. For example, high gravity load versus low gravity load, different base spacings, high seismic load versus moderate seismic load, different concrete strengths, different number of stories in the moment frames and the brace frames using rectangular CFTs, circular CFTs, et cetera. Next slide, please. And for this parametric investigation, we can see here the gravity load that we used for design and the masses that we used for design, and then for the analyses on the right, according to the FEMA P695 procedure. We use 2.5% damping in the dynamic analyses we're doing, and as would be typical in frame analysis, we're not modeling collapse here directly. We're not modeling fracture. We're not modeling lateral torsional buckling. But this is the state of the art on how we assess seismic systems in the US. Next slide, please. And so this procedure would involve doing both static pushover analysis, such as we see here, which helps us look at the overstrength factor. Next slide, please. And a series of dynamic analyses, and in particular doing incremental dynamic analysis, which some of you might be familiar with. This is an approach where we do a large number of nonlinear dynamic analyses and aggregate the results for a plot like this, which is plotting the magnitude of the earthquake on the vertical axis and the maximum interstory drift in any of those particular archetype structures on the horizontal axis. This graph is for a single one of the structures and for numerous earthquakes. Each one of the lines is a different earthquake, and we scale that earthquake to different values, run a nonlinear dynamic analysis, and plot the maximum interstory drift. And so that creates a graph like this. And this helps us to assess collapse, where we have procedures that I'll talk about in a little bit for estimating when a structure collapses based upon some parameters of these curves. And the blue line, which represents the design earthquake, can then be compared to our estimate of collapse assessment, which is the red line. And that in turn feeds into an evaluation of the seismic performance factors. Next slide, please. So for composite structures, we found that the R factor for moment frames and brace frames that we've been using for years is acceptable, so that was good news. We found that the overstrength factor, omega naught, was also generally good, although a number of the moment frames were controlled by stiffness to limit the displacement, and so they do have some significant overstrength. And then the C sub D factor that we've been using is also proving to be quite reasonable. And there's been some discussion in the US about increasing that C sub D factor significantly, but we're recommending that we don't do that. So this is the nature of the procedure that gets used for assessing collapse and performance of structures. This was for existing systems that are already for which we already have design provisions, but any new structural systems that are put forward in the US typically goes through a procedure like this. Next slide, please. So can we take a next step to try to model collapse more directly in our work? And for this, I worked with Junho Song, who's now at Seoul National University. You can see a number of my former students here. Next slide, please. And so here, let's go back one. Yep, thank you. Here we're doing high fidelity modeling, so continuum finite element analyses, fairly fine mesh. So these are computationally expensive, but certainly still quite feasible. And so modeling both geometric and material nonlinearity. For the material nonlinearity, we adopted a plasticity model from Yoshida and Umura. This is a bounding surface formulation with a strain-based memory surface. Next slide, please. I'm not going to go into the details of any of this. And what we predominantly worked on was ability to simulate the initiation and propagation of fracture in these structures through using element erosion, elimination of finite elements. And so we are tracking through the plasticity formulation accumulation of damage as a function of triaxiality and load angle. And when we reach a certain damage level, we start to soften the stress, as you see in the red curve here. And when we hit zero stress at any one of the Gauss points in a finite element, we eliminate the element. And through this, have a rough simulation of propagation of fracture with the intent of being able to model collapse of structures to the ground. Next slide, please. So the formulation is quite general. We have capability of simulating a variety of different metals and have calibrated this for grade 50 steels, but also for bolts and welds with the limited test data that's out there. This shows plan views of principal strain space showing the surfaces that are used for prediction of when we initiate the fracture. Next slide, please. And so this can have a variety of shapes depending on your metal. And as I said, it's predominantly a function of triaxiality and load angle, which really help govern fracture. Next slide, please. This is calibrated to a series of specialized coupon tests that have been developing in the fracture mechanics literature over the last number of years. You could see there are various shapes here, and these different shapes give you a range of load angle and triaxiality and other parameters of stress and strain that help you cover the space necessary to try to have a robust fracture performance. Next slide, please. So there are a number of parameters in this model, and we use particle swarm optimization to calibrate these parameters. This was done for a 572 grade 50 steel in the plots that we're showing here, comparing experiments to the analyses. Next slide, please. And so we validated this against a number of typical tests that we are all familiar with respect to seismic performance of steel structures. But I just want to show the culminating experiment here. This was a shake table test done at Buffalo by Helmut Krauwinkler and Dimitrios Lignos some years ago. This was a 4-story, 2-bay steel structure, excuse me, that you could see here. The green are the masses that were used to excite the frame. This was a 2-dimensional frame. Next slide, please. This was at 1/8 scale. And they had specialized connections here. You'll see a close-up of this in a little bit, but these are essentially a pin with a couple of tensile coupons that represent the flanges. And through this, we're able to track plasticity and fracture quite carefully. This was one of the features of this system. And the system was designed to collapse. Next slide, please. So this shows an example of one of the experiments they did on the connections. And this shows you the nature of the connection and also the general capabilities of the formulation that we've developed, both with respect to geometric and material nonlinearity and with respect to the fracture. Excuse me. So you can see on the lower right, a comparison of the experiment and the simulation. Now, these are using calibrated parameters from the coupons that I showed earlier. Next slide, please. Next slide, please. Yep. And so this animation shows our capability of picking up the shake table tests. Now, there were 5 shake table experiments done at increasing levels of earthquake. This is the last one, which actually caused the collapse of the structure. And so a number of the connections here, of course, yielding and fracturing like you see at the bottom center. And able to pick this up fairly well. You can see some of the force and accelerations are a little bit off in the time series, but generally quite good. Next slide, please. And this shows some of the results. We were able to track the location of where these failures occurred quite accurately. Next slide, please. Then this led to a second phase of this project where we wanted to see if we can develop an approach for predicting when collapse occurs. This is going to help us, for example, develop fragility curves. And so for this, we also did a series of analyses, but now using the approach that Lignos used for his simulation, which were beam elements with nonlinear springs, such as you see in the lower left. And here, again, on the shake table, they did a series of experiments at increasing magnitude scale factors on the 1994 Canoga Park earthquake record. And the scale factor of 2.2 is the one that caused collapse. You could see our analysis compared to the test data here was matching well. Next slide, please. And so what we developed here was a method of predicting when collapse occurs. And qualitatively, we're finding that what we call the gravity energy in a structure, when it heads towards infinity, that is representing collapse. The gravity energy is essentially the vertical displacement times the mass. Quantitatively, we found that when this exceeded the input energy from the earthquake, then that was reaching a point of no return. And so, for example, nope, next slide, please. That was perfect. If you see here at the scale factor of 1.9 on the shake table, you could see in the blue the accumulation of the input earthquake energy, and in green the accumulation of the gravity energy. And these energy quantities just continue to accumulate with each of the successive shake table tests. Next slide. And so as we go now to the scale factor of 2.2, which caused collapse, and you can see with the blue arrow there, we're just rescaling here. The earthquake energy continues to accumulate, starting at about 103 seconds. And then the gravity energy also accumulates and indeed starts to shoot up towards infinity. And when we cross over, that's what we're designating as the point of no return on collapse. Next slide, please. So the way in which we can use this, for example, is when we're assessing collapse in an incremental dynamic analysis for use in determining fragility curves or in use in determining the seismic performance factors like we were seeing before. For those who are familiar with the incremental dynamic analyses, we often assess collapse by one of two procedures: an intensity measure, in which we take these squiggly blue lines, and when we hit 20% of the initial slope, we deem that to be collapse. Those are the green dots. Or we just say 10% interstory drift. Those are the yellow dots. Both of those are pretty arbitrary. The energy rule we developed are the red dots. Next slide, please. One of the challenges in using incremental dynamic analyses is these lines do not increase monotonically. And so, for example, on the left for the displacement-based rule, you could have 3 points that are at 10%. But with the energy-based rule, those energies accumulate monotonically. And so there's really just 1 point designated collapse. Next slide, please. And so then we can use that, for example, to develop a collapse prevention fragility curve, such as we see here. And there's a variety of other ways in which you can use a measure like that. Next slide, please. So in conclusion, we've looked at methods and considered methods for assessing collapse, both using current approaches from FEMA P695 to look at composite structures and assessing seismic performance factors, and then through developing fracture-based formulation for high fidelity modeling, and using that to form the basis for predicting of collapse, and then developing a new collapse criteria that's based on energy that can then be used for development of fragility curves. I apologize again for my technical difficulties and appreciate the organizers' flexibility on this. Thank you.
Okay, thank you so much, Professor Hajar, for this excellent presentation. I would like to stop sharing, wait a minute, just to see. Do you have any questions from YouTube or from the Zoom participants? Any questions? I have very quick, very simple one. These seismic performance coefficients given in Eurocodes 3, 4, are you familiar with those?
Roughly, yes.
Okay, so is there any big difference between your findings and in our Eurocodes?
Well, I haven't studied the ones in the Eurocode directly, but from my understanding, certainly, while the nature of the specifics of those are different, the intention is quite similar. Yes. And so I would anticipate similar findings.
All right. Okay.
And I think in general, you know, one of the advantages of composite construction, and in particular concrete filled tubes, is they're pretty robust.
Yeah.
And so a bit forgiving on some of these issues.
Okay, any more questions?
Can I ask one question?
Yes, Professor Takeuchi. Yeah.
Thank you very much for the nice presentation. In the later part, it's shown that the collapse of the structure is decided by the release of the potential energy. In other words, the P delta effect. But I wonder in which cases you think that this collapse is decided by the low cycle fatigue of the element.
So I think the gravity energy is able to pick up both of those. And that's one reason that we liked it. Whether it's through material nonlinearity and fracture, or whether it's through geometric nonlinearity, we think this energy metric would pick that up.
So you mean that some members low cycle fatigue lead to the direct increasing of straight angle to the P delta collapse?
That's correct.
Okay, thank you very much.
Okay, again, Professor Hajar, thank you so much and for your very kind contribution to our online event, and hope to see you soon.
Thank you.
Thanks a lot. Thank you. Also, thanks for accepting our invitation in a very early time in the United States. Sorry for that. All right, thanks. So now it's time to hand over to Professor Tuncay Taymaz. This session, the afternoon session or Earth Sciences. Professor Taymaz is a professor of geophysics engineering here at ITU. He's an internationally well-known professor in this area. And yes, Professor Taymaz, it's your turn. And sorry for this late. I know we are quite behind this schedule, but it is quite difficult to synchronize everything at the same time. Thank you for your understanding again, Professor Taymaz.
Well, good afternoon, and thank you for all of the participants for sharing their time for this very nice weekend. We are all imprisoned. It's all because of our faults. So we apologize once more again for being rather late for about 1.5 hours due to the technical problems in the morning, early hours and lately. So we have a distinguished scientists in earth sciences. They are well known globally, so I will have no time to introduce them. So they are already by invitation only participating in this meeting, and they are all well-established scientists. I am especially honored to welcome Professor Laurent Jolivet from Paris. Bonjour, monsieur. So we will have enough time, lengthy time, I hope to be on time. So we are heading with Laurent. Please share your screen. And we have 20 minutes, maximum 25 minutes, please.
Okay, do you see my screen now?
Yes, excellent, beautiful. You can make a full screen.
Okay. Which do you see? Do you see the only one image or two images?
2 images with timing.
Okay, that's not the good one. What about here?
No. Same.
It's the same. Which one do you see? Only one image or two?
No, we see your entire image.
Okay, so just one image. Okay, that's great. So thank you very much.
No, this time now it's changed again. Double picture with timing. Rehearsal mode. This is a rehearsal mode.
Okay. And here?
The blank screen.
Wow. Wait a second. What about now? Oh.
We don't see anything except yourself. No screen sharing.
And now, is it?
Blank screen.
Oh.
Now it's a full screen, yes. This is right. You have to go back to the first page, first figures.
Okay, we should have it now.
Yes, I think it's all right now.
Okay, let's go now. So thank you very much for this very kind invitation. So I'll try to go through this comparison between the say Neogene extension in the Aegean Sea and what is going on now, and especially of course this recent summer earthquakes last year. So this earthquake, it's not the first one in the area, of course, but it's rather large magnitude, and it's characterized by a north dipping fault, as you know. And what is pretty sure is that this deformation has been going on for quite some time, because just north of this fault, we have a basin developed. And also to the west, further to the west, the Ikaria Basin. So we have a rather long-lasting deformation, still active at the present. So we are in the framework of the general extension of the Aegean Sea in the Bacard Basin. And on the lower image here, you see strike slip focal mechanism in green, blue ones that are extensional and red ones that are compressional. And in the area where which we are talking about, we have mostly extension. And this extension, it's mostly localized in the eastern part of the Aegean Sea, part of the offshore partly, and also of course in Western Turkey, but also in Greece. And the most striking example is the Gulf of Corinth. In the middle of the Aegean Sea, it's quiet at the time, rather few earthquakes, or very, very small ones. So the Samoth earthquake here is part of a system of active deformation that is characterized at the scale of the Menderes Massif, for instance, by several very large grabens. And these grabens, they are characterized at present with steeply dipping faults, but in the Neogene, or even quite recently, they were characterized by low-angle normal faults that I will show briefly afterward. So if we just move briefly to the Gulf of Corinth, the Corinth Rift in the west, this rift is one of the fastest on Earth, and it is characterized by a very significant asymmetry. The main normal faults active normal faults that are shown in red, sorry, on this image, they are on the southern side, while the main epicenters of the main earthquakes, they are on the northern, below the northern margin of the rift. And this asymmetry is in fact linked to the fact that the main faults are north dipping, and they are cutting along the southern margin of the rift. And the sediments, the deposition of sediments in the rift itself is also very asymmetric, with a sort of a half graben. If we go to the westernmost part of the rift, there it's slightly different, but the asymmetry is also with the same sort of asymmetry, with the main normal faults on the southern margin of the rift. And you see here the distribution of this famous work by Rigaud and others in 1996, with the distribution of micro earthquakes here, delineating a possible low angle normal fault at the depth of the brittle ductile transition there. And these are more recent studies, and these more recent studies in the same area, they suggest also the existence of a low angle normal fault or brittle ductile shear zone dipping toward the north, and which is probably the development of a future large scale detachment. This is a picture we showed in a paper in 2010. And you see the low angle detachments here that are no longer active. And you see at depth the probable low angle detachment, which is active today. So we have this very asymmetrical feature in this fast extending rift. So what about the oligomycin deformation now? If we go in the eastern part of the Aegean Sea here, and if we compare what's going on nowadays in Samos and what has been going on in the Menderes Massif, for instance, in the Alaşehir Graben, extension there is characterized by a low angle detachment, which is very well known here, the Alaşehir detachment. And this detachment is very well expressed in the field, and you can walk on the fault plane if you like, and it extends all along the entire length of this huge graben, and it's also dipping toward the north. These detachments, they have shaped the evolution of the Menderes Massif during the Neogene. If we now go further to the well, let's have a look first at a north-south cross-section of the Aegean Sea, and at lithospheric scale. So you see the south on the right, north on the left, and the extension in the Backward Basin, if we focus on the Cyclades here, has worked with low-angle detachments that are quite famous, and these with several metamorphic core complexes. And these metamorphic core complexes, they are sort of windows showing the deformation in the middle and lower crust. You note here that these detachments are mainly dipping toward the north. So let's see a few examples here. So we have in this area, that's the area with two islands that we will see, the island of Tinos here and the island of Mykonos, where the detachment is the most spectacular. So you see, for instance, on this little islet just north of Tinos here, it's called Planitis. The detachment is very well, is quite obvious here in the field between the upper Cycladic unit and the Cycladic blue schist unit. And it's a rather spectacular feature that you see here with the Cycladic blue schist in the footwall and the upper Cycladic blue schist in the upper plate. Close-up views of this show that the detachment is a very low angle fault here that separates these two units. It was active in the Miocene, started already in the Oligocene. And another view separating the mylonite, ductile mylonite below the detachment from breccia in the upper part of the figure. Another view of this detachment here with several branches and very clear sense of shear evidence here, always toward the northeast. Then in the same island, we have this granite that formed in the middle Miocene. And very close to the intrusive contact between the granitic intrusion and the upper Cycladic unit, we see these very spectacular features where the apletic sills, intruding the upper unit, are cut by northeast dipping normal fault here, again showing this very clear asymmetry before, during, and after the emplacement of this granite. Let's move to another island that is Mykonos here. And there the detachment is even more spectacular. Okay, so Mykonos Island is made mostly of a granite, which is shown in yellow and orange color here. And to the west with the core of the metamorphic core complex that is made of granite and migmatites. But I will concentrate on the detachment itself, which is seen in the eastern part of the island between the greenish upper Cycladic unit and the yellow granite here. So let's move to that. So the granite is deformed internally. You see the stretched feldspars here. Again, here, when you're closer to the detachment, the feldspar are very strongly stretched with a very consistent direction. And if we look at the contact here, the detachment, you see it's very low angle on the cross sections. And if we go to that little beach in the northwestern part of the maps here, it's called Mersinni Beach. The detachment is very conspicuous, very easy to spot here and between the granite and the upper unit here. And I'll show you a few other pictures. You see here the upper unit in green and the granite in sort of pinkish color here. And the close up on these structures, see very low angle normal faults here and shear zones, top to the east and northeast. Below, the granite is transformed into an ultramyelinite, signing a very intense deformation during this extension. Another view of this detachment can be observed in the northeasternmost part of the island near Cape Everos here. So you see in reddish colors, these are the sediments, thin detachment sediments, so late Miocene sediments here. And so if we look at this section, you see the dip of the detachment, which is very low, around 15, 12 degrees. And so we'll have a look to this, to these outcrops there. And these outcrops are quite spectacular. Probably the most spectacular detachment in the Aegean Sea here. You see the sediments that are brecciated here, this sort of violet color. And the detachment is very clearly seen here with a low angle toward the northeast here. Actually, we have two detachments, what's called the Livada detachment and the Mykonos detachment. I will not enter into any details. This is another view of the Mykonos detachment here, very low angle here. On the other side of this small peninsula here, we have an even more spectacular view of this detachment. You see the lower part of the landscape here is made of the granite, and the top part is made of the thin detachment sediments, Miocene sediments. And you see the detachment is a very low angle feature, and you see the sediments that are tilted and separated cut by northeast dipping normal faults here. So we will see a zoom on this. You see the granite in the lower part of the figure. You see the sediments here, Miocene sediments, with normal faults and thin extension sediments here, as shown by the fan-shaped deposits. And you see the very conspicuous asymmetry and tilting of the consistent tilting of these sediments. The detachment plane is also very easy to spot here. You can walk on the detachment plane here. Okay, and so we some time ago we compared these outcrops in the Aegean Sea with what we see below the Gulf of Corinth here, and we think that what we see in these different metamorphic core complex is equivalent to what is going on now below this active low angle shear zone that is evidenced by microseismicity below the Gulf of Corinth. Just a brief look to Naxos, which is famous because it was the first core complex described in that area. So low angle detachment as well. And in the middle, below the detachment, we have a magmatic core, so high temperature metamorphism here exhumed by this detachment. And also a granite that has intruded the dome, and it is also affected by this low angle detachment. And you see here a picture of this detachment here between, on the right, the granite, and on the left, the Miocene sediments. So the general picture is something like this, with low angle detachment dipping toward the north, capping with sometimes thin extension sediments, and capping metamorphic core complexes with a core of migmatites and sometimes granites placed during the extension. So that's what's going on during the Miocene. Further to the south here in this, for instance, this small island of Seriphos, we have exactly the same type of picture, except that the detachment is there dipping toward the south here. And this is one view of this very spectacular detachment in Seriphos. Another view, and this is very similar to what we see in Tinos and Mykonos, only that the only difference is the sense of shear along this detachment. Then in the eastern part of the Aegean Sea, recent works have shown that we have mostly top to the north shearing along this sort of detachment in the islands of Valeros, Alki, and so on. And so in a large part of the area, we have this top to the north sense of shear along these detachments. And this is the case, for instance, in near Furni, just south of Samos, with this very clear detachment we see on Thimena Island here, which is top to the north. And further to the south here near Kalymnos, we have a longer cross-section in the eastern, in the Dodecanese here. We have mostly top to the north detachment, and when we arrive in Kalymnos, we have a south-dipping detachment here. So we have mostly top to the north, and along the southern border of the Cyclades, we have top to the south detachment. This is reminiscent of what we have in Turkey then, with south-dipping active normal fault as you see in the picture here. So what we observe, I think, is some continuum from Miocene ductile extension with the North Cycladic detachment and the West Cycladic detachment system toward recent brittle extension with the Gulf of Corinth, the Menderes Massif, Samos earthquakes, and so on. For me, it's the same evolution. But we have a difference. And this difference is that extension is more localized in the recent period than during the Miocene. So why? The main reason probably is that the slab, the Hellenic slab, is torn into several pieces, and that the Cyclades rest upon above a part of the slab that is isolated from what is going on in Turkey and what was going on below the Hellenized further west. So we have less deformation above the slab there, and the deformation is concentrated along the edges. So we modeled this sort of evolution some time ago, and you have this 3D model here with slab tears that you see from below. And if we look at the deformation from the surface here, you see the velocity field in black here, and you see the strain intensity, the strain rate, sorry, in these colors from green to red. And you can compare this with what is going on presently in that area with a GPS velocity field in the upper right and a strain rate calculated from this GPS velocity field in the lower right. And what you see in the experiment is that we can reproduce very easily the North Anatolian fault and the extension further south here. So I think we have captured the main engine, which is slab retreat, of course, but also slab tearing. Another model here to finish up with a different initial setup shows the slab retreat here and the flow in the mantle that is associated with the slab retreat. In 3D, you see that because of the slab tear, you have this toroidal component of the flow here. And if we zoom on these images here, you see that the mantle is flowing faster than the crust in the back-out region, imposing a shear at the base of the crust. And this shear here is also well seen on this diagram where you see in red the velocity. And you see that we have a velocity gradient in the lower continental crust here. That means that we have a shear zone there. And this shear zone is top to the north, which is compatible with what we observed in the metamorphic core complexes and in the most recent extension in the Gulf of Corinth or here near Samos. So the conclusion that the Samos earthquakes and similar ones in the Corinth Rift here result from the same processes as what had been active during the Miocene and part of the Oligocene, that is slab retreat. And the associated deformation pattern at crustal scale is quite similar. But the main difference is that the recent deformation is more localized because the Hellenic slab is torn in several pieces, and that deformation tends to localize above the slab tears. So this is in line with what we said earlier, that the Miocene deformation is, and the active deformation is the continuation of what has been going on in the Miocene. And this was well said recently in this paper very recent paper by Meng et al. Claiming that the sum of earthquakes is the result of slab retreat and the continuation of a long story. Well, thank you very much.
Okay, thank you very much for a very nice presentation, Professor Jolivet. We have time for questions and discussions from audience participants. Please, as I don't have a sign of some of the following speakers due to the very early morning in California, but we have time for further discussions, questions. Maybe I should start. Dear Jolivet, do you have time today to follow up the following talks, presentations? Because my former PhD student, Dr. Judith Maria Confal, she will present our recent tomographic results on the tier of the Hellenic Trench and some slab break-off and so on, based on her PhD works that we published in 2020, 3 tomography papers in JGR and 1 in EPSL. Maybe you missed some of them, and that's the Meng et al. That we all know it, but just to open up discussion, maybe Judith can ask a question if she's hearing me. Do you have any
yeah, I'm not sure I can attend to many of the talks because I'm with the family here.
Yeah, you have a family gathering today. Yeah.
Yeah.
Yeah, we published alternative models to tomography, a breakup of the and tearing of the slab in the Hellenic Trench and from Adriatic Sea and so on. It's all been published last year.
Okay. I'll have a look to this paper. Thank you very much.
Okay, then if there is no questions, we can continue with Professor Rob Gowers, if he's hearing me, and we have plenty of time, Rob, so we don't have to rush with 20 minutes because I don't see a sign of Sylvian Barbot yet, so we have time. Thank you very much, Jolivet. Merci beaucoup.
Thank you very much.
Okay. First of all, can you hear me?
Yes, indeed, very clearly, and the picture is fine.
Okay, excellent. So let me start with thanking you, Taimas, for inviting me. It's an honor to be here in your session. I will give, as promised, an overview of the geodynamics of the Aegean Sea region. And to be honest, Laurent set me up already quite nicely, and he already introduced quite a few of the things that I will be talking about. I will show some new numerical analog experiments that are particularly relevant to the region that we're talking about today, which is the eastern part of the Aegean region, of course. Okay, the Samos earthquake took place on Samos, not a big surprise. The reason for me showing this figure is that it is something that is clear also from Laurent Jolivet's presentation, that there is quite a few active faults in the region. Not all faults are equally seismically active, but certainly all those faults may or contribute to the seismic hazard in the region. Well, clearly the faults near Samos were active that way, as we found out last year, fortunately. So I want to start with what we knew before the event. And before the event, our geodesy colleagues had started decades ago already collecting geodetic data using GNSS velocities to see what is moving in more detail. And here you can see a recent compilation and analysis by D'Agostino et al. where you see the escape of Turkey, and then here turning into the Aegean region and somewhat accelerating. And that has become quite a renowned structure for all those working in the area. And so it is also quite a bit of inspiration for subsequent work. Like one of the things that has been happening in various studies is to investigate how much slip and what the slip rate is on various faults. And a whole bunch of block models have been developed based on those GPS observations. And particularly this one is interesting because it does have a major block boundary in the region of Samos. It's slightly different from where a geologist would draw it probably. But I think this model captures something interesting, namely in the context of this analysis. And it's always going to be, there's going to be question marks related to the exact choices of the boundaries, and also whether all the faults are continuous and enclosing blocks, things like that. But what is interesting in the context of our discussion today is that the rate that they find of extensional motion across this boundary here is on the order of 7 millimeters per year. Give or take a few, but that is a very substantial amount. So on the basis of that already, we should be concerned about this. Now, the next thing that we should think about before any earthquakes in seismically active regions is whether those faults are then creeping, or are they building up strain? That is, are they locked? Well, in this region, you see that I'm now stepping towards a recent study that we did on South America margin, and there we identified the locking pattern. And yeah, it would have been so nice if something had already happened with the geodetic data in this region, but most of the work, recent work in Turkey has been on the North Anatolian Fault with lots of very interesting studies. And here you see one that I particularly liked by Lange et al. And where they also identified the locking patterns, but the locking patterns on faults along the Aegean west coasts remains unclear. So from that perspective alone, it is unclear whether the faults near Samos were creeping or building interseismic strain towards, in preparation of a next earthquake. However, we obviously have more information than that. And here you can see, here I drew from the whole slew of very interesting papers that was triggered by the earthquake, a paper by Ganas et al. And in this figure, I chose this figure because it also shows the historical seismicity in the region very well. Focuses mostly on the bigger events, and as you can see, they're quite substantial in many cases. So in that sense, it is quite likely that there was strain buildup. Otherwise, we would obviously not have had these historical earthquakes. However, whether it was on this particular fault, that is something we don't know from the geodetic observations or otherwise. Okay, now the event itself was initially identified by various institutions. Here I list one focal mechanism that is, of the USGS. And as has become clear from subsequent studies, most of the authors looking at the event favor the north dipping fault plane of the two fault planes, and that makes it then a normal faulting event. In this study of Karrakostas et al., they looked further into the seismic moment release distribution on the fault and found that, yeah, it's quite variable, but most of the energy release was around the epicenter. And that roughly is in the region of more than 10 kilometers deep. So all very interesting studies, I would say. Now, the Altunel and Penard looked also at the aftershocks, and the aftershocks have somewhat variable characteristics. But what they share, they very clearly show, is that the t-axis of these events, they are quite uniformly located, nearly horizontal, slightly off towards the to east from the north, but very consistent in their slip behavior, therefore. So we can conclude that both the main shock and the aftershock conform with the historical extension direction. Here I repeat a figure that Laurent Jolivet just showed, namely that the events that happened historically. And it is quite a well-established historical pattern of earthquakes, but also of geological strain. So in that sense, the earthquake was not a surprise either. Okay, the next question is what drives the surface information? And in the study of Meng et al., that came out shortly after in Scientific Reports, essentially their title already says this: Greece and Turkey shaken by African tectonic retreat. What tectonic retreat is a figure of Laurent. Sorry, Laurent, your citation hasn't been dropped below the figure. The overriding plate extension is driven by trench retreat as a consequence of rollback of the Hellenic slab, and that is very nicely displayed in this graph of Laurent and co-workers. And I'm not going to challenge that. That is very clearly a very substantial motor of the entire extension, and also very likely of this earthquake. I'm going to go to a part of the eastern Aegean region, where also we know the trench ends somewhere, and then is followed up by what we refer to as a step fault system. And previously we identified, in our 2005 paper, for instance, we identified the Pliny-Strabo as a step fault system. And for those who are not completely aware of what a step fault is, imagine I rotated the figure from the original figure of the original paper. So here you see subduction zone. This plate is subducting beneath the overriding plate. So that would be this Africa, and this would be the Aegean region. But importantly, where this essentially part of the plate is descending into the subduction zone, the adjacent part to it is part of the same plate, but remains at the surface. As a consequence, we identified this point as a point where tearing, lithospheric scale tearing, is required. And so we call that the step, and that stands for subduction, transform, edge. This is the edge, and it propagates. This is the geologically more interesting feature, which is the step fault. So that's where, as you can see, for instance, here in these rotation symbols, there is differential motion between, and that strike slip motion between those two plates. But this is a plate boundary which lengthens and lengthens and lengthens as subduction goes on. So we said in the 2005 paper, that is, well, we in this vicinity, we didn't make it a solid line. We were not sure what its orientation was, either this direction, other ideas have gone into this direction. So we followed this up in a study with Ali Özbekir, and essentially he looked at the tomographic imaging structure again at depths greater than 200 kilometers, because we know it's relatively reliable there, but also combined that with surface structural evidence of strike-slip surface deformation. And all that agreed with what we had said in our 2005 paper. So that although we talk about the Pliny-Strabo trenches, it is a step fault system. However, more recently, Bocchini et al. Made a point which is excellent, namely in the upper mantle at a depth less than 200 kilometers, when you take a cross section through any data, let me first focus here on the ISC data. What you see in that data in the cross section here, we see a full subduction zone in the Wadati-Benioff zone, extending below 100 and then extending further down. And actually, we know from seismic tomography that actually the slab continues further on seismically. So that's a consistent picture. More interestingly, and more relevant for our discussion today, is that here in section number 5, so perpendicular more or less to that trench, or parallel to the trench and perpendicular to the subduction direction, there is also something similar. And Bocchini et al., and also before that, Thomas Meyer, asked attention for that issue because essentially they said that's not consistent with a step or a step fault. Now, from the ISC data, we were not sure, and they also looked at what they had, regional data from their networks, but they essentially confirm what they had found also based on the ISC data, and that indeed there is, irrespective of which cross-section you would take, there is evidence for at least indications for subduction deeper into the system. And yeah, in a weird direction from the perspective of a step. Then also more recently, together with Andreas Fichtner, I looked in his tomography at the more shallow structures, and we also found an anomaly in this region, as you can see here in the dark structure, which seemed to be off from the Aegean slab. Essentially, from the perspective of a step, it should not have been there. We talked about it.
Hours.
Thank you. The Samos is here, and it would sit roughly at the edge of that anomaly. Okay. The other thing one can ask then, okay, it's all great, but why would this be relevant, for instance, today? Well, if you look at the velocity field here, you can see essentially that vectors here are nicely pointed towards the Hellenic Trench here, but here they essentially take a more, if you like, eastward turn, as if there is something pulling here into this direction. And that's also something that was already found from the geodetic observations, the analysis by Neist and Thatcher, who claimed that there is evidence for this extension. And that may be actually true. So the velocity field also suggests a step perpendicular forcing. So we decided we needed to look at the detailed tearing process of step propagation. So we set up an analog experiment with a continental plate, in the middle an oceanic plate, and then a continental plate. So this is 2 steps, which we pre-cut so that subduction had already started. And then we let the system develop itself. And then the tearing here would subsequently develop dynamically. So I'll show you a couple of movies. First, a top view. We're looking, so now on top of the slab. So here you can see the asthenosphere, and this is the slab which has started sinking. This is the pre-cut. And you can also clearly see that now it ends, and the real tearing, or at least it should have happened, but it doesn't. As you can see, it's delayed. The subduction, however, continues. The asthenosphere gets on top of the overriding plate, but it is simply that the tearing here is very strongly delayed. Okay, now we wait a little bit, and now you start seeing that essentially here, material from the continent here. Oh, no, that's not so good. I should need to restart. That's my mistake. I should be able to get it here. So material is starting to move in. There's extension. So that is slabward extension here and here. And that's simply because part of that material, which is still attached, is being dragged in with the slab. So I'm going to move it a little bit faster. And now you start seeing some light from the sides coming in here. And that is the tearing has started. And then, it happens at greater depths, obviously. There's rebound, as you will be able to see as I move it. See here, a asthenosphere has disappeared again, and the tearing here has started. And here at a later stage has also started. So that's the top view. Now we'll look at the side view. And here you see a structure developing, essentially that continent being dragged along with the slab. So it becomes like an amphitheater of the entire system. And again, I'll try in the interest of time to see whether I can speed it up a bit. And you can see
Don't
here.
worry, we have time, Rob. Please take your time. We have time.
Okay. Then I'll leave it so that you can easily see it develop. Meanwhile, I can tell you that 1 minute, 1 hour of model time, which you can see here, is roughly 0.75 million years. So our scaling, we have paid quite a bit of attention to the scaling. And the reason why this tearing happens eventually is that our lithospheres have a very new material, which is highly nonlinear, such that it represents Earth materials better than other analog materials. So we have quite some confidence in this result and in the development of the tearing at a later stage. Okay, now it starts getting a little bit slower, so I will. Very clear. So it's and here we start reaching the end of our aquarium, so that's why it is continuous. So now I'm reaching out, and of course, neither experiment is going to be in perfect representation of the real Earth, but here is my tentative interpretation of the results. Here you can see one frame out of that movie that I just showed. So the way I would interpret this is that the Hellenic slab is this feature. You're not surprised. This would be the Aegean plate. And okay, the trench must sit roughly in this direction here at this point, roughly. Then here somewhere along this part of the plate boundary, we have the Pliny-Strabo trenches. Then there is Rhodes and Samos. But as we saw, Samos roughly sits at roughly the end of where the anomaly ends. It doesn't continue, and I particularly mean the shallow anomaly. It does not continue very much further to the north. Obviously, the tomography is of limited resolution, so we cannot be entirely precise, but certainly it's an interesting correlation when you start thinking about this process. So the consequence is that, and I'm already moving towards my conclusions, the consequences well, first of all, let me have those conclusions. The GNSS observations suggested strain buildup prior to the 2020 earthquake. Normal faulting during the 2020 earthquake was consistent with previous events, so no surprises there. But it allowed us to look into the driving mechanisms. The main driver was no surprise either. It is rollback of the Hellenic slab. And Laurent said that already, and that has been essentially an understanding within the community. But we suspect that some fraction, which at this point is yet unknown, and we're doing now numerical experiments to constrain that, some fraction is also driven by the so-called Pliny-Strabo slablet. So that is that lateral feature that developed due to the delay in the shearing of the slab due to the breakoff. So we think the event itself occurred in a highly interesting place, and we are already following this up, and you'll see our paper soon on this. Thank you very much.
Thank you very much, Rob. It was a very nice talk covering all the models you proposed earlier on the recent ones. And we have plenty of time for discussions to enlighten those who are not familiar with the local tectonics. Professor Jolivet, Jury, Thanasis, do you have any questions? We have time. Jury, please.
Yes, thanks for a nice presentation. I would like to ask you whether your model does include also an explanation for intermediate depth earthquakes in this zone, stress concentrations, etc., in particular intermediate depths.
And thank you for the question. And which zone are you precisely referring to?
No, I don't mean any special zone. I mean in your model.
In our model does not produce seismicity. So in that sense, I only can speculate, but it's the intermediate zone seismicity is likely related to the tearing. While there is a continuity of this Hellenic slab and this lateral slablet, and the Aegean slab is sinking fast, it essentially stresses the slablet, and the stresses hopefully likely will generate earthquakes.
That was my question. Thank you.
Okay.
Any more?
Yes, I can ask Rob a question. This great presentation, this one also, and the one by Laurent Jolivet before, of course, very interesting ideas going back several years. One, I thought also you, Tunçay, could perhaps have a comment that I thought that the Hellenic slab, somewhere below Rhodes, is disrupted and falls down in the asthenosphere. Yeah. So there is an asthenospheric window between Rhodes and, let's say, Antalya, in Turkey. Yeah. Right. So the rupture of the slab basically is towards the east of Rhodes, i.e. the Hellenic slab is being torn vertically east of Rhodes. So the slab is intact west of Rhodes until Kefalonia, and east of Rhodes, there's no slab. There's an asthenospheric window. And this has resulted also in an uplift of relatively uplift and a hot lithosphere in this region. Yes. So Rob, is this incorporated in the model? Because I did not follow that. It was just a short presentation, so I need to read your paper. But did you take account of this or the other way, or the slab actually dips, the slab tier dips, let's say, the other way to the west?
Yes, yes. Thank you for that question, because that is indeed something that I a little bit deliberately did not discuss. And it was not deliberate because I did not want to discuss it, but it is a complication in the overall system. Okay. I think I saw in your paper, yeah, I have been reading all the 2020 earthquake papers this week. And I think it was in your paper that I saw also that structure well described. And essentially, you're talking about the vertical gap between the Cyprus slab on the one hand and the Hellenic slab on the other hand.
Yeah.
And so my story does not include the gap, which indeed exists. I have no doubts since the work by De Boerder et al. And more recently Biriol. I think it's well established that the gap with the Cyprus slab exists. So that is separate from the system that I'm looking at here. Here I'm looking just as to the tearing of the Hellenic slab away from, let's say, the rest of Africa due to the step process and how that generates a lateral gap. So the way I have, I don't have enough hands to show. So this tearing happens here, but here no, sorry, this doesn't work. It's 2-3-dimensional.
Right.
If I had your 3D picture, which it was nice, had that handy, I could probably make it more clear. You know what I will do? Very likely, I will use your very nice starting picture and modify it to include the lateral edge here in that I mean. But sorry, I cannot explain it very well.
Okay. No problem. No problem.
Thank you very much. Any more questions from audience? But if you have time late in the afternoon, I'd like to invite you to the presentation of my student, now Dr. Judith Maria Confal's models on the tearing and slab and gap, and also to Meken's talk that we published recently. So thank you very much, Rob, once again. It was a very nice talk to cover all the questions. And Thanasis, do you have time right now just to start a few minutes earlier to your talk?
Yes, sure, I'm ready.
Because Andreas Fichtner is not able to join us. His mother is being taken to the hospital. I think he has to be with her. And there is no sign of Sylvain Barbot, although I have confirmed him last night and early this morning, but he couldn't make it. I don't know the reason why. Now we are back to the schedule as advertised. A few minutes earlier, we can continue with Ganas's talk.
Okay. Yes, no problem, Tunçay. Just I can start.
So
now.
You have more than 20 minutes, no worries.
No, it's okay. Okay, I respect my time, don't worry. Okay, thanks again for the invitation. Really a great initiative to you, Tunçay, and your colleagues in Istanbul Technical University. I think it was a real need to come together after 1 year and discuss what we found after this major event at the Aegean Sea, which, by the way, was the second largest event in terms of seismic energy release since 1999, since the Izmit earthquake, in August 1999 in the Aegean Sea. Right, so I will share my screen. Okay. Right. One moment, please. Okay. Right, for some reason. Okay, one moment. Sorry, Tunjai, I cannot find the PowerPoint.
No panic, no panic, we have time.
Why is that happening? Don't save that. Close other windows. Okay. Okay. I think I'm all right now. So can you see my screen now?
Yes, if you can share it now with the full screen.
Okay.
Perfect.
Okay, great. I apologize for the short delay. So the topic of my talk today will be about deformation, the strain patterns, and the fault model of the Samos earthquake, which occurred 1 year ago exactly. So this is a combined effort with my co-authors and colleagues from National Observatory of Athens and the École Normale Supérieure. In this talk, we identify the main source of the magnitude 7 earthquake. We use space geodesy observations of ground displacement as primary data to model the source by inverting then this data. We provide some information on the amount of post-seismic deformation, then we provide in-source evidence of earthquake-induced landslides and other effects. So the location of the earthquake, as already explained by Laurent and Rob, is in the middle of Barkak region of the Hellenic subduction system. And it's very nicely located above or in the middle of metamorphic core complexes to the east, the Menderes, and to the west, the Cyclades. So it's, let's say, a very interesting area to look at modern day process with respect to Miocene and late Miocene and Pliocene extensional processes in this respect. Right, so the Samos earthquake range in magnitude between 6.9 and 7.2 according to various data sets used in inversion models, and it occurred along a normal fault oriented east-west as indicated by the moment tensor solutions of both regional and teleseismic data. And the fault dips to the north, as we found from geodetic data. This map was shown already by Rob. What I would like to show here, of course, was the evidence of several historic events reaching 7. And one moment, yeah. So here, for example, this event is a particular interest, the 1955 event, 16th of July, magnitude 7, east of Samos. And then the 1904, and there were 2 events on the 11th of August and the 18th of August of 1904, magnitude 6.8 and 6. And of course, there is a large uncertainty on the location of these epicenters, but if you consider the amount of north-south extension and the slip rate of this major fault system here, perhaps one event every 6.5 to 6.8, even to 7 event every 100 years is capable to be produced in this half graben. Other fault system exists also to the north and to the west, but it doesn't seem to have produced such a large magnitude events near 7 as in this region. Notably, the bathymetry shows a deeper basin to the west of the 2020 epicenter on the main fault area, notably north of Ikaria and south of Chios. And this also map shows that when I plot the first 24-hour aftershocks, okay, I see most of seismicity is located south of the epicenter and to the east. And then there is a large gap for about 20-25 kilometers. And then the epicenters are located to the west or to the edge of the fault. So this clearly shows that the main fault slip occurred to the west of the epicenter, and basically a large area of the fault had ruptured and is now free of aftershocks. This picture of seismicity shows, for example, in panel B, you can see here the daily frequency of earthquakes with respect to east-west longitude, showing that this is the epicenter here, showing some gaps in the seismicity that persist in this area, for example, for 20 days, which shows that these parts of the fault plane get ruptured during the main shock. We processed immediately the first interferograms that were available from the Copernicus program from the European Space Agency. So the first results showed deformation onshore Samos, not so clear image with a lot of loss of coherence, but definitely shown at least 1, 2, 3, possibly 4 fringes of deformation onshore, with no deformation on the Turkish coast in Kusadasi and in the north of the epicenter, and also some deformation minor in Furni. So it was clear to us that this involved some uplift of the island because of the motion towards the satellite. So this Samos was on the footwall of the fault. Then we processed better with our time another interferogram that the best one was covering the period from 23rd of October until the 10th of November, including also some post-seismic part of it. And this interferogram, which is very nice, one of the best ones I've ever seen, shows clearly deformation comprising 1, 2, 3, 4, 5, almost 5 fringes of motion towards the satellite. This is an ascending orbit, so the satellite looks to the right. So all these fringes indicate motion towards the satellite. Deformation also affecting Furni. Again, no deformation on the Turkish coast, Chios, and on the other side, onto the east. I'm going to show you later the profile here. I drew a profile with the displacement profile with the fault model that was produced on this data. So the major picture we get from this event is that all the Samos was uplifted, with exception of this coastal strip here from Agios Konstantinos, which is a village, coastal village, until Kokari, which is a famous touristic location here, that showed motion away, few fringes away. It was really hard. We had a really hard time to explain this, and eventually we could not explain this using a fault model, a uniform slip model for the main shock. We had to assume some rupture complexity near the upper part of the fault surface. Right. So for both tracks, for the ascending track 29 and the descending track 36, you see that the fit between the observations and the model is good, with the exception in the area near the Agios Konstantinos and Kokari, which is really a local effect and could not be explained by a landslide. Because I went in the area and I walked over this place trying to find evidence for landslide. I could not find any major landslide in this place. So it's really part of the rupture, but we could not model that. And this is the line I mentioned before. It's a 20-kilometer long profile on the Western Samos showing the data, which is the dashed line here, and the model, which I'm going to show you in a few moments. So the fit is quite good. The second data set we used was GNSS. And the GNSS data, the main data set, it comes from 2 stations onshore Samos. The first station, those are both from private companies. I would like to take the opportunity to thank the private companies for sharing the data with research institutes and the academia. So the one station in the East Samos, in Vathi, which is the capital of Samos, showed motion, permanent uplift, slight motion to the west, and larger motion to the south. Okay, this is the time of the earthquake is here. And the second station, which is located in West Samos, in Karlovasi, showing largest motions, an uplift of about 8 centimeters, permanently uplift. And then a permanent, displacement to the west and further permanent displacement to the south. This displacement here is about 36 centimeters co-seismic. Some post-seismic motion is included, and then you can see clearly there's a post-seismic signal that dies out about 1 month after the earthquake, on the 1st of December, 2020. The overall picture is amazing. You can see displacements recorded at a distance of about 100 kilometers from the epicenter, 120 kilometers in Kalymnos. And of course, we have displacements of the order of a few centimeters in Chios, Chesme, Izmir, in the Izmir station, which is southwest of the town of Izmir. And large motions, horizontal motions that are recorded, that were measured across strike, and keep that into your mind. Okay, largest motions across strike than along strike. For example, this station Samu is located a bit off, but it's along strike, the fault, and also Aydin here, and other stations in the Cyclades to the west. So largest motions, a few centimeters of permanent offsets, indicating north-south extension along this major half graben of the Aegean Sea. We use this data to invert. We used 99 INSAR displacement points and 14 sets of GNSS offsets, assuming very simple half space elastic model and uniform slip. So to show you what we did is we picked the phase. This is wrapped phase of INSAR, both ascending, track 29 and track 36. Those are, we picked the values, those are millimeters. So 28 millimeters of displacement over the satellite, increasing towards the Karlova Sea area, which is 14 centimeters here. And the zero displacement line is on the Turkish coast. And on the descending interferogram, we could not pick data in the main part because of loss of coherence, but we were able to pick the 28 millimeter contour here, then zero line in Bathi. So with this data set, we inverted jointly and we obtained this fault model here, outlined in black, which is about 40 kilometers in length and 15 kilometers of width. This model, which now I show you a synthetic interferogram, that resulted from this, fits nicely the GNSS. We gave more weight to the GNSS. In black is the model, in white is the actual observations, with some discrepancies towards Ikaria, but the rest of the data fits. It's very nice. So I show you some statistics of the inversion. It's about 5,000 runs. So the convergence is about, this is degrees anti-clockwise from north-south. So it's about the strike, 276, almost east-west. Here you see the top fault is about 600 meters from the surface. It's very, very almost on the seashore. This is the length of the fault, about 40 kilometers. Here is the width, about 15 kilometers. And there is the uniform slip is about 1.7 meters. So the fault model I show you here. This fault model has an overall RMS error of 13 millimeters. It's much better than the one we published soon after the earthquake in the tabular website. And we were better constrained the depth to the top fault, which is 600 meters, which is very important for the tsunami that followed the earthquake. And some other statistics I give here about the fit to the observations. What I found also interesting in this earthquake, it's very, very nice signal of post-seismic deformation. And this is something that really comes up because we have now new data, new GNSS data all over the world, reliable data. We can catch this amount of deformation not following the main shock. So here I show you the post-seismic deformation, focusing on the day after the earthquake, which is here until there's no motion on the station in Samo. Samo is in Karlova Sea, which is Western Samos. So here you can see that there is a fast part and a slow part on the post-seismic motion. The fast part ends on somewhere over here on the 11th of November. And then there is a slow part until the 1st of December that we faithfully see. So it's 1 month of the station was moving 1 month. This is the north-south component. So the station was moving to the south another 4 centimeters approximately. Okay. 4 centimeters of post-seismic motion in the north-south direction, which we could not be able to measure that without GNSS. And then also we picked up uplift on the footwall, okay, which is another important piece of evidence that on normal faults, there is a contribution also of post-seismic uplift, not only co-seismic uplift, but also post-seismic uplift. And we were able to measure this as about between 20 and 30% of co-seismic motion was the post-seismic uplift. And here I drew a cross-section. So this is the fault, the model fault. This is the model, and this is the data. So this is the model co-seismic motion on the vertical. And here I have the data, and then I have above that data, I have the post-seismic, the blue point here. That's very nice results. I really like that, showing that one of the few cases we can measure post-seismic uplift of the footwall. Another observation that came out of this earthquake, we learned so many things of this earthquake. One important observation was that when you scale the data, the GNSS offsets, this is a formula I published in a journal back in the Bulletin of Geology of Greece, 2018. So here I scale the displacement, the P ground displacement, this is square displacement versus distance with earthquake magnitude, okay? I see that our data, this is a station in Samos, Western Samos, this is Middle Samos, 0938, this is Chesme, this is Chios, okay? Those fall very nicely in the 7 magnitude line, okay? With respect with distance, about 100 kilometers here. But when you look at stations that are located like SAM-U or the stations here in Didim or Aydin, which are located along strike, they are corresponding to displacements further less in magnitude, which means that the energy was attenuated, okay, along strike than across strike. So I think this is important when people try to scale GNSS data displacements with earthquake magnitudes, for example, in tsunami warning cases, right? In Indonesia or in Japan or in California, when we have plate boundary faults, okay? They should be careful what data should use if they want to quickly may have an estimate of the earthquake magnitude, because in normal faults and in thrust faults, again, the stations that are located across strike are better recording the seismic energy than stations located along strike. I'm going to show you some secondary effects also, which I think is important. So here is an overall map, Samos with geology, showing some liquefaction. We mapped with the blue dots here, liquefaction here and here. We have port damages, we have landslides all over. We have cracks. And this area here is what I will show you in a moment. We identified a large area of deep-seated landslide affecting almost all the basin here that is located in this color in the Miocene-Pliocene basin of Karlovac. This is bedrock, of course. The blue colors more or less is bedrock, and light colors are the new sediments. So this we identified that using INSAR, okay? So some of the effects I show you here, the liquefaction places in this area, okay? right? All this coastal side was liquefied. And also the land, here I myself studying on the coastline that subsided half a meter in this area here. The fault edge is somewhere over here in Kokari. Right, so going back to the place where we had this deep sea landslide, okay, here using INSAR data, what we basically have is we have loss of coherence in this area, but in the boundaries, we're able to, when we unwrap the face, we're able to measure opposing motions. So here in this east-west component that we obtain from INSAR data, we see this part of the basin moving east, and the blue color on that other part of the basin moving west. So it is phenomenal, the amount of area. You can see the scale here is 2 kilometers, this bar, okay? That was activated, gravitationally moved towards, overall towards the north-northwest because of the earthquake. And the effects on the ground were the cracks we mapped on the asphalt, this area here. Of course, on the other side. And that's another example a bit further south, also with an explanation what caused this sliding surface, the weak interface between two beds of Miocene and the Pliocene cap. Right. I don't know if we have time to show the tsunami. Tunkai, we have yes. 1 minute. Yeah.
A few minutes, yes.
Right. 1 moment. This is exactly 1 minute. 1 minute after the earthquake. Or see these cars here that are already below the water. So the sea. This is the port of Vathi on the east Samos. 1 to 5 minutes after the earthquake. It's the first wave. So in this, we see now that the sea has retreated. So we are now a few minutes later. So the sea came in and now the sea goes out. Okay. Sorry. All right. So summarize my talk now is that the fault that ruptured during the Samos earthquake is very close to the island. It is located 1.5 kilometers offshore, the port of Karlovasi, sorry, the western part of the Samos. That fault is, let's say, intermediate angle normal fault, 40 by 15 kilometers that dips towards the north with a 37-degree deep angle. It continues towards the west of Samos. The geodetic data show ground motion and crustal opening in the north-south direction and uplift of Samos in agreement with long-term geological data. we observed a fast post-seismic slip, including uplift ranging between 22 and 33% of the co-seismic slip value. And we attribute that to shallow after slip along the main fault. We think that post-seismic uplift is an important process that should be included in earthquake deformation studies. I would like to acknowledge the Sentinel satellite imagery, the ESA European Space Agency, the GNSS data from Greece, GNSS data from Turkey, and the Samos local authorities. Thank you very much.
Thank you very much, Thanasis. This is a nice talk for covering all the earlier and later studies of your models, and a very exciting one. I hope to receive a couple of comments, questions from the audience. Rob, Jiri, do you have any questions, Rob, please?
Yes, I do. Yes, I do.
Why not?
I know.
I saw Ciri Zahradnik also smiling, so maybe he wants to ask.
Yes, I have a question, of course. So may I?
Yes, please. Rob was first, I think.
Thanasis, I was greatly impressed by your 1 month post-seismic motion. Could you comment it perhaps from the viewpoint of the depth of creeping zone? Is it very shallow effect of something more regional? Up to which depth? How does it relate to creeping process in general?
Yeah, I think, thanks a lot for the question. I think this uplift is due to the afterslip along the main fault surface. So it's not something that is related to any secondary faults, because we don't have any data to model any branching of minor faulting on the upper part of the fault, on the fault rupture plane, because we measured the top of the rupture is 600 meters. So yes, it's very close to the surface. So if you concentrate afterslip there, it is possible to induce uplift after the main shock. So this, my best guess is that this post-seismic uplift is due to afterslip along the main rupture fault.
Okay, thank you.
Rob wants to ask a question.
Yes, please, Rob.
I liked your talk very much. Thank you very much for that.
Thank you.
I was thinking about your the post-seismic deformation that you saw through the geonetics observations. What percentage of that post-seismic was aseismic? Because obviously there was also aftershocks.
Yeah.
Did you look at that?
Yeah, you're right. That's an excellent question, by the way. Excellent question. I have a problem with the accuracy of the relocation of the aftershocks. In order to be able to fit the relocated aftershocks to the position of the fault plane. Because most of these aftershocks could be off-fault aftershocks. Not on fault. So, so the portion of the uplift, which part is aseismic and which part is seismic uplift, can be, let's say, can be determined if we have very good data from seismology. Unfortunately, these data were not available because in Samos, we had only one station from the NOAA network that was not working during the earthquake. Yeah. And then it was out of order because of a lightning that destroyed the power. So it was there, and we installed two portable stations 3 days later, one in East Samos, one in West Samos, but only with two stations. And then the stations from Turkey in the north, which is still far away, it's still 20, 30 kilometers away. We cannot have the accuracy that I I would be confident with to say to you, Rob, that from these 100 aftershocks, because we have errors less than 300 meters, 200 meters in location errors, then from these, as an example, from these 100 aftershocks, the 50 of those are on fault, so the uplift is seismic, and the 51s are off. So that's why I cannot answer your question.
Yeah.
Okay.
Yeah. Thank you.
It's lack of data. Basically, we did not have that good seismological data to be able to answer those very important questions.
Thank you very much for nice presentations and discussions and comments. And the only problem is that we don't have enough time. And Thanasis is lacks of time because he can't catch the earthquakes, write the papers, comments, and the follow-up. He needs 48 hours a day, because he cannot catch the talks. Now, that discussion brings us to an excellent talk by Jiří Zahradník about the Aegean earthquakes and their model to tackle. And so I hope you are ready, Jiří. Please.
Yes, I am.
Thank you.
So I will share my screen. So good afternoon to everybody. This talk comes from Charles University in Prague, Czech Republic, and the first author is František Galovič. Professor Galovič unfortunately cannot be present today, so I am the presenter. My name is Jiří Zahradník. First of all, Professor Taimas, I would like to thank you very much for the initiative making this conference and inviting us. So in this first slide, I would like to briefly mention our activities in Eastern Mediterranean during the last 15 years. It is an introductory slide just to showing earthquakes we were dealing with. In all of them, trying to go a bit beyond standard seismic routine, beyond point source analysis in two directions. That first of all, we developed new codes for kinematic and dynamic slip inversions and concentrated on finite extent sources using broadband ground motions. I mean, including broadband stations and also strong motion stations and GPS if possible. Also, roughly same age, 50 years, is the age of our software Isola, and younger are softwares for slip inversion developed by František Galovič. My first example will deal with this Samos earthquake, which is topic of the conference. It is from our paper still under review, joint work with the Aristotle University of Thessaloniki and University of Patras and Prague, of course, also. You know the situation already. And here I would like to present our current status of the method. What are we doing? So we usually, as in this model situation, start from low frequencies. And in very low frequencies, we investigate the centroid moment tensor by our software Isola. In this case, this centroid is placed here, slightly north to the relative to the global centroid moment tensor, but having practically the same nodal lines. Then we increase frequency, and this allows us to investigate more the source complexity. In this case, we reveal 3 sub-events following each other with increasing time and slightly changing focal mechanism. And thus we suppose, or we have a strong indication of the rupture propagation towards the west. And this is our basis for the finite extent model. And the finite model then is solved by Lin slip inversion code and provides final slip like this. This example is the inversion from seismic data, from regional seismic data at the stations shown, but here the GPS data were not used. For that reason, you see that blue arrows showing GPS data are not fitted by this model. However, if including GPS measurements, look here now, not only seismic data are very well fitted, but also the GPS data. And the change in the slip model is relatively small. In a way, very important because it indicates this shallow slip close to the Samos Island. This is the example of standard snapshots from the slip inversion showing development of the slip rate. This is final slip. This is time function, showing that roughly the same can be also obtained from simpler modeling. And this is something which was slightly maybe overlooked in previous studies. There are so many already papers about Samos earthquake, but without this investigation, we added a new method for inversion of apparent source time function by empirical green function method. And we have shown that clearly this suggests or supports the directivity to the west, as shown also here by very good fit of the duration of apparent source time function with its standard azimuthal distribution. So it was about our, let's say, more classical methods. And now I would like to proceed to more, let's say, complex or sophisticated methods dealing with dynamic slip inversion. And this dynamic slip inversion will be presented based on paper which has been already published. The first author, František Galovič, publication in Communication of Earth and Environment, joint effort with colleagues from Greece and also from Turkey. You know the situation. So we are in 2020 on the East Anatolian Fault, Elazig earthquake, magnitude 6.8. And our first approach is multiple point source inversion using Isola software. Green star is the epicenter. And the software provides us not only just one focal mechanism, but so-called 3 sub-events. First sub-event is here. The fact that it is the first is reflected by its color. This color here shows early time. Then slightly later, we have major rupture here, close to epicenter. And even more, even later, latest is the smallest sub-event shown by this color. So the difference is between 8 and 18 seconds, roughly between these. You do not see 3 circles, although I'm talking about 3 sub-events because each of them is uncertain. So these numerous circles show the uncertainty of position of the sub-events. And equally well, you can see here that we have numerous nodal planes. This is uncertainty of the focal mechanism, the largest for this. By the way, this is a bit overlooked feature because most of these source models, finite extents models, usually are working with just a single plane on which there is a single focal mechanism, but these variations in certain cases might be quite important. Anyway, all over we see rupture propagation towards southwest. Now let's deal with this effect in more detail. And we investigated one very interesting feature. It is 2P onsets. In several stations, we were able to identify one very small, but very clear relative to noise, first onset and second onset with different distance, I mean temporal distance between the 2 onsets at different stations, from which it was possible to locate relatively one with respect to the other. So we have something funny, maybe, to hypocenters, and I'm going to show why and explain this very interesting dynamic feature of the event. Of course, we were unsure in the beginning, so we obtained good confirmation of these two hypocenters also from back projection by Evangelidis and Fountoulakis from NOAA, who are co-authors of this study. So actually, their back projection identified beginning of the motion here in hypocenter, then propagation to H prime, and then propagation to this southern part to the southwest. So we have confirmation and now should explain. And this is just the newest part of my talk, firstly developed, first of all, led by Professor Galovic and his students and colleagues. So the basic feature of the dynamic source simulation is a prescription or assumption about friction law. Here in this case, we use the simplest friction law. It is the standard slip weakening law. We have some distribution of parameters of this friction law, so we can solve forward problem, dynamic simulation of the rupture evolution. We have slip rate, and can compare with seismograms. In reality, we are interested in the inverse problem, so we have observed data and try to invert them back on the fault plane and to obtain not only slip, but also these dynamic parameters. Why? Motivation is clear because we believe that such a dynamic simulation is more physics-based. In this sense, it is much better than standard kinematic inversion, which has no this clear physics base. It is not dealing directly with mechanism of the rupture creation. Of course, doing dynamic simulation is much more difficult than kinematic in two respects. First of all, we lose linearity process. I mean, relation between model parameters and the data is no more linear. So we cannot use the least squares method. We must use general optimization techniques like Monte Carlo. And this is why also the method is very expensive. I mean, time consuming, you will see later. It needs dynamic solver to be fast with some new fast methods. How the method is parameterized? In this case, František Galovic is using this parameterization of the slip weakening law with three parameters. We have friction drop, which is here. We have characteristic slip weakening distance, which is here, and we have initial stress. These parameters are not homogeneous, they are not constant, they are heterogeneous over the fault and are the subject of the inversion. As I said, it needs a fast solver. Fortunately, one of students of Galovic, Jan Premus, has developed such a fast dynamic rupture simulation solver, fourth order finite difference method. The rest of propagation of seismic wave from the source region to the stations is made in a more traditional way in 1D models using discrete wave number method and code etc. Very importantly, this method is constructed in framework of Bayesian methods, probability distributions can be obtained. So we assume certain data variance. We have certain prior information, for example, about non-negative friction drop. And in that way, we are able to get something like schematically shown here in the right-hand side. We can get samples of the Monte Carlo Markov chain parallel tempering. So we get some discrete representation of the probability density function. Of course, we meet also difficulties in practice. We have to start with kinematic inversion, make some manual interventions to improve the fit, etc., etc. And still, we must fight, even having such a fast solver, we must count with very long computing time because there are millions of repetitions of the forward simulation. So a single dynamic simulation requires something like 3 weeks, although it uses acceleration using graphical cards. This is example of a waveform fit, quite satisfactory. In near station, František was able to go up to frequency 0.3 Hertz, you can see here. At a more distant station, we were able to go to frequencies 0.15 Hertz. And here, this is the maximum a posteriori model, the best fitting model. You can see that we obtain not only slip distribution on the fault. Be careful, please. Here, northeast is here on the left part. Here we have these two hypocenters, which I mentioned, H prime, and this is southwestern part of the Elazig earthquake fault. We have also rupture speed. Please note quite large spatial heterogeneity of the rupture speed, locally even super shear. Also quite heterogeneous over fault is initial stress and stress drop. This DC is even more complicated. Thanks to Bayesian formulation, we have also uncertainty estimate. So we do not have only the best fitting solution. If I talk, for example, about mean slip over all realizations of this method, we have also some two standard deviations. So you can see uncertainty of the slip. You see that locally uncertainty is quite large, maybe of the order of 2 meters, but only locally. On the other hand, mean stress drop has much larger variation or uncertainty as expected. We have histograms also thanks to Bayesian formulation. You see that overall variance reduction fit of seismograms is quite good, between 60–70%. For example, mean stress drop varies between 10 and 14 megapascals. And this is one of the interesting pictures. You will see something interesting in the first stage. You see this H and H prime I mentioned before. Those are the two hypocenters. And now the earthquake started and it is almost dying. There is practically no, and now after it went to H prime, something new happened and the rupture is going in opposite direction to the southwest, according to the right-hand plot showing time. So this was just this initial part of rupture and its dynamics which attracted most of our attention. So we included several additional experiments, and one of these experiments is briefly described here. What we did is that we reduced the initial stress in the topmost 12 kilometers. And do you know what happened? What happened? It was really very interesting because we obtained something like the initial stage of Elazig earthquake. We obtained just an earthquake of magnitude 5.8, which failed to further develop into 6.5 or something like this. So I'm explaining this because for me, it is one of the most exciting features of Galovich's calculations. It is the situation which throws light on the nucleation of the event. And it shows how sensitive the nucleation of large earthquake is to heterogeneity in the initial stress. It is possible just with small manipulation in this initial stress to stop earthquake, not to let it propagate into big one. And I think, or we think, that this was just the situation in the interseismic period. Because if you look at the Eastern Anatolian fault and you see this seismic gap where the main shock has occurred, you see that this was not complete gap. There were many earthquakes, but all of low magnitude. Those are magnitude larger than for earthquake from ISC catalog since 1964. So you see something like 10 events or so. But none of them has developed into big earthquake rupturing all this gap. And we believe that our previous dynamic simulation gives an explanation. We believe that the initial part of Elazig rupture resembles each of these events, but these events were developing that they could not grow up into big 6 or 7, 6.6, 6.8 earthquake. So this is what can be obtained from dynamic simulations. And we can, of course, continue in this study. All the time we are interested in this exciting Eastern Mediterranean region, even for future. The main goal of the group led by Galovic is, of course, to use even more sophisticated friction laws, including gradient state. And why? The reason is clear, because this is also why I was so much interested in results of Thanasis Ganas in joint interpretation of co-seismic and post-seismic data in a single joint inversion. And naturally, there are also many other applications of dynamic modeling because we are able also to go to, let's say, improvement of predictions of future ground motion, making scenarios with this dynamic modeling, and thus contribute to earthquake hazard assessment. So that's all. Thank you very much again for your kind attention, and again, thanks for your invitation.
Thank you very much, Jiří. That's exciting questions and for a good summary of your groups and Galovic's groups work so far. So we may have questions, Thanasis and other participants, but we do have also alternative papers. Probably you have seen on the Eastern Autonomous Fault Zone earthquake and the Elazığ one. We published in Tectonic Physics. Jiří, I don't know whether you have seen it or not, because we did also see similar features from back projection, INSAR modeling, and seismology. I will send you the details, but you'll see the movies and animations we have confirming your results. And from the same kinematic point of view of a planar fault, it's a southwesterly direction. And with that experience, we are, with my group, we are also working on the kinematic and dynamic modeling of the Samos earthquake. So if you have time, we can discuss further. And I look forward to seeing your submitted paper under review. But it's with today's clusters of computers, it's the way to go from kinematic to 3D dynamic modeling is still possible. It's expensive for CPU time, but Thanasis, do you have any point to raise, or we are already familiar with Jiří's outstanding contribution to the seismology and the tectonics, but he may be more experienced with the numerical aspects of the seismology and the modeling problems we face nowadays.
And less experience in tectonics, of course.
Of course. Yeah, but this is the reason why we have sharing our experience.
Why we must cooperate.
Tectonics, field geology, space geodesy, tectonogeophysical, geodetic seismology, I would say, and rock covers, numerical modeling, and this is the meaning of science for the love of science. I assume this is my personal opinion, but we have quick questions. Rob, I see you are standing up. We've been sitting all day, nearly 10 hours.
Yes. I have no question at the time. I thought it was a great presentation, yes. And I look forward to your further work.
I look forward to meeting you, Jiří, in person as well. Life is short, but we never made a chance to meet each other and face to face, but with you, Rob, as well. So, but anyway, so we'll see how it goes. Thank you very much.
Sorry, I have a quick question for Jiří. Okay. Actually.
Yes, please.
Yes, Jiří, nice. It was a nice results. I mean, you showed. I was just wondering whether you only from Isola solutions, did you get any indication of this initial stage of this earthquake?
What? Of what?
So did you get any indication of this initial stage earthquake from the Isola solutions only, without going further immersions?
Yeah, I showed you that it is a solution for, we talk about Elazığ earthquake, yes?
Yes.
Yeah, I would say that the first sub-event, which was located towards northeast from the epicenter, was just that.
Okay.
But what do you think? What was the reason it failed to grow a larger earthquake? What is the kinematic or dynamic or physical criteria you may think that stopped?
Yeah, so those are two different questions. For example, first I finished the first one. So question was whether in Isola we see something like this preparatory phase between hypocenter H and second hypocenter H prime. I said yes, maybe it is probably a sub-event of Isola solution. Second question, Professor Taimas, what was your question?
So, I mean, just to clarify the doubt in our minds, what do you think it is the reason to stop developing a large earthquake magnitude larger than 5.8? What are the physical or dynamic or kinematic or geodynamic, I don't know, any parameter, any physical explanation in your mind that stopped developing a larger event? Yes, what do you see as far as the numerical modeling is concerned?
Yes. Initial stress, I would say. It was initial stress and it was heterogeneity of the initial stress, because if we simply reduce the initial stress, it does not develop into strong event.
What is the number in initial stress in megapascal, for instance? Normal initial stress, how big?
I don't know exactly the number. I don't remember it. I should look in the paper
I can. No problem. That's a technical detail.
I don't know. I don't remember the exact number.
Yeah, I am having the similar difficulties in modeling the Samos earthquakes.
But it was really low. It was 10%. Yes. I don't know how much in absolute numbers, but 10% is nothing, and 10% can stop earthquake from developing into damaging one.
Yeah, but these small details matters. The Ghana stasis was after small, subsidence on the Karloas in this, it's a couple of kilometer square area. What's happening? It's going down, the others is going up. So these small, fine details matters much to my mind.
Of course, it explains why we still have such a big difficulties in predicting earthquake.
Yeah, to challenge science.
We can never get such details, even from measurements in the depth.
Okay, thank you very much for the whole participation. So we have to go
Professor
for a quick
Taimas,
break.
Yeah, I have a comment.
Yes, please.
I have a comment on Professor Zahadnik's presentation. I confirm the Westward directivity of the main shock based on GNSS data we processed for Samos.
You mean Samos?
Yes, Samos.
What's the percentage whole series of south or east-wester? I don't know.
Yeah, we looked at the data, the high rate data. These have not been published yet. And the amplitude of the displacement waveforms for stations located to the west is larger than the ones to the east. So the rupture goes directly to the west.
Yeah,
that's the result from the GNSS.
So it confirms our observations as well. So
thank
you very much.
Thank you.
For this nice presentation and discussion. Now I give the chair to Oğuz Çelik for the next civil engineering talk. Please, Oğuz.
Okay, thank you, Tuncay, for handing over me this session. So the next speaker is Professor Michel Bruno. He's a SUNY State University of New York distinguished professor at the Department of Civil Structural and Environmental Engineering. He was actually a former director of Structural Engineering and Earthquake and Simulation Laboratory, and also the former MCER, the deputy director and also director for a long time. So his research topics include earthquake-resistant design, blast-resistant design, multi-hazard engineering, dynamic response of structures, seismic evaluation and retrofit of steel bridges and steel buildings, seismic evaluation and retrofit of unreinforced masonry buildings, ultimate behavior of steel, metal, and advanced composite structures, behavior of guide towers, cable structures, long span and tall structures. So he has also some awards and honors, very latest ones, 2020 AIAC Special Achievement Award,
2019 AIST's Lifetime Achievement Award, 2019 Fellow of Structural Engineering Institute, and also many awards from ASCs, American Society of Civil Engineers, including Mosef Award and George Winter Award. So I would like to invite Professor Bruno for his speech on resilient buildings from a post-Christchurch earthquake perspective. Yes, Michel. Thank you.
Thank you. Good morning. Well, not good morning. Good morning for me, but good probably afternoon for you.
Good afternoon.
Yes.
Thank you.
Okay.
And it's nice to see you again. Thank you.
Nice to see you again as well. So thanks for the invitation. It's a pleasure to be here this morning/afternoon to talk to you about resilient buildings from a post-Christchurch earthquake perspective. So because it says Christchurch in the title slide, let's dive into it. There were many earthquakes in Christchurch, in the Christchurch vicinity, starting in 2010, for example. There was a bigger 7.1 magnitude earthquake that occurred, but it was quite farther away from Christchurch. So the earthquake I'm talking about is the smaller one, magnitude 6.3, because it occurred 5 miles from the central business district of Christchurch, which is this yellow box right here. And because of that, it did a lot more damage to the city. So I'll start this presentation, very short presentation this morning, with an experiment. This is an aerial photograph of Christchurch taken about 2 weeks before the magnitude 6.3 earthquake. And the name of the game is you pick one building, you keep your eyes on that building, and I will move from that picture to 3 days after the earthquake on this picture. And I'm willing to bet that chances are the building that you selected 2 weeks prior to the earthquake is still there. There's a change in the angle of the picture and there's different light conditions, but the building is probably there unless you were very lucky and you picked the 2 buildings that collapsed in the central business district and that were responsible for most of the casualties, not all, but most of the casualties during this earthquake. You could have picked other buildings that suffered a tremendous amount of damage, such as the Grand Chancellor Hotel, who suffered tremendous damage to its shear walls and was in fact leaning precariously towards the street, or the Forsyth Bar building, which looked fine, but lost its staircases for 13 stories, and so people had to become creative to find ways to exit the building. But other than that, the city looked pretty much the same after the earthquake than it did before the earthquake from the perspective of an aerial photograph. Now, the next step in this game is instead of looking at one building, take a global view of the central business district overall. And now we're going to move from 3 days after the earthquake to 14 months after the earthquake. And now there is a visible difference. In fact, if anything, Christchurch is turning into a giant parking lot because there has been more than 1,000 buildings demolished in the Christchurch area after the earthquake because they were deemed to have too much damage to be worth repairing or demolished for a number of other reasons. And therefore, the consequence of the earthquake is not so much the collapse of buildings, but the fact that so many buildings had to be demolished after the earthquake and are in the process of being reconstructed. And the reason this happened is because building codes are designed on a life safety perspective. And we can make a car analogy with life safety. The way cars are designed is pretty much what you see on the left here, where during an accident, a frontal accident, the front of the car is a cripple zone. It dissipates the energy of the accident. And then the occupant, together with an airbag and other safety devices, will be able to remain alive and survive the accident. And the buildings we design for earthquakes are pretty much designed the same way with a life safety perspective. But the owners of these buildings sometimes think that these buildings are designed to survive earthquakes. Just like if you would do the car analogy, the building owners would think that the car that they are purchasing are the cars on the right. So that, of course, creates a problem because during an earthquake, we do not get one car in an accident. We get everybody getting into an accident at the same time. So this is more like a massive pileup of cars being destroyed. And this explains essentially what we see following the Christchurch earthquake, where we had so many damaged buildings and so many of them were demolished. Now, the Christchurch is in the nearing the end of a reconstruction phase that has lasted more than 10 years. And so in 2007, Greg McRae and I did a study talking to all of the engineers, well, almost all of the engineers that were designing the buildings that were replacing these demolished buildings and that were essentially implemented in Christchurch as part of their reconstruction. And so this is an interesting document that you can download for free, either from that very long website that is shown right here, or you can just, if it's easier to remember, just type my first name, last name.com, and there's a place to navigate and download this document. And it's good bedtime reading, because what we can see in there is that from the perspective of the tenants or the developers or the architects and even the engineers, the concept of business continuity and repairability was not even on the list of priorities prior to the earthquake. When people were designing, they were designing per code in accordance to life safety. And most of the new buildings that were built before the earthquake typically were reinforced concrete structures. That was essentially the culture, and that's how things were done. Now, after the earthquake, of course, business continuity and repairability moved up tremendously on the list of priorities, and became very important. And so during the reconstruction, many were thinking about that, but many were also thinking about the the media coverage that was constant about these buildings that were damaged, that were leaning, that had to be demolished, that were deemed to be non-repairable. And so even though when you talk to the engineers, they felt that every building behaved exactly as they expected, except the two that collapsed, which were of an older vintage, but every other building designed to comply with the current code did exactly what they were supposed to do. They provided life safety. And that was not a surprise to the engineers overall, but it was a major surprise to the public. They did not expect that at all. So when you read this report, you will notice that there's no one-size-fits-all solution in the reconstruction of Christchurch. Although some had predicted that maybe one type of structural system like base isolation would become overwhelming in the reconstruction, that's not the case. There's a large variety of different structural engineering systems being used as part of this reconstruction. But one thing that changed in a major way is that most of the reconstruction now is of steel construction, various structural systems in steel, but still mostly steel-dominated structural construction for designing the lateral load resisting systems, which is surprising because, as I said before, Christchurch was a concrete town. And let me illustrate this. This is a parking garage. It was there prior to the earthquake. It was designed using a system that is called eccentrically braced frames, in which the energy dissipation during the earthquake is supposed to take place in the central link of the system. And there was a lot of them in this garage. There was a tremendous amount of redundancy, but a few of them failed in a brittle manner, as you can see here. Now, there's a paper that has been published that can explain why this fails, and I don't want to get into that today. It's a little bit too technical. But the point I want to make is that to repair this building, what was done is that the frame was cut essentially. Parts of the frame were cut at various locations, and you can see the welds behind the red lines that I am making right now, because the part was essentially taken out, replaced with a new part, and welded back together. So it was a fairly rapid repair, and the parking garage was back in service after only a few months. So that raises an interesting question, because when we talk about resilience, we're talking about rapid return to service. And some structural systems have been designed in recent years to facilitate rapid return to service. For example, some engineers have designed a system where the links are bolted with the intent that they would be easier to replace. And when we asked the engineers in Christchurch whether they would prefer to use these replaceable links or the ones that are shown here, which are incidentally two pictures of new buildings being constructed in Christchurch following the earthquake, the opinions were split because some engineers felt that even without the replaceable link, as shown by the example on the previous slide, it was not that difficult to replace a piece of steel from an existing structural system. And that was in contrast to the challenges in repairing a reinforced concrete building, which is a lot more complicated than that. And that is in part why Christchurch is being reconstructed to a large degree with structural steel frames for lateral load resisting systems. So having said that, talking to structural engineers, we've been talking about structural fuses for decades where we have used the yielding element as the replaceable part. But to really talk about a structural fuse, it's not only just the fact that it's a sacrificial element, but it should also be replaceable fast, because the analogy with the fuse would only be complete if we can return to service rapidly, therefore being more resilient. And so to illustrate what a structural fuse concept is when we want to think about removing and reinstating fast, we, about 15 years ago, decided to try using buckling restrained braces in frames to see how fast we could replace them following an earthquake. And to make sure they would be easily replaceable, we left a gap in the gusset because the angle here that starts at 90 degrees, oops, not a straight line, but will eventually change the angle during the earthquake excitation as the column moves back and forth. And so we need to not damage the gusset to ensure rapid replaceability of the BRBs there. So, get out of this pointer. Okay, pointer does not allow me to start the video on the left, which is awkward. But in any event, this is the shake table test of this structural system. There's not much you can see in a buckling restraint brace because all of the yielding takes place inside that yellow encasement that you see here. But if we go and take a look at the replacement scheme, which is what we really wanted to test after these buckling restraint braces have yielded tremendously, we wanted to take them out, put a new set in there, and retest the structure. Now, the reason we're removing the so-called floors here is because this is a scale test at a 1/3 scale of the real building. And we do not have 1/3 scale technicians in our lab. So for them to be able to work standing up, they had to remove some of these masses there that looked like floors. But in reality, these buckling restraint braces would be replaced without removing anything but the buckling restraint braces. Now, thinking about resiliency, these buckling braces don't necessarily have to be replaced. And we have a project coming up in a few months where we're going to be testing them repeatedly for multiple earthquake excitation to demonstrate that the equations that have been developed for low cycle fatigue calculation for these BRBs are valid, or are they valid? But we think they will be. And so that's why we'll do the repeated tests. And therefore, they can be left in place even following an earthquake. Now, thinking of other structural fuse systems, a lot of work has been done by many researchers across the world on self-centering systems that use essentially a post-tensioning scheme to bring a structure back to its original position. And then we can replace the fuse quite easily with that. So this is an example of that using a steel plate shear wall, where the plate is the energy dissipating system. So if we take this detail here where the flange of the beam is touching the column on both sides, but is beveled at an angle so that it does not touch when it rocks. When the angle between the column and the beam change, there will be no contact at the bottom flange. And we introduce this post-tensioning element at the bottom, and this is how it's implemented in the lab. So we essentially have the post-tensioning element, the beveled beam, and we constructed a 3-story steel plate shear wall specimen to validate this solution. There again are 3 floors because we're going to put that on the shake table. There's some interesting detailing that has to be done, for example, at the column base. So if we want this to truly recenter, we have to make sure that there will not be a plastic hinge at the bottom that will produce permanent inelastic deformation. But once all of that is said and done, we can cycle the system back and forth to verify that the hysteretic behavior will be exactly what we will want it to be before we put it on the shake table. And the plates get damaged because that's the intent of these plates, to be sacrificial. So during the actual cyclic test that you saw there, we can take a view at the upper movie on the upper left corner, and you can see the open and the closing of the gap there where the beam is connecting to the column that pushes back the structure and recenters it during these cyclic loading cases there. So now we're going to put this on the shake table, and this is a frontal view of the 3-story self-centering steel plate shear wall. And from the front, you can't really see the damage that takes place in the wall, but you can certainly see that it comes back plumb pretty much through the excitation. And let's take a look at the side view where you can see a little bit more how this plate is yielding. This is a very thin plate, so it yields in tension, but it buckles in compression. And so it will yield as a diagonal tension in alternating directions during the earthquake. And that would be the structural fuse, the structural element that would have to be replaced following the earthquake. So this is just a couple of examples among many, many, many structural systems that can be used to achieve resilience, to mean either rapid return to service by having recentering, as was the case here for the steel plate shear wall. As you can see, after the earthquake, they all came back pretty much to a 0 initial position. And this was a test for 140% of the design basis, by the way. So we really pushed that wall quite far. And but there's other techniques, again, as I said, that can be used. So in conclusion, there's a lot that could be said on this topic, but in the limited time today, I wanted to highlight that the post-Christchurch earthquake reconstruction provides a very interesting example where steel structures were deemed to be more desirable and seismically resilient. That the structural engineers, we have a critical role to play to provide all kinds of solutions to enhance the resilience of infrastructure against extreme events. And there's more than one way to do this. And replaceable structural fuses and self-centering systems are just 2 examples of those that I've shown this morning that can help achieve this objective. The slides that I have used today have shown experiments from the graduate students that are listed here, as well as the sponsors that have made this research possible. None of what I have presented would have been possible without having had the pleasure to work with these graduate students. And so I thank you very much for your time.
Okay, thank you, Professor Bruno, and also thanks for being with us on an early Saturday morning for you. So that was a very interesting speech, actually. I mean, summarizing everything about seismic resistant design for especially steel buildings and the construction types used in reconstruction and in Christchurch, including some tests actually you've done before. So do we have any questions for Professor Bruno from the Zoom participants, also from YouTube followers? Let me quickly check if there's any question from the, maybe I should start with, okay, yes, Jerry, it's your turn. Okay, good morning again.
Hello. Yeah, Michelle, you talked about the sum, and I wanted to see if you could provide more insight. I mean, early on after Christchurch, it looked like this was really going to be a major opportunity to have structures with replaceable fuses and other innovations in so much of what they were designing, both for steel and for composite. And this seemed to dissipate significantly as time went on. I was wondering if you had that impression and if you had had enough discussions to understand where some of the real pressures were. Was it coming from the contractors? Was it coming from the designers? Were the design codes inadequate? What can we do to address this?
Thank you, Jerry. For good morning to you too. Another brave soul early on a Saturday morning.
Yeah.
So this is a very good question. And one thing the report does is that we ask every engineer for, New Zealand, okay, it's early in the morning here. Let me try to get my ideas clear. We talked to engineers and they were candid enough to tell us what happened for every one of the building projects. So we were able to tell them for each of the project, what was the driving factor that led to the decision for using the specific structural system. And then for all of the 75 buildings that we had in our database there that we had interviews for, we grouped them in categories. So how much of it was cost driven? Give me the building with the lowest cost, right? How much of it was the tenants wanted something? I mean, the tenants watch the news, they may show up in the engineer office, or sorry, in the architect office, and they say, we want the engineer to be there in the first meeting. We want to talk to the engineer, which is unheard of before, right? They want to know what structural system will be used. Tenants. So that's a very interesting thing. So there was a lot of diversity there in the opinions and in the reasons that led to structural systems. But what we saw is that there's three general categories: lowest cost, then engineer making a decision by themselves. The client says, I trust you, decide whatever you want. And then other dictating that they wanted specific structural systems for a number of reasons, right? And over time, we did that as a longitudinal data analysis. So right after the earthquake, there was a lot more driven by, we want this structural system. And over time, the structural engineer deciding stayed pretty much flat. And the lowest cost request started to increase the further away you are from the earthquake. So as people forget the earthquake, they tend to revert back to, give me the lowest cost building. And so I'll be curious to see if that trend extrapolated from 2017 to further on down the line. We'll probably see after a few years what has happened, because the reconstruction is still underway. But I think what you also have to appreciate is that New Zealand is a small country. There's a lot of foreign investors. And a lot of foreign investors just kept their money out for a while, seeing how it would play out. And they're probably coming back in right now. And these tend to be the lowest cost type drivers when they want for a building, because they're not necessarily living there. They're just an investment further away, right? So we'll see. There's a lot of good dynamics there. There's still data to collect. But I think your question is very accurate. Right after the earthquake, people are a lot more sensitive to wanting specific types of structural system. Sorry for the long answer, but.
Yeah. So I guess it's safe to say these innovative systems, it's hard to make them cost competitive still.
No, that's not true. Yeah. A lot of the buckling restraint braces are just on cost, same as other structural systems. And so what we noticed is that there's been a shift. Right after the earthquake, a lot of folks went for base isolation. I want a base isolated building because it's, you know, the holy grail, but they were more expensive. And the requirement for base isolation building sort of vanished rapidly after a few years. And engineers sort of latched on buckling restraint braces because they realized that, hey, it's cost effective. It doesn't entail more cost. It's ductile. Maybe not even need to replace it following an earthquake. So we've seen that was a structural system that was gaining steam and becoming more and more popular. And every year I went back to Christchurch, we saw there was more of them being built. And interestingly, even in Auckland, they're starting to use buckling restraint braces, which is a low seismic region, because the engineers from Christchurch talk to the engineers in Auckland and they say, you know what, it's a cost-effective system and it's more resilient.
Great, thank you.
Hey, thank you, Jerry. Thank you, Michelle, again for your contribution. I guess we need to move, Tunjai. It was a pleasure to have you here, Michelle, and hope to see you in person soon. Thank you.
Same here. Thanks a lot.
Okay.
Thank you very much, Michelle. We have seen a little bit of seismicity of New Zealand as well. That's a nice contribution, and the tectonics behind. So now that brings us to the exciting story of playing with water, ocean circulation, how the earthquakes triggers sea waves or ocean waves. And now we have our colleague, friends from University of Iceland, Dr. or Associate Professor now Ruiz Angulo is going to present our common interest of work and joint work on this one. So Angel, can you hear us, or can you share your screen so that we can start?
Yeah, I'll share my screen now.
Okay.
Can you all see my screen?
Yes, not in full mode, but...
Yeah, okay, I'll put it full mode now. Now?
Yes.
Okay, excellent. Well, hi to everyone. Good morning and good afternoon, depending where you all are. And thank you for all the presentations that you gave before. I think it was really fascinating to hear all about it. This work that I'm doing is some work that I started doing with Tunjai, and like starting last year, and at some point, and we actually submitted one paper that we still have to resubmit the tsunami part, but nevertheless, I think I'll try to give you some of the results that we came up with, and I think they are, from the ocean point of view, I think they're like, this area is very exciting. And well, first of all, like we all know the area that we are studying. We have been seeing many examples of it. I just wanna point out here that basically the complexity of the boson bathymetry, the bathymetry of the ocean is so complex in this area that makes the propagation of waves like a kind of a paradise for anomalies and behaviors like that. And this is one of the examples that we're gonna be presenting here. We have 3 sleep distributions that Professor Tunjai made and his group. And we also use the USGS one. And those are the ones that we will be presenting on this one. And a little bit of what do we use for modeling. Sorry for the sharp change in the equations, but they're really, we take down the equations from Navier-Stokes, like the classic equations, and we make some approximations using a well-known model by now that is called GeoClaw. And we take the nonlinear version of the shallow water equations. That means that we could take we could include some of the friction by using this Manning coefficient that is typically used. And it's a set of equations that's relatively simple to solve. So we solve the surface elevation and we take into account the bathymetry. We decide where are we gonna use more of the friction or less. And so GeoClaw uses some technique that makes it a lot faster. That is called adaptive mesh refinement. The adaptive mesh refinement is basically changing the size of the grids and the time steps as the wave propagates. So it's a method that is basically chasing the solution, and it chases the solution and it adapts the meshes as the wave propagates. As I said, we are going to use 4 sleep distribution models. We use GEPCO for our bathymetry, and there are some reasons why we decided to use that one. The resolution is 15 arc of second. That's the order in this area is in the order of 450 meters. For the land, we sim them together with SRTM3, and that's 3 arc of a second. That's a very good resolution on land. And basically what we're gonna do is we're gonna discretize the ocean into something that looks like this. So our ocean is no longer like continuous, it's got discrete volumes. That's what we're gonna do. And the model works really well even for large domains. This is an example that the GeoClaw sort of website uses as a test. It's Tohoku earthquake, and it shows where the domain is changing. So it does not resolve very finely where there's no wave, there's no need to resolve that area, but it just keeps chasing the solution as it moves. And we could go to even further, like this is the example of Hilo in Hawaii, how this wave made it all the way. And we could even increase the resolution there as well. So this tool is really nice to use. I'm very happy for the developers that have made this like an open source, and they keep supporting all the questions that we have. And so here's a little bit of some snapshots of the models that we use. We are gonna be calling them Model A, Model B, Model C, depending what were the constraints that the group was using. And we took all these models and we put them as initial condition for the map. This will have been how it looks, the sleep distribution on the map, the seafloor. And the model, what it does is takes these sleep distribution models and it performs an Okada transformation to uplift to get the perturbations on the surface. And the perturbation on the surface, like they look something like this. This is, I apologize for this, we smoothed them a little bit more than what we should have, but it's just to make a symbolic scenario of how the models they look. The star represents where the location of the epicenter is. And I'm going a little bit ahead on this one. We are already adding to this plot the bars of the wave heights that exist on that result from the simulation on the coastline. And something that I want to point out is that there are like some of the models they actually go, they make some waves that are a lot higher than others. However, most of them, they catch the locations where the wave heights are the greatest. And they indeed like find that the conclusion that we will come in the end, they will support it as well. Something I forgot to mention, and it was, maybe this map is gonna be, oops. Can you still see my screen? Because it got a little frozen, my computer.
Yes.
Okay. Yeah, okay. So before I start the simulations and I show you the movies that we came up with, in this plot, I'm showing like the contour of 500 meters on the thick line. It's a relatively thicker black line that is here. And the reason why I'm showing this line is that there's some trapping of waves at the coastline. And this trapping of waves is something that has been, I don't think we did not have a lot of measurements before on these type of regions where we could find trapping of these waves. But anyways, this is kind of the model that we have. And also something I was also mentioned before is that there's like a large basin here. The Icaria Basin is something that is really deep. And something that I want to point out before the movie starts is that actually once the waves, they get into fast propagation media, they're gonna go away. But if the waves, they start or they are generated in regions where they don't propagate that fast, then they don't really wanna go to the region that they have to propagate fast. So they want to remain in that area. The reason for that is that they will have to increase their energy to go to a faster propagation media. They are not gonna like it. So let's just start the model. And we're gonna see that the color bar is saturated such that we can see when the wave gets really high. So there are some regions, like for example, this area here gets like saturated colors. But in most of what I would call in this case, the continental shelf or the platform here, or like the shallow area, this area here, like, I don't know if you can see my pointer, but towards the north of the source and towards the east of it, we could see that there's red and blue coming up and down. And this is because these waves, they basically get trapped here. And it doesn't happen the same for the areas that they don't have any platform where it can support this trapping of waves. However, there's one little spot here in Samos Island that it has enough length such that it can keep these waves trapped here. And it's on the videos that were online, that's an area that we could see that waves stay there for a little longer. Now we're gonna show like I said, all the models, they show some really similar behavior. Some of them, they get like a lot bigger waves, but some have like smaller waves. But you could really see this increase on the wave height here in this area that is in this little, I guess it's like a little bay here, and where there's a marina here, and it gets like, the waves get really trapped, and the same up here. And one more area that I wanted to point out is the one that is clearly here to the east of where the source happened. This is the model that has the highest waves, and the same scale will remain, so saturation will occur at different locations, but still you can see clearly how some of these waves, they actually trap and propagate along the coastline. So this is effect that we are going to be discussing during this presentation is these like waves that get trapped along the coastline, and how do they propagate, and how can they actually like to live here, and for how long can they live here. And we're going to go, let's go to the last model here. It also generates relatively high waves. And again, like the same propagation phenomena, we could see that it sort of gets trapped along the coast. It's a really big wave that propagates along it. But I wanted to point out that it just does not escape the region that is shallow. And this is because when they see this like steep region, to propagate towards the outside, they will need to get more energy, and it just violates the laws for them. And so this is a little bit of what was a little bit like, just to recall the summary of it. This is the maximum wave amplitude. Notice that in these maps, we changed the scale from 0 to 2 meters. So we could see that for the USGS model, we do get like these hotspots. One of the hotspots that is here, like right straight north from the source. All the models, they catch that. Model V exaggerates a bit the wave heights, but once we compare to the observations, we'll see that they all do somewhere okay in between. But this scale bar is not really helping too much to notice that the wave height can be really high here in the island, in that little corner that we were talking about. That is very peculiar behavior that it has. As I said, it has like enough sort of shallow area to get this trapping effect. The rest of the areas, they don't really get this trapping effect. And why is this trapping effect important? And then we try to, this is another kind of summary of this. This is wave height versus distance along the coast. The upper panel here shows the north coast of Turkey, and then the lower panel shows the south part, the Samos Island, for one particular model, in this case, model A. And we could see the little stars are the observations that were documented in the reports for both cases. The observations are based on both on the run-up on the estimated wave height. For some locations, there are many observations in a particular spot that are not really spread out along the coast, so we don't really have those observations, but the model like captures that. So we believe that some of them are correct. In general, the models, they sort of capture the hotspots areas. And on the right-hand side, what I put is the time after the earthquake when the maximum wave is reached. And this is an histogram that tells us like, so the waves, they got to the coast, the first waves, within minutes. But some of the largest waves at some locations, they actually made it to be the largest amplitude wave up to 4 to 5 hours afterwards. That means that these waves, when they get trapped and along the platform, when they get trapped on it, they can interact constructively with each other. And once they do that, they might actually end up being a really large wave at a given location that was not expected. And also like not expected that 6 hours later, you will get another big wave. And fortunately, these big waves that came out later, they are not extremely big. But there are like some cases, and Japan has taught us that after the main tsunami, people went back again and tried to check how their houses were, and then another wave train came and hit back again. And those are experiences that we would like to really emphasize in work that I have been doing with my colleagues about it. And so there's a recent paper from Mohammed, and that actually emphasizes how long after, from observations around the area, from observation, it shows how long after the earthquake or the main waves, it actually comes the biggest waves. And not only the biggest waves, but also like the most energetic trains. And some of these trains of waves, they come in pulses. Those pulses are most likely because they get trapped in one of these peninsula. Then it cannot really exit, then comes back again, keeping the same sort of wavelet behavior. And so did we see that in our models? Well, yes, we're gonna start walking on our domain from the furthest northwest on this station. That is the 1035. So this station is furthest out here, one of those pink ones that are here. I'm just choosing from the clusters of them. And sure, the first waves, they arrive like within, as I said, like minutes of it, like less than half an hour. But after about 6 hours, the wave heights, they still remain kind of relatively significant. Some of them like 0.5 meter wave heights for this case. If we walk towards the peninsula that is here, then we get like the train of waves that is on the upper panel. Similar to behavior is on this small area that is on the almost straight north, where there's the hotspot. We could really see that the wave height went really high up to 2.5 meters high. But then still like almost 2.5 hours after, we still get like waves that were in the order of 1 meter height on average between an ensemble from the models. And this area is one that fascinated me here. It's an area that is very flat on land as well. And fortunately, I was at least looking on Google Earth and talking to colleagues. It doesn't have a lot of population or buildings that could be flooded, I guess. And so the waves here, they live the longest. On our models that are 48 hours, they live for the 48 hours out there. One of the things that our model has is that they might not have all the tools for dissipation properly implemented, but still within 12 hours, I mean that the risk is relatively high. And the waves, they still remain high. And now if we move to the Samos Island and we go to the furthest west of it, where the bathymetry was showing that was the steepest, so there's like a cliff in the ocean, if you want to call it, then the waves, they do actually go really high, which is very close to the epicenter and the source, where the highest peak is. But then very quickly after, they just vanish, like the waves just dissipate. And that's because they just propagate into the deep ocean and they are just not going to come back. They don't have any boundary to bounce. But the little bay that is here, that has a little bit of shelf, enough for these waves to live trapped there, it does show this mechanism or this behavior. Not, fortunately, again, like the waves, they don't remain for a long time with very high amplitudes, but they do remain for a long time. Like this is just 6 hours, but we have like more time. And this, this again, showing that is very complex, the slopes here. And here I'm showing just instead of bathymetry, I'll show the slopes of the area. There are really steep slopes in this area where I said that the waves, after they come in, then they go out, reflect, and then they're just not going to make it back. On other regions here, the slope is really flat. So these waves, they can really live on it. This little bay here has also like some extension, relatively good extension of flat. These areas as well. So all these platforms, all these areas is quite flat. It's like it's one of the flattest areas. And it turns out that from previous work that we've been doing, it's like a really prone area for what's called edge waves. Edge waves there are many names for those in oceanography, and these are one particular ones that actually they can live trapped to the boundary. And they could be like Kelvin waves or any waves, but they decided that they were going to be called edge waves, and there's a full theory about it. The theory is very nice. It could be like solved very nicely to this. We could come to this dispersion relation that we can actually solve for a given wavelength. Usually we give like a wavelength or like a wave number we estimate that based on what we see on the simulations, the frequencies as well. Sorry. And some of the other previous authors, they also show that these waves can be very energetic, and actually they could come back as an unexpected coastal wave that will hit, and that they have to be taken into account. These are previous studies that have shown that. We came up with a metric at some point that we follow a metric that is called the tsunami coda. It's very similar to the coda for earthquake signals, like the seismograms coda. And for us, we did we noticed these waves first in Mexico when we were working on a relatively recent earthquake as well. We noticed that there were some waves on the sensors that they just lasted very long. And like I'm going to walk through these relatively quickly. This is the Tehuantepec shelf in Mexico. Is really wide. It's relatively as wide as the one that we have seen in the Aegean Sea. And we had an earthquake that was sharing both on the shallows and the really deep part. And that means that the wave triggered also within the shallow part. And it propagated and trapped the waves. And we could actually see the reflection. And we just, the equations that I was just showing, we just wrote them down, and they actually match very well with the theory, the slopes that we could see in this histogram of the waves. Oops. I think. Can you still see my screen?
No, your screen is gone. And can you also please summarize?
I think I'll just summarize very quickly with that. So basically, like, sorry that my screen is gone. I'm going to try to, I think my keynote just broke.
Was there anything else to show, or we can wait?
There were just like the conclusions that were going to come, but I could just mention that.
Okay.
So in conclusion, I think that the area that we had for the Samos earthquake, it really has this type of waves that live very long, and the observations have shown that, and we could actually model that, and all your models, they all agreed to it. And I think it's important to keep in mind for not only the early warning, but actually the post warning. Should keep in mind that waves can live even for up to 12 hours. So this rewrites the codes on when are we going to lift the emergency of a tsunami alert. And I think this area is one of them. There might be some that are not, but this is one. And I will close it there, and I'm open for questions. Thank you very much.
Thank you very much, Angel. I think it brings us to a very nice discussion. Now, I don't know, you have realized there's a paper just Thanasis also informed us over the chat box, published a couple of days ago, last week. I've seen about the Samos Island, that's Karlova Sea, and the small marina you were mentioning. They are the trap waves of the tsunami waves. So there are some more field observation from the Greek parts that we can check matching. It's on the paper. I will send you the details. I seen it, I read it, but it's not going to change much of our results, but it's a new contribution. So any questions, please, Thanasis, Jiri, Rob, Tuna, open to comments and discussions. Okay, if not, we'll say thank you and congratulations again for being appointed to Associate Professor tenure track position at University of Iceland for a new position. And now we can move to next talk, Mehmet Ergin. Please.
Yeah, can you hear me?
You already shared your...
Yes, already, yes, I did.
No worries, we have time. Don't worry, we can have extended time later on. If you like, maybe I can skip my talk, no problem whatsoever. You are the guest. Okay, thank you.
Thank you very much for invitations and for organizing, especially to Jai. And dear participants, I'm going to share our studies with the aftershocks monitoring for this area. Here, I think it's not moving. Can you hear me? Can you hear me?
We can hear you, but your screen is frozen.
It's locked. I didn't understand what's happening. All right.
Oh, it came.
Yeah. Anyway, it shifted a little bit, but I didn't understand why it happened. Okay, let's go this. And as you
can go from the beginning, no problem. Just go from the beginning.
No, it's also beginning this, no problem. And as we know that the location of the main shocks reported by the different seismological institutions varies and scatters, and you can see here their results, and I share here. But for us, the relocation of the main shock is really necessary for the interpretation for the rupture processes. And here, the red lines are the showing the main fault areas here. And in order to relocate the main shocks, first we have collected all the recorded seismograms up to 300 for worldwide, since there were no stations operating by our institute around that and at that by time. So after establishing our temporary stations, we did study and we used the velocity model obtained as a result of our study and derived station corrections for these our stations. Then belong to also our agencies, and then we contributed these studies. And after a series of iterations, we found a very reliable hypercenter locations, as you can see here. The depth, the parameters is here, solution parameters, and the depth is 15.4 kilometers. And as we can see here, determined focal mechanisms are very similar to each other. And they all together slightly slip on the normal fighting striking roughly west-east directions. And here our moment tensor solutions. And also for the moment tensor solutions, we did another empty inversions. And our result consisted with several other solutions, and that indicates the main shocks. It's MW7, and we found the depth, central depth is 8 kilometers, and faulting mechanisms. And here we used about 84 displacement records all over the world, right? Less than 10 degree distances. And here our MT inversion results. You can see here the solutions, how is it? Then we did our aftershock studies for this region and for investigate and monitor the high precision after seconds. And our stations were first installed along the epicenter region to cover the aftershock zones around the Kuşadası Bay. And here you can see our 8 stations. And also we put 5 GPS stations, but these studies will be held on other colleagues. And we established this station just after 10 hours of the main shock. And here's the instrumentation which we used, high resolution RefDex, and this is the temporal network, therefore we have to be very hurry. So they are 4.5 Hertz 3D component seismometers. And this is also continuous recordings about 100 seconds per second. And this is the GPS recorders properties also, you can see that here. And I'm not going to go detail about the tectonics for this region because already many people are discussing here the figures, schematic figures of the main faults here, and you can address here you can find their address here. And when we look at the historical earthquakes also, we can see that lots of reliable events happening and continuing to around the Turkish inland here. This also can be found easily. This is the instrumental aftershocks, some earthquakes around here region, and you can see that region also that's shaken for a long years again. For aftershock studies, really phase picking and monitoring of micro earthquakes are really challenging tasks. Processing of huge data for aftershock studies due to high seismicity, and dense station coverage. Therefore, we did a lot of work for this reliable for earthquake studies. So therefore, we have picked all arrivals visually for aftershocks, and we had a very large amount of aftershock data collected during the 2 months period, and about 1,700 events with 150,000 readings. And also for this kind of temporary stations, it is well known that they create Wallace models leads high uncertainties in hypercenter locations. And also when we started to work, we didn't have any detailed information for the value structure here. And after a series of iterations, an optimum 1D crustal velocity model was obtained with the station correction residual values, and we used the Wallace algorithms. And then after having a new 1D optimal crustal model, all events were relocated again. And for these studies, we retained on the best located events for further analysis. And then we applied some filtering to our data sets and including only well-located events. Here, their histograms for uncertainties, number of stations, root mean squares, and the gray ones are, primarily distributions of the aftershocks parameters, and the red ones are our reliable solutions. Then they can show they are really very good solutions. We can understand it. And also magnitudes of the events range between 0.6 and 5, and detection threshold of this or network order of 1.0, and only two larger and powerful aftershocks of ML 5.0 struck this region. This is the P and S wave arrivals numbers, as you can see here, and we used our 8 temporal stations and our other national agencies and also Greek seismological observation stations, and you can see how others also contribute to our data solutions for our aftershock studies here. And here I want to show you that now maybe you can understand that how better and how hard job it is to play with the aftershocks. And this is the Izmir 5 stations. This is really very close space for the epicentral zones, and therefore at least one station was always within the distance of the hypercentral depth, which enable us good control the focal depth estimation for this region. And you can see only 1 hour recording time, and you can see how many events that we have to detect. And this is our records for all our 7 stations recording around for the aftershock studies, and how many earthquakes that we had on it for these studies. And when we come to the aftershock distributions, this is the preliminary results. When we talk about before about 700,000, 700 events here, and their distribution showing here. And when we put our reliable solutions, they took over the older region, and you can see with the red circles here. And the epicenter distribution suggests that seismic slips occurred along the different sections here, and on the same faults or different faults here, as you can see here. And closer look at aftershock distributions reveal 7 distinct zones of cluster activity, as you can see, and separated by gaps which are colored and numbered from 1 to 7 from west to east here. And the most notable feature of the aftershock distribution is the presence of the high density Arctic soil along the main fault zone with a smooth strike direction to the main shock here. And the number of the aftershocks of this cluster is really larger and little bit diffused. And one of biggest aftershock MW5 is located here. And at the eastern end, seismicity patterns bend to southwards towards the direct peninsula, as you can see here. And the prominent feature is the elongated cluster of aftershock with an azimuth of 40 degrees around here, approximately 20 kilometers long at the west of the main shocks. Displays compact distribution patterns here, as you can see here. And also it is observed that there is a rare activity in the far west of the islands here with number of 7 cluster. And another notable activity cluster 5, which we name it. This is the intense activity that started 2 days after the main shock in between Samos and Dillek Peninsula. If we look at closely this clustering, their spatial distribution appears more diffused with 3 traces of subparallel lineaments, and another condensed activity can be distinguished, possibly corresponding to second faultings for this region here. And also for further analysis, furthermore, isolated seismic activity is recorded offshore Kuşadası, which is also started 2 days after the main shock and displays more concentrated small seismic events inside. And if we look at the time sequence of the aftershock occurrence along the east-west longitudinal directions here, according to the main shock, we can see that just soon after the aftershock, main shock occurrence, it is seen that most clusters densely activated on both sides of the main shocks along to 40 kilometers here. But after just 2 days after later, it extended southeast, northeast part of the Samos Island. As you can see here, the time occurrence here. And if we focus on this more here, and these clusters are just activated on 1st of October for the eastern part. And when we look at the depth sections that includes well-located events of aftershocks, also were studied with the 3-week programs, and we tried to scan all the various angles for each cluster to examine variation of rupture trends with depth. And you can see from the north looking side here, their distribution like this. And I will come later this one. And here another explanation from west to east, their depth sections. And this shows that activity is concentrated in the mid cluster about 4 and 12 kilometers. And the activity in the upper class at shovel depth is much less. And for offshore earthquakes in cluster 6, almost no activity was observed at depths of less than 8 kilometers. And here's the main clusters, as you remember here. The depth section of this cluster examined at all profile azimuth angles. And as you can see here, it does not show any clearly defined dipping angle when we look at them from different angles here. In fact, depth sections at deep profile angles we study here and do not reveal any clearly defined dip angle as discussed before dealing with the fault polarization, especially the offering the north dipping. But here we couldn't see any clearly defined dipping here according to defined fault plane solution. Therefore, we can say that certain dipping plane is not observed with these depth sections. And if we come to other clusters, we can see that and certain dipping plane is observed in the depth section here, about 140 north azimuth angle, trending azimuth angle, and we can have this maybe dipping angles here. And when we come to the eastern part with the cluster 5s between Dillek Peninsula, you can see some consisting of several distinct seismic activity when we scan by azimuthal angles. This activity reflects subclusters and here showing dipping slope, especially the C clusters, the subclusters remains at shallow depths without any dipping. And also here, D cluster shows normal and strike deep slip here. And when we look at the fault plane solution for this area, we can see here the normal faulting, and here there's some striking fault strike is, and here is also, and there, when we correlate with their fault solution with the depth, and they're really proper with that, and we can say that this section shows maybe dipping slope with extending of these faults here as they define it here. And here's the moment tensor solutions we apply for this region. About 1200 maybe. However, the geometry of the network not allowed reliable fault solution determination for small earthquakes, since the majority of the earthquakes are outside of our network with azimuthal gap. Therefore, we couldn't do phase arrivals peaking, especially for FP fit for the aftershocks, but only fault plane solution for aftershocks in the vicinity of Kuşadası are calculated by FP fit algorithm with manually picked P-wave polarities for small events, because here with the blue ones are solution with the FP fit, the red ones are MT inversion solutions here. And if we focus on this region for the main cluster area, you can see that the all fault distributions, and they are much more proper each side, and they mostly show normal faulting. And when we look at their stress tensor inversions, we can see that sigma 1 is vertical here. And when we look at the western part of, focused on the western part of that, our solutions like this here, and mostly they have strike slip properties, as you can see here. And their stress tensor analysis give strike slip, which is sigma 2 is vertical here. And when we concentrate on the eastern part, we can see the tree part of that here. And if we go to the northern part, and if we focus on all the condensed activities, you can see their explanation here. And they have both strike slip faults on, and especially here, strike slip faults with the same direction and the same properties here. So as we come to our solutions, we can say that we analyze the aftershock seconds of some of those earthquakes for 2 months observations, and the general pattern of well-located event aftershock distribution shows six seismic elongated east-west direction together with some distinct northeast-southwest directions. And the main cluster activities borders the Samos northern coastline, and most aftershock mechanism associated with it predominantly pure normal faulting along east-west striking planes. Unlike other studies, we could not see any clear north dipping plane on that section, especially for the main clusters. And the westernmost cluster and easternmost cluster with northeast-southwest alignment are both associated with clearly strike slip motion consistent with the aftershock distributions. And these findings also consist with the tectonic history of the Aegean region since late Oligocene, and north-south compression region turns into the north-south extension in late Miocene. Along the weakness zone developed in this tectonic region, some authors also observed normal fault characteristic along the east-west and northwest-southeast directional structure, while they observe mostly strike slip characteristic along the northeast-southwest structures, as we found here. Thank you very much for your attending.
Well, Mehmet, thank you very much. It's a very nice talk after chasing after earthquakes, aftermath of the Samos earthquake, like a marathon of seismicity. I know the earlier days how you made a break effort to catch some lacking seismicity in that Dilek Peninsula. So the presentation is open for questions, comments, Thanasis, Jiri, Rob, and all the other participants, please. So we may have reached the converging the similar results or conclusions, but we have some differences in finer, small details. So that's why I think maybe Mehmet can complement his data with the existing Greek data, maybe if there is a lack of it, so open share base to improve the bits, but it's a nice piece of work. So the questions, the stage is open for questions. Thanasis, Jiri, do you have any?
I have a question for Dr. Ergin. You didn't mention the velocity model you used. Did you use your own velocity model or some literature?
Seismicity.
Of course, this is the main problem. And first, we used some artists which they have a velocity models for this region, a closer region, not just for this. But as you know that the velocity model with your appreciate with your data. So we call it huge of data. First, we started some other studied velocity structures from other studies. And now we develop our special velocity model with station corrections, which we used here. Then we had our own velocity model for this region with station corrections, which we are using, okay, both our stations and other organizations.
Okay, thank you very much.
So there's so much to complement. Jiri, do you have any comments?
Yes. I don't understand why it is not possible to see the Nord dipping plane. If I understand, it was hypo-DD relocation, yes. So why not? What is your explanation why there is no any indication of the dipping plane? And second question, and this is general question to other participants, I would like to know whether in such situations, some people try also grid search method pre-constrained to search aftershocks on a plane, on a given predefined plane. Thanasis mentioned that he has doubts, some aftershocks may be on fault, some aftershocks may be out of fault. So it is related to this. So I have, in fact, two questions. How do you explain missing correlation, missing indication of the dipping plane? This is first question.
Okay, this is really a challenge of finding good epicenter locations. And we did also hypo-DD.
Yes.
And if you play too much with your data, you can get the solution what you like it. But there are so many parameters that you can see the errors. Mm-hmm. And after that, we play too much because this is really very important. And we had a huge of data and we took all the best one, mm-hmm, as you see here, because we use other organization stations also. And when I play with the hypo-DD, yes, and when I play with the, our hypocenter solutions, they didn't give too much differences, okay? And I would like to put here, I put it in solutions, but I didn't see any differences. And then I learned these 3D programs to see, and it is my scene that also we talk about the main clusters, and we divide also subclusters that. Uh-huh. This is my scene that I mean, really it was a big job for me to find, because many people say North dipping. No, I didn't see that. As I showed here, okay, it's not clear dipping because, mm-hmm, I chose our data, okay? And it doesn't show any, when I look at here. Of course, you can put some traces here.
No. Yeah, I understand. But in this sense, you said something very interesting, is that in this data, really such a dipping plane is not seen.
Can you see
I have some concern or maybe some worry. In many papers, not related to Samos, not related to any specific earthquakes, I have seen it very often that in these hypo-DD locations, we often see certain very clear clusters. and many clusters, not just one, simply many. And I have a general question, Dr. Ergin, to you, but maybe also to anybody else. If there are some doubts about reliability of clusters in HyperDD, because often I see so many, so well-developed clusters, and I'm not expert in HyperDD. Could some clusters originate artificially, according to your opinion?
When you use the HyperDD, friend, I can say that I don't want to lose my data, all right? Because you have to lose most of the data, and they cluster very small events, and they make very smaller your data. And I play with the HyperDD, and really I didn't make it because they are very close to each other. I'm talking about the main clusters, okay? I am not considering other clusters, and I work on it too much. And really, when we apply it to HyperDD, because I didn't want to discuss HyperDD here, this is the hypercenter solutions after having a velocity strategy and station corrections, which more help our relative solutions. So what can I do? I mean, I didn't want to lose my data playing with the HyperDD. Okay, because they were close to each other.
Yeah. Thank you very much. It's very open questions, of course. Nice results. But can you give error bars on your locations from relocations or what? Maybe. But the other thing is, remember, this is a normal fault, okay? It's a deep slipping fault. It's distributed all over the fault plane. If it's a strike slip earthquake, like East Anatolian fault zone, it would have been much better to see the directivity effects. But this is a deep slip faulting, and the fault plane is being occupying all the aftershocks as distributed seismicity. Yeah, but maybe in some angles it's not easy to see it, but it's there. Yeah. I can see the entire fault plane where the aftershock is being accumulated. Yeah, anyway, this is not an answer, of course, this is a comment. Yeah.
Right,
yes.
Thank you. As I told you, that this is the play with the huge of data and the correlate with the real features, really it's big job, you know.
Okay, we can discuss later on, maybe among ourselves or maybe some other occasions. Thank you very much. I know you've been rushing behind, chasing after earthquakes and after the event. So it's a nice piece of work in a limited time with the limited resources here in Turkey during even COVID-19 issues. Thank you very much. I think we should really move on to the next talk by Tuna Eken, on the geodynamic aspects of Eastern Mediterranean tectonics. So Tuna, the stage is yours. Please share your screen. And thank you very much.
Hello, do you hear me?
Yes.
Okay. Hello, everyone. So now I will bring your attention back to the general picture of the geodynamic facts in the region. So, as we all know, almost geophysics and especially seismology provides a strong tool to elucidate the deep interiors of our planet, where actually we do not have any direct access otherwise. So, for instance, seismic tomography, as in this example, simply gives the present snapshot of various physical properties. These could be seismic wave velocities, as in this example, or attenuation or viscosity, or can be converted viscosity or density. And usually for simplicity, inverse models are performed under isotropic Earth assumption. However, in reality, our Earth is anisotropic, of course, and this means elastic properties of the medium are not the same in all directions. So vertically, layers with different stiffness can behave anisotropic around the vertical axis of symmetry, as in this example on the upper side, upper panel, or in some cases, natural fractures around the horizontal axis of symmetry can also cause anisotropy. So why it is important? Because having a proper knowledge of anisotropy can be very useful for understanding deep Earth's interior kinematics. So if we start with olivine in the mantle, so olivine is a rich upper mantle mineral and it's highly anisotropic. When this olivine mineral is strained, then lattice preferred orientation develops. Thus, observing anisotropy using seismic waves within the mantle can be a certainly good guide to understand present or past deformation styles in this part of the Earth. One of the most, or maybe the most diagnostic tool is shear wave splitting technique to detect seismic anisotropy in the crust and mantle. And usually when shear waves enters into an anisotropic medium, they split into fast and slow components, depending on the thickness of the anisotropic layer and anisotropic strength. The delay time may occur between fast and slow components. Also, orientation of the fast component is controlled by the anisotropic trend. And these shear waves, this is an example from shear wave splitting measurements. I'm not going into too much details, but I can say that anisotropic parameters in this case can be simply estimated through a correction process of the elliptical polarization when an anisotropy existing between affecting the horizontal components into a linear polarization in case of isotropic conditions existing. This whole process can be simply done in a grid search manner. So in general, the simplest possible thing is to link between mantle flow driven LPO or lattice preferred orientation of anisotropic minerals and seismic anisotropy parameters. That's the basic thing that intuitively we are doing. But it is hard to establish such linking always because for some regions with more complicated mantle velocity field or fabric types and strain distributions. So here we see velocity field performed in 2D or 3D, considering 2D and 3D conditions as numerical simulations of the mantle flow. Usually geodynamic models together with seismological observations and models have great potential to tell us about the past and present deformation and dynamic processes in the Earth mantle. So now, if we go back to our region, most of the information on seismic anisotropy comes from core mantle refracted shear wave splitting measurements, in other words, SKS splitting measurements. Here we see the blue and yellow and reddish and some of the green arrows. They are compilation from different data sets and represents the fast polarization direction or fast wave or azimuths scaled by the length, scaled by the delay time, observed delay time as a function of strength of anisotropy. Also in the region, there are some recent advances in, because of the recent advances in geodesy and seismology, in the observation from GPS velocities and seismotectonic constraints clearly suggest that the significance of subducting African plate along the Hellenic Trench and Cyprus Trench with especially with rollback mechanism along the Hellenic Trench in the west, and of course collisional tectonic regime in the east. So there are some several tomography studies in recent 2 decades, and they are relatively having good resolution. And we still keep, in the region, we still keep updating tomographic images of the mantle. One of the most recent one performed by our former PhD student Judith Konfal in our group. And she clearly imaged African slab fragmentation with the slab pier and broken slab in the east. So just after me, so she will be going into details about this model. And to further understand how these features have been evolved with the resultant flow properties, so Judith performed a 3D time-varying petrological and thermomechanical models. So depending on our knowledge, we consider various model constraints, which include geometry of the plates and tectonic evolution and retreat in the Aegean region, and convergence rates and direction of the convergence, And the tear is a perturbation or heterogeneity, significant heterogeneity in the slab, as well as slab break-off phenomena. And we set up an initial model, and so she she considered initially the subduction of a branch of the Nile Tethys Ocean, which is still subducting, and secondly, the collisional area of the Anatolian and Arabian continental plates in the east. And that's the results. One of the results that we considered an optimum one. Overall, we tested 60 models, and this animation is representing our optimum model. And so the optimum model at the present day involves the rollback of the African slab, clearly here, and the break-off. If we look at the model result from the east, the break-off in the east. So we have decided on the optimum model in general among these 60 models by considering seismological constraints, of course, mostly seismic anisotropy parameters. Since one of the outcome of these simulations is 3D mantle flow vectors varying for the entire model area. So these can be converted into synthetic SKS splitting measurements, and in this way, a comparison of synthetic SKS splitting measurements based on our final model with observed SKS splitting measurements can confirm, for example, trench perpendicular FPDS and strong time delays in the Aegean region and circular FPDS or circular phosphorization directions at the edge of the tear and break-off, and a general trend similar to the observed splitting measurements. So, but then, okay, the mantle, the situation in the mantle, or sublithospheric mantle in this way, we could model. What about the kinematics in the crust and mantle lithosphere? So there are several studies of the crustal and lithospheric properties, including seismic velocities, thickness of the crust, and LAB in the region. For instance, S-receiver function analysis suggesting the entire mantle lithosphere is not thicker than 100 kilometers beneath Anatolia, as you can see in this example. However, there are, of course, our knowledge is quite enhanced in seismological constraints, in terms of seismological constraints and data. However, the questions on how the deformation is being transferred vertically, or whether a global crustal viscous channel flow exists remain still unknown. So there must be more understanding and consideration on these issues. So let's start with the upper crustal. If we start from this very shallow part of the crust, a compilation of local shear wave splitting data, for instance, in the North Anatolian fault zone or across the North Anatolian fault zone, indicated in the past that within 8 or 10 kilometers, the seismic anisotropy nearby the fault zone is structurally induced, whereas it is controlled by stress regime away from the fault. So in fact, these type of observations were well consistent with an early model proposed by Bones and Zobeck. So for deeper part in the crust, so we can use P-receiver functions because P-receiver functions are sensitive to the seismic anisotropy in the deeper sections of the crust. For this purpose, we selected teleseismic P waves recorded in and around central part of the North Anatolian fault zone. And we simply apply a harmonic decomposition depending on the azimuthal variation of the radial and tangential receiver functions to be able to get the significance of anisotropy and its orientation in the crust. Here we can see directional dependence of radial and tangential receiver functions with the polarity changes at 2 example stations, Alic and Doğuriol, I think, or Doğaniol, at the central located at the central North Anatolian Fault zone, central part of the North Anatolian Fault zone. So these harmonic decomposition analysis mainly indicated a strong asymmetry across the fault. Southern block, especially in the upper crust, are very complex and highly anisotropic, confirming also early local shear wave splitting measurements. But deeper parts, so we could observe the effect of peridotite type rock containing melt on anisotropy. So another PhD student in our group, Derya Kelesh, also applied the same harmonic decomposition technique to the northwestern part on North Anatolian Fault zone, and her results in the end were able to detecting strong asymmetry, but with depth varying pattern, also complex and highly anisotropic upper crust in the southern block was existing. In a very recent seismic tomography study, through our collaboration with Chinese colleagues, seismologists, we inverted local P waves for isotropic and anisotropic velocity distribution in the crust and uppermost mantle, considering entire Turkey. Our anisotropic orientations indicated vertically coherent deformation between the crust and uppermost mantle. To the east or to the further east, we observed more decoupled crust and lithospheric mantle in the central part of the Turkey. In particular, observed decoupling between the crust and uppermost mantle beneath the central part can be explained by maybe potential influence of upwelling mantle material and resultant melt activity, as interpreted from isotropic seismic velocity perturbations in this study as well. So lateral variations, if we look at simply single SKS splitting measurements results, the lateral variations in some cases can hint about the depth extent for the faults. So in Pamir case, for instance, stations that are closely located to the Karakorum fault in the south east of Pamir, or Talas Fergana fault, indicate fault strike parallel anisotropic orientations. We observe similar behavior for the south and north Kulnun fault in northeast Tibet, as this may imply that these faults might have a very deep lithospheric extents. However, when we approach to the west along the North Anatolian Fault zone, we do not apply, this consistency fully doesn't apply to the NAF, where we observed SKS-based anisotropic orientations, more or less oblique to the major trend of the NAFs. So we wanted to go for whether this is correct or not. So to further investigate this observations, Ceyhun Erman, who is another PhD student in our group, has selected teleseismic SKS phase recordings at several permanent stations in Western Turkey. First, he performed a grid search considering two-layer anisotropy. And here we show 4 estimated modal parameters with respect to each other beneath station Lapseki, which is located in the northwestern Turkey. So here red circles results of this grid search and indicate final modal parameters in each panel. So in this example, we can clearly see that the mantle has more complex anisotropic structure, especially in the western part, with upper and lower layers, possibly this referring to the lithospheric and sublithospheric mantle respectively. And his two-layer models in general in the central and western Anatolia implied that upper layer phase polarization directions align with the North Aegean trough in the northwest Turkey, but to the east of it, a clear inconsistent anisotropy with the North Anatolian Fault zone he could observe. So to conclude, we can say that numerical models and observational constraints usually confirm the dominant role of converging plates in the region with presumable heterogeneities, for example, slab tear and slab break-off events. And the role of this subducting and rollbacking subducting will cause a regional trend of LPO-induced anisotropy in the asthenospheric mantle, most likely due to the mantle flow induced by slab rollback activity or extension beneath the Aegean Sea. So in the upper crust, on the other hand, we can say that there is a strong control of active tectonic features on observed seismic anisotropic signals. And mechanically decoupled lithosphere and asthenosphere observations from both shear wave splitting measurements or local earthquake tomography results can be a signature of the imprint of a lithospheric petrofabric that is formed by a recent deformation. And we could observe at the western part of Turkey, we could observe a continuation of the NAFs at lithospheric scale in the west. So vertically coherent kinematic properties is conflicting with the idea of east-west pervasive, a low viscosity layer in the lower crust, which possibly accommodate crustal flow. And in the central part, decoupled anisotropic observations between crust and mantle can show the effect of temperature or thermal influences in the submoho, and constraints from recent tomographic image in general hints about possible melt and upwell of the hot mantle material in the central parts. So that was my talk. Thank you for your interest and listening.
Thank you very much to that. Nice overview of the Aegean and Mediterranean tectonics. We may have one or two quick questions or comments, if any. I know it's been a very long day, but do you have any questions?
Yes, I would like to ask, Dr. Eken. Yeah. I find one result quite interesting when you also consider the geodetic data about rotations. I'm talking about vertical axis rotations. So you find that the upper crust and the lower crust, at least, are coupled. Is that correct or not?
Depending on tomography studies, for example, here, it shows a regional variation or lateral variations. For example, to the western part, we observe a vertically coherent coupling between crust and uppermost mantle. But to the eastern part, we do not observe this anymore. Okay, now, by the way, we are looking at the difference between crustal orientations from the SKS orientations, okay? So at 30 kilometers, this difference is very small. So in the central, sorry, in the western part, so indicating a possible coupling. But in the central part, we observe that these are quite high, these difference. So there must be not anymore a vertical coherency. Instead, decoupling is ongoing.
Right. So I would like to clarify, your resolution is from 30 kilometers and below. You cannot differentiate shallower anomalies.
We can also differentiate shallower, but we mainly focus on this lower crustal part. So looking for a coupling between upper crust and uppermost mantle.
Okay, thank you.
Welcome.
Well, thank you very much. We should move on to the next one. It's another talk by our group members, Dr. Judith Maria Confal. Now she's working at INGV Bologna. Judith, is your workshop or laptop is ready for screen sharing? Can you make it full screen, please? Full screen, Judith. Okay.
Yeah, thank you very much for the invitation. As Tuncay said, I did my PhD at Istanbul Technical University with him and Tuna and several others. And yeah, like mostly my topics were about anisotropy, but today I will share one of my projects, which was P-wave tomography in the Eastern Mediterranean, and that Tuna already mentioned shortly. And yeah, so we're in the Eastern Mediterranean, and we had in the last few 100 million years a lot of different subductions. That's why we have so many fragments in the Anatolian plate. We have currently the Arabian and the African plate moving towards the north. We have an oceanic subduction in the Hellenic Trench. Yeah, more or less like a continental subduction around Cyprus, and a continental collision zone in the east. And the Anatolian plate is escaping towards the west because we have some rollback extensional regime in the Aegean. Yeah, so the last 30 million years, a lot has happened to the African-Arabian slab. It was a continuous slab at some point. Because of the fast rollback, like a tear appeared around 15 million years ago. Then when the two plates collided in the east, a break-off appeared, and probably there also another tear appeared in Western Greece. And this is more or less the simple explanation of the tectonics at the moment. And of course, there have been a lot of P-wave tomographies in the last recent years, but yeah, tomographies change the more data we have, and the better computational possibilities we have. Therefore, I guess every now and then, like, it's good to make a new one. And yeah, we can already see that, like, in every different model, there's also some small differences about, for example, the geometries of the tiers, how some other small tiers, or how much extending is the Aegean slab. Yeah, so this was one of our main reasons to do another P-wave tomography. Another one was that the most recent ones didn't have much data in the Western Aegean, and also small part of this tomography study was to correct the P-waves for anisotropy. Yeah, so we had 7 years of data, and as I said, like, we especially extended the models compared to prior ones in Western Aegean in Greece, and yeah, we cross-correlated the P-wave forms. We did a hybrid ray tracing method for the inversion, and we used the 1D model for the outside model and 3D inside. And to to correct for anisotropy, we added an anisotropic field and inverted with that to improve the model. And yeah, as usual in this region, when we use teleseismic events, because of the location, the Bergazimuthal coverage is it's a little bit one-sided, but in the end, yeah, we have more from one side, but we do also have some events from the other sides, and we noticed that for the whole region, we had a good break coverage to get reliable results. Yeah, so these are my isotropic results, depth slices, and you can see the slab, the Aegean slab in the south here. You have the eastern and western parts of the Cyprian slab. At some point, you can see the break off in the east, and some small fragments of the Bitlis slab are in lower parts, and in very low parts, you can still see the Cyprian and the Aegean slab. So I will start again and come to some other parts. So in Western Greece, we can see a high velocity zone. And yeah, this is probably related to a tear. And then we see the very prominent tear in Western Turkey. And yeah, we also saw a tear in between the Western and Cyprian slab. And below the Aegean slab, we can see also a slow velocity zone. Yeah, so here we have some cross sections of the slab area, and again, the first few cross sections are about the Cephalonian low velocity zone, and yeah, it's very prominent, and the data is also still good enough to resolve it. We can see that in a depth until around 150 kilometers, I guess. And yeah, we see the other tier here. And also we see a very, very thin tier between the eastern and the western Cyprian slab. Yeah, so Tuna already told us that there is a lot of anisotropy in the region, and yeah, it's the strong anisotropy in the upper mantle is mostly northeast southwest directed in a lot of regions, with small differences, for example, around the tier or in western Greece. And because anisotropy changes the velocities of seismic waves, we saw from Tuna's presentation that it changes shear waves, but it can also change the velocities of P waves. So in general, if we have horizontal anisotropy, we could get a slow velocity artifact, and especially if the anisotropy is vertical, we could get a fast velocity artifact. And especially these vertical anisotropy would have a very strong effect on our P waves. So, I mean, the horizontal anisotropy is quite well known from shear wave splitting measurements, and is especially strong, for example, in the rollback areas, It sometimes changes its direction, for example, if we have a tear or something like this. So, but yeah, it's horizontal anisotropy, and if it's everywhere, it wouldn't change it so much in the perturbation. But if we have, for example, very strong vertical or subvertical anisotropy around the slab, this could change some features in the P-wave velocities that we see in our figures. Yeah, so we did two things. So to correct the data, one is, so Tuna also showed the numerical model for the region. And from this one, I got also an anisotropic field. And the good thing about this synthetic model is that it also allows for vertical, subvertical, any kind of direction of anisotropy. So we were able to, yeah, get any kind of direction that anisotropy could have. And we tried to fit, because it was a synthetic model, of course, it's a bit difficult to, I mean, it was made for the region, but of course, it's sometimes a bit difficult to still fit it. But we did our best to fit it to the region, and I guess we were more or less successful in that. And another way of how we corrected the data was to use shear wave splitting measurements from Paul et al. 2014 and interpolated that over the whole region and then corrected the data for that. Yeah, and so in general, like if you, this is the completely isotropic one, then the one corrected for anisotropy from the numerical model, and the one corrected for anisotropy from the shear wave splitting measurements. And these are the differences between these two and A and D. So in general, like you would say, okay, like we have up to 2% of differences in the perturbation. This is quite high, and of course this is in general high, but if you look at actually the result figures, the big features of high or low velocities, velocity perturbations are more or less the same. But we have to be careful if we interpret some small features. And yeah, for example, I mean, we already talked a lot about, for example, the tear and how this window in the slab looks like in this in this workshop. And so, like with tomographies, we usually interpret these kind of the geometry of slabs. So we have to be careful, like how reliable our results if we're not including anisotropy, because the geometry of the slab could change in small scales, but sometimes this can be important. Also, we see some differences, for example, in the geometry also of the general Aegean slab, and this is probably because of the strong dipping anisotropy. Yeah, these huge differences in the east we are not sure if they are real or they might be artifacts, because yeah, the station density in the east is not that big, so these might be yeah, some artifacts. And also in the cross sections, we can see small differences between isotropic and the one corrected for the numerical and the shear wave splitting measurements. For example, the strength of this low velocity beneath the slab, or some geometries of some low velocities, or for example, the tier here is also a little bit different, this window. But the general features are more or less the same. Also, here we can see again nicely the tier between Eastern and Western Cyprian slab. So now we are looking from above to the isosurface of the fast velocity perturbation. Here we have the Aegean slab. We have the very large tier in Western Turkey. We have the Western Cyprian slab and the Eastern Cyprian slab, and you see a very nice tier in between. Now we have here in the east, we have the Bitlis fragments. We have some fast velocity structures here, and we can also see that the upper parts, we don't have any fast velocity in Western Greece because of the probably more or less horizontal tier there. So this is a bit of a comparison between the different studies of the last few years, and you can see that, it's getting more defined, maybe, the models, but it's also getting a bit more complicated. But in general, I would say the location of the tier is more or less the same. The interpretation of, or like the lower parts are a bit different. We also say that it's might be going stagnant, or not completely stagnant, but at least the dipping angle of the Aegean slab is not that high anymore, but where Portner says it's going at least down to nearly 1,000 kilometers depth. We clearly see this nice horizontal tier at the Kefalonian fault zone. We also see sub-horizontal tier between the very, very thin Eastern Cyprian slab and the Western Cyprian slab. And some fragments in the east, but we don't see, for example, a continuation of the Aegean slab beneath Central and Eastern Anatolia. Okay, thank you very much.
Thanks for timing, Judith. Thank you very much. Very interesting. I hope that we have some comments or questions, and I hope Dr. Rob Gowers would have been here to ask this question about the slab tearing and breakup of mantle. But anyhow, so I sent him your papers. I hope you can read it one day. But the stage is open for questions if you have.
Yeah, but I found it interesting how he explained the step, because I mean, everyone took the step theory of him. And actually, I also understood it wrong how he meant it, but the way he explained it today was
he did this aquarium sandbox experiment with the subducting slab beam abducting the overriding plate animation. Was a bit questionable, but anyhow, so he promised that he will read your papers, but anyhow, so today is some sort of holiday in the West. People are taking weekends off, and so he might find it interesting, but we certainly have some disagreement with his results. So thank you very much. We should really move on to Seda's talk. If you are ready, Seda, we can start.
Okay. Hi, everyone. The title of my presentation is Earthquake Source Modeling and Tsunami Simulations in the Eastern Mediterranean Region. This is the contents of my presentation. It starts with the seismicity of the Mediterranean Sea region, and then I will explain the major active boundaries and major structures in the region, And then I will talk about tsunamigenic zones and source rupture modeling studies in Aegean and Eastern Mediterranean. After that, I will explain source mechanism solutions of recent earthquakes. Then I will show some examples for numerical tsunami simulations of 1481 Crete earthquake. When we look at the Mediterranean Sea region, it is a part of the Alpine Himalayan orogenic belt, and there are many earthquakes occurred along the major tectonic lines. The Mediterranean is generally shallow with an average depth of 1,500 meters, but it reaches a maximum depth of 500 meters of the southern coast of Greece. The active tectonics of this region is governed by the relative movements of the African, Eurasian, Arabian plates. In the west, the convergence between the African and Eurasian plates along the Hellenic subduction zone, and also in the east, the collision between the Arabian and Anatolian plates shape the geodynamic evolution of the region. The major boundaries are Hellenic Arc, Cyprus Arc, North Anatolian Fault, East Anatolian Fault, and Dead Sea Transform Fault Zone. We can determine the plate motions, the rate of plate motions, by using geodetic measurements. And according to McCluskey et al. 2000 and 2003, the African plate moves towards northward 6 millimeters per year, and the Arabian plate motions as 18 millimeters per year. Along the North Anatolian Fault Zone, we observe 24 millimeters per year. Depending on the tectonic motions, we observe different tectonic blocks like north-south extensional tectonics in Western Turkey, and also in north-central Northern Aegean region, strike slip zones, and the convergence, due to the convergence between the Arabian collision between the Arabian and Anatolian plate, we observe collisional zones in Caucasus. The tectonic boundaries are can be defined by intense earthquake activities, but most of the earthquakes are concentrated along the Hellenic subduction zone. And some of these earthquakes trigger effective tsunami waves along the Aegean coastal plain. So we can say that earthquakes and associated tsunamis are the most important natural events affecting the Aegean coast. By looking at the historical documents, we classified these regions as 11 different tsunamigenic zones. The first one is Bartın-Amasra Shelf in Black Sea, Marmara region, North Aegean Trough, Gulf of Corinth, Western Hellenic Arc, south of Crete, Eastern Hellenic Arc, Cyclades, Seferihisar, Kuşadası region, and Cyprus Arc and Dead Sea Transform Fault Zone. From 2017 to now, the intense earthquake activity is observed along the eastern part of the Aegean region. The intense earthquake activity started on the southern end of Biga Peninsula with Ayvacık-Çanakkale earthquake series, and then proceeding to the south continued with Lesvos, Bodrum Kos, and Samos earthquakes. The location of these earthquakes are shown on this map, and also we observe many destructive earthquakes in recent times along the Hellenic subduction zone near the Crete Island. We determined source mechanism solutions of these earthquakes by using teleseismic distance waveforms, P and SH waveforms, and we used Green's function assumption to find the fault parameters. Strike, dip, and rake angle of the fault plane, source time function of the earthquake, focal depth, and seismic moment of the earthquake is determined. The Green's function is calculated by the convolution of crustal effects under the receiver, crustal effects under the source, and the mantle effect. Also, we determine the rupture history and spatiotemporal slip model of these earthquakes by using the immersion algorithm developed by Yagi et al. 2012. According to this algorithm, first of all, we divide the fault plane into different scale subfaults And by inverting teleseismic broadband P waveforms, we determine fault area, source line function, maximum and average displacement occurred during the earthquake, and slip distribution and stress drop. When we look at the earthquake source mechanisms in North Aegean region, we observe that the earthquakes mainly occurred with strike-slip faulting mechanisms, and they are associated with the North Anatolian fault zone in the region. When we look at the 2017 Ayvacık-Çanakkale earthquake series, we determined mainly normal faulting mechanisms with northeast-southwest extensional directions. There are along the Lesbos Island, near the Lesbos Island, another earthquake series hit the region, and the earthquake source mechanisms indicate normal faulting together with the strike-slip mechanisms. In the Sığacık-Seferihisar Samos active tectonics, the seismicity and active tectonics is shaped with the several right lateral strike-slip faults and normal faults. In recent the recent earthquake is the October 2020 Samos earthquake occurred along the Samos fault in this region, and the historical earthquakes also showed several destructive earthquakes in the region, and some of them occurred tsunami waveforms along the coastal plains. Another earthquake series occurred at 2005 near Seferihisar region, and they showed mainly strike-slip fault mechanisms associated with the strike-slip faults in the region. When we go to the Gulf of Gökova region, again we observe intense earthquake activity, and the mechanisms of these earthquakes indicate normal faulting at very shallow focal depths. And 2017 Gulf of Gökova earthquakes are also analyzed by using regional moment tensor inversion, and we observe that the focal mechanisms indicate normal faulting, and together with oblique slip mechanisms at very shallow focal depths. Along the Hellenic subduction zone, we observe mixed focal mechanisms like thrust faulting, strike-slip faulting at different depths. Recently, there are 5 destructive earthquakes occurred near the Crete Island, and some of them trigger small-scale tsunamis near the island. When we examine the historical tsunamigenic earthquake catalogs in the Eastern Mediterranean, we observe many earthquakes, and we know that the development of human civilization in the region has been profoundly influenced by destructive earthquakes and related tsunamis since earliest recorded history. In this study, we numerically simulated several tsunami scenarios of 7 historical earthquakes occurred at different parts of the Eastern Mediterranean region, and we estimated synthetic tsunami wave heights along Southwest Anatolian coastal plains and compared them with the valuable historical catalogs and previous geological and archaeological studies. We know that the tsunami is a series of ocean waves generated in a body of water by an impulsive disturbance that displaces the water. And the main important thing is the speed of tsunami waves varies as the square root of the water depth. So the water depth and the bathymetry data is the most important parameter in tsunami simulations. There are different types of tsunami sources. In our studies, we numerically simulated earthquake origin to tsunamis by using our focal mechanism solutions and slip distribution models. The bathymetry data is shown in this slide. As you see here, there are many tectonic structures that affect the wave characteristics, tsunami wave characteristics, and the major ones are Dalaman-Rhodos Trough, Anaximander and Eratosthenes Seamounts, Mediterranean Ridge, Cluny and Strabo trenches. I will show an example of our simulation results belongs to 1481 Rhodes earthquake sequences and associated tsunami. We assumed that this earthquake occurred with the strike-slip mechanism with the dominant thrust component at this region, at this area, at the very shallow depth, 15 kilometer focal depth was assumed, and the maximum displacement was assumed as 3.5 meter, and then we numerically simulated this earthquake to tsunamis. Here, below, you'll see that several numbers, they are the pseudo tight gauge points, which we try to obtain the synthetic tsunami amplitudes. According to our numerical simulation results, the waves, tsunami waves, propagate in a perpendicular direction of the strike of the fault plane, and the waves arrive different parts of the Mediterranean coasts in different time scales. This is our results. According to this result, near the Rhodes Island, we obtained about 3 meter wave heights. In the Gökova Gulf, we obtained 1.4 meter tsunami wave heights, and Dalaman also, in Dalaman, 1.3 meters. In Alexandria, near 1 meter wave heights are observed. According to historical documents, these earthquake series caused 3 meter high tsunami waves that flooded the coast, while a ship that was moved ashore was smashed in a reef and sank with all its crew. So our results are quite compatible with these observations. We numerically simulated 7 earthquakes, historical earthquakes, as you see on this map, and all overall results indicate very effective tsunami waves along the different part of the Mediterranean Sea region. They are mainly Libya, Africa, and Alexandria, Egypt coasts, Crete, Rhodes, and southern Greece coasts, southwest Turkey, Cyprus, Levantine, and Iskenderun Gulf. As the Gulf of Gökova and the other southwest Anatolian coastal plains locate very close to the tsunamigenic Hellenic subduction zone and the deep Rhodos-Dalaman trough, they might have under a potential to tsunamigenic risk. As a conclusion, I can say that recent Aegean earthquakes occurred mainly with east-west and northwest-southeast oriented normal faulting mechanisms that are presumably developed in response to north-south extensional tectonic forces in the region. However, we observe considerable number of moderate-sized earthquakes with strike-slip faulting mechanisms, predominantly near the Lesvos Island and in the Gulf of Gökova near the Kos Island. Understanding the complex behavior of earthquake source evolution provides principal knowledge in terms of estimating input parameters of tsunami studies, so the importance and necessity of seismological parameters and also high-resolution bathymetry data in tsunami simulations are emphasized. Numerical simulation results of the historical Mediterranean earthquakes and associated tsunamis occurred along the Hellenic and Cyprus subduction zones clearly demonstrated tsunami wave characteristics and potential tsunami risk, particularly at the coastal plains of Crete and Rhodes Island, Turkey, Cyprus, Levantine, and Nile Delta regions. These studies are financially supported by Istanbul Technical University, Turkish Academy of Sciences, the Scientific and Technological Research Council of Turkey, and Science Academy. Thanks for your attention.
Thank you very much, Seda. If there is any comments or questions, we can discuss. Although it's getting rather late behind the schedule, but Thanasis, please.
Yes, have a question for Seda.
Seda.
Yes, excellent talk. Congratulations.
Thank you.
Very good. The earthquake that occurred last year in Crete on the 2nd of May, did you try to model that? Did you try to model that? Yeah.
Yes, we modeled Hiera Petra earthquake. I think.
Yes, Hiera Petra, yes.
Yeah.
Okay.
We modeled, yes.
Okay.
We obtained thrust faulting mechanism at very shallow focal depth for this earthquake, reflecting the convergence of African plate towards the Eurasian plate along the subduction.
I agree with you. The earthquake that occurred last week on the 19th of October on the Herodotus Basin. This earthquake is an intra-slab earthquake. It is not on the interface. It is located inside the African slab. And it's a very interesting, actually, event because it can show that the African slab is still active. So there is compression. Probably the compression is east-west because of the curvature of the slab. So the p-axis is trench parallel and the t-axis is trench normal. It's a very interesting event. I suggest you study this event, although we didn't have a tsunami.
Yes, we looked at source mechanisms of this earthquake also. It shows strike slip faulting mechanisms dominantly, but the focal depth, as you said, is a little bit deep. So strike slip mechanism is valid for this earthquake.
Thank you.
Thank you.
Well, thank you very much. Jury, please.
Just a very short primitive question. I know about tsunami warning system in Marmara Sea, but is there tsunami warning for the whole western coast and southern coast of Turkey, for example, for southwestern Anatolia?
I am not sure for tsunami warning system, but there are studies for installing tide gauge stations near the Gulf of Gökova and Fethiye Dalaman region. But I'm not sure tsunami warning systems.
Yeah, there are a few initiations to increase the number of tide gauge stations around Aegean and Mediterranean from both Greek and Turkish sides, but they are not as much as that we are used to have it in Atlantic or Pacific Ocean side. So it's very limited, a few faraway stations, and still much to invest for tsunami observations in the Mediterranean Sea, in the eastern part at least.
But in Marmara, we can speak about existing tsunami warning, yes?
Sorry?
But in Marmara Sea, we can just already speak about existing tsunami warning system or not, even in Marmara Sea, not?
Yes, there are, both in Athens and in Marmara too, but they are not, the number of observation points are limited. It's not as much as what we observe in Indonesia or Japan or Hawaii or Cascadia. So a few, but still more to be done. So with a few stations, we have the data sets in our hands for the Samos case or Hierapetra case, but so limited, and we cannot explain all the seismological observations with 2 or 3 stations.
Thank you.
Thank you.
Thank you very much, Seda. If not, you can leave now. So I have we are coming to the end. I'm just asking our foreign participants. So we are behind the schedule, so that we can have an overall discussion on this 15 minutes, so that I can skip my talk. Maybe I can give some other times in some other occasions. And what do you say, Thanasis or Jiri? Would you like me to, go for my own talk, or we are already behind the schedule for a long time? So it's
I suppose that you will give definitely your talk. I suppose that.
I don't know, because it's been over 11 hours with the time frame is about to end. So
it is a review summarizing talk, so I think that it should be done.
I agree with Professor Zaharnik. Yeah, please go ahead.
Yeah, so I have my own talk and then general discussion. So, okay, I will try to summarize, but this is not published work, but I will share my screen so that we can start. I don't know whether you see, do you see my results? My screen, at least? Hello?
Yes, yes.
Yeah, okay, so we've been working on this since the beginning with my colleagues, and the number of participants is here. We submitted our paper on the 5th of May, 2021. For some reason, it's been kept for a long time by the referees and reviewers. And I asked some of them to be changed, but over 5 months is unbelievable longer time for a review process, although I review almost 10 papers in a month for some others' research. So we did study the kinematic of the Samos earthquake, and some of our results has been already for the tsunami simulations being presented by Angelo from the University of Iceland, that we are collaborating on the tsunami simulations, and we will write a separate paper on that one. So I have colleagues from GFZ Potsdam and the Chinese friends from the Wuhan and the Shenzhen Technology Institutes. So we are all familiar with this type of the stress rate variations on the planet Earth, and we see where we expect more major earthquakes. So, so this was also already shown by Angel as well. So this is the location of earthquake with red star along the in the top of the Neon-Karlov Ocean towards the Ikaria Basin that we know from the seismicity that we observe many minor earthquakes even from the USGS or ISC. Seismicity is visible to expect large earthquakes in the Aegean Extinction Province or even the subduction months. In fact, I was interested during 2014 and when I was visiting as an Alexander von Humboldt Fellow in Berlin, and there are a number of earthquakes occurred all the way through Zakynthos in the Adriatic, in Patras Bay, 2014 and onwards. With the about magnitude 6 earthquake, including later on Gökçeada and in the Soros Basin, and followed by Lesvos earthquake in 2017, Bodrum Coast earthquake, and eventually the 2020 the Samos earthquake. So we did study all of these, most of them not published yet. And all of these earthquakes and the mechanisms, in fact, proves to the north within the Aegean Sea, my old proposed model of the broken slats model, explaining the escape of the North Anatolian fault towards the Aegean and the deformation on the Greek mainland and the Western Turkey, anti-clockwise rotations and so on. There's so much evidence from neotectonics, paleomagnetism, and field data sets and so on. And as Seda said, this was her PhD study. We also studied entire data set in the Gökova Basin and Datça Bodrum Peninsula. We published this one in 2012. And then, so we had this recent earthquakes in Bodrum and the Samos, then followed by the other major events. So when we, I don't know what's happening, when we closely go to the north of it, here, so this is again the location of simple seismotectonics of the Samos area to the north of Karlovasi, epicenter, and all the blue-colored earthquakes that we studied. Some of them we have published, some of them still waiting to be published in our paper submitted. And these blue ones, and also their extension in the mainland Western Turkey, most of them are right lateral strike slip events on the to the north. But for the Samos earthquake, we had a major aftershock at a depth of 6 kilometers as a mark here in the red and blue. So we are concentrating on those two in this study. So what we did, eventually start with looking at the PN and SH broadband displacement waveforms to look for the point source mechanism. We have used very well-known MT5 algorithm of the, the Nobel-X PhD thesis. It's been modified by the McCaffrey and Zivik and so on. We used for the epicentral distance from 30 to 90 degrees. The reason I want to show you this one, because we also look at the closer near field station and regional stations first motion. So for less than 30 degrees epicentral distance, and we have tightly constrained the north dipping fault plate. So it cannot be larger than 270 degrees because of the polarities and all those nearby stations in either end. So then we get the from point source strike depth and focal depth carefully, and then look for the finite fault the distribution. So this was the stations we have used for the teleseismic broadband P waveforms, in this case, velocity seismograms using the Kikuchi and Canaveres methods, recently extended by Yagi et al. Using hybrid back projection for broadband velocities, P components only. So this is what we get, and it's been already shown from the previous talks, and this is the first finite fault mechanism, what we call model A, and for his plan view of that one and plan met view on the below. So we have up to maximum just 2.7 meter of slip at a depth of 11 kilometer. First 16 to 20 seconds of source time function is evident in this one, but there is a progressive westward direction of the slip rate, and it's been a planar distribution on the deep slip faulting. So then we have used another technique, again, being developed by Xie et al. In this case, it's been applied for wavelet domain teleseismic P and SH waveforms, 30 degrees and 90 degrees epicentral. This is plus local 3-component strong ground motion seismograms in 3 components, in regional, in the Turkish coast, Greek islands, and like Naxos, and in the Mytilene and Yalikavak and so on. So to have extended data sets for a joint finite fault kinematic inversion for PSH waves and the strong motions. In this case, all of them is a velocity model. So this is what we get. So we have west to the east, strike is 270 degrees, dipping 35 degrees towards north, and up to 3.5, but already we have this slip distribution and moment rise time and slip rate, and the release time has been also shown clearly in colors. So when we closely analyze waveforms, here is the broadband velocities. P waves, not much problem. We have almost over 90% fit, but in SH waves and teleseismic stations, we have problems. So we cannot properly match for some reasons, but also there's some local stations and in the strong motion 3-component stations that we used these famous Agelados, Libnet, Dirk Becker's velocity model in the south of Crete and also on the whole area, but anyhow. So then we have decided to map the details of the slip distribution, looking at only to, again, using teleseismic broadband stations, P waveforms, and using almost entire data sets that from the AFAT strong motion stations, 3-component, to see the details of the near field strong ground motion data sets. So, and in this inversion, again, simultaneous joint kinematic inversion, we get again the focal depth 11 kilometer, but only a couple of degrees in the rate is changing, and the maximum slip is about 320 centimeters, just over 3 meters. And we have westward motion, migration of the fault towards the surfaces and in the shallower parts. And this also explains the uplift of the Samos Island and the observed tsunami. So it takes within first 22 seconds at most. So these are the representative waveforms. So the teleseismic broadband P waveforms are displacements, but the local stations here, entire strong motion data sets is the 3-component velocity seismograms. So we had a quite nice, almost identical fits to the Turkish strong ground motion stations, but we had in previous inversion difficulties modeling some of the Greek islands, strong motion, a couple of them. Probably the velocity structure is quite changing. They are not visible, but we have some global assumptions on those. But so we have managed to map the fine details of the strong motion data sets almost entirely. And this also explains this westward migration of those. So this is the bit is in contributing a lot to the strong motion data sets in Turkish mainland. So here's the classic snapshots of the slip distribution up to 3 meters, 12 centimeters, the maximum displacement of slip here in this white star at a depth of 11 kilometers. Here's a small animation explaining how the rupture is propagating upwards in time. And it's almost up to 16, 17 seconds. It takes time, and the later parts contributes a lot to the uplift and the tsunami resources and the wavelengths. If you like, I can show you maybe one more time when it ends. Okay, so this is the joint kinematic inversion both for teleseismic broadbands and local 3-component broadband stations, and moving upwards in time. So this also explains the aftershock distributions quite well in the region. So what we did later on, so we have, for those interested, maybe Jerry and Thanasis, you know, we have, including USGS, we have 4 finite fault kinematic mechanisms. So this, our best model is this one, so this one, yes, from the near field data set, and it satisfies the majority of, in fact, almost all of the observations from the local and teleseismic broadband data sets. And then we incorporated our favorite kinematic fault model stress distribution that we had from the finite fault grid, and in the distributed that field to the fault plane as preferred model C. And so we have a stress map using the curved grid finite difference method in 3D environment using Zhenguo Zhang's theory and applications. He's also co-author in our papers. Then we had inverted results to input to the stress. In fact, this case in the dynamic modeling is the forward modeling. So this is what we get as a slip plane. So it's up to 3 meters. We have some observations. So here I have prepared a small movie for this scenario for model C. And this explains the distribution or migration of aftershocks along the fault plane in a deep slipping normal faulting case. So it's a majority of the energies disappears within 16 seconds. But the rest is just final details, but those details are needed for the strong motion data to be modeled. So these are our final dynamic rupture simulation parameters we have to use. And from the dynamic simulations too, we get moment magnitude 7 and the seismic moment just under 4 times 10 to the 19 Newton meter. So these other parameters are for the dynamic model. So I'm not going to go to details of that one. But what else that we did also look at the back projection of the high frequency seismic radiation for our model C. That our favorite one is in a cyan, the contours showing the normal fault distribution or northerly dipping fault plane. So if there's interest, I can show this animation of this one too later on, but we have very slow rupture velocities starting from 1 kilometer per second, goes up to 2 kilometers and so on. So we also did the Coulomb stress transfer based on our best fitting favorite model, and then this distribution explains the side effects or ramification or engineering problems that we face on the mainland, Kuşadası, İzmir, Karabiga Peninsula, and also Samos Island and nearby Ikaria Island and the Ikaria Basin. So I'm not going to the details of this one, but this is also part of it. It's under the papers. So when we compare all those results with Kandilli or National Observatory Athens catalogs, and we see similar separations that already published partly by Ganas's paper, and also Mehmet Ergin presented his fine detailed ones. But these are confirming our fault plane solutions, both kinematic and dynamic motion modelings for planar deep slip faulting. Okay, we don't have, although it's a 3D, but we don't assume it's being curved. We use a planar fault modeling. So these are our combined results of all of those point source or finite fault slip kinematic models in only a few degrees is changing in rake angles, but obviously you see that there's a moment and this Richter magnitude is being confirmed independently. So I don't want to read it, but with the dynamic rupture simulations, this is the forward modeling case, constrained, of course, by the kinematic joint inversion, elucidate the source process we have already observed from the various seismological data set. And slow rupture speeds goes down to 20 kilometers, but majority of from 12 kilometers upwards, and the length of aftershocks and the dynamic faulting goes up to 60 kilometers in length as a westward striking and rupture propagation at the directional strike of 270 degrees. This is independent from kinematic and seismotectonics, the kinematic and dynamic modeling. But when you look at the high frequency back projections, we see the western rupture directivity about 277 degrees. So this is also confirming the results. So the slip distribution above 11 or 12 kilometers to the surface or near surface explains local coastal uplift of the Samos Island and perceived tsunami. And then we have the tsunami part is in preparation right now. So these are the majority, the preferred fault plane solution confirmed from kinematic and the dynamic modeling and the representative source time function magnitude and the seismic moment. But if you want to go to detail, the 60 kilometer long, 24 kilometer wide fault plane is being broken in 20 seconds, as slow as from 1 to 2 kilometers per second rupture velocities, and of those 75% in the first part along the 60 kilometer long one. But the high frequency emissions goes up to 3 kilometers in some locations. I can show you later on in the animation if you like, but that's also breaks about 30 kilometers of that seismic slip. So we have a 15 kilometer slip in the first 13 seconds, and then we have another 30 kilometers within 13 to 20 seconds is being accommodated with these observations. So on top of that, so already Angel showed that the results. So using the existing bathymetry, we implemented USGS to the left, Model A, Model B, and Model C. Our favorite model is the Model C at the right-hand corner behind, explains almost all the tsunami field observations published by the Turkish field survey, but we will include in this database now the Thanasis' advice that I have seen the paper by Kostas Sinolakis field study published recently, so we will have no difficulties in combining all those data sets. So one more time, this is a nice presentation of Angel works. So I will stop here. Maybe we can have open discussion, or maybe I can show you the other movie if you like. But so with the tomography results and the 3D with cluster systems of the computing facilities, nowadays we can have, sorry, do you still have my screen?
Yes. Yeah.
So maybe I can show you this small movie. Because I don't know, for some reason, I couldn't get the codec right, so it can only play with this VLC player. So I will show you. So we have used, maybe I can show you with the normal size, with the full screen. So we use more than 600 broadband three-component stations globally. So from array number 1 is in the HyNet. I mean, sorry. Yeah, this is the HyNet in Japan. And as you see, it's all in colored, black, blue, red, lines are just showing the orientation of it. So we have back projection, rupture directivity on the animation to the left, and how the speed or velocities is changing in time. So this is evidently showing with the broadband teleseismic and the near field three-component strong ground motion seismograms or recordings of weak motion or strong motion broadband data sets and the strong motion data sets, plus back projection and aftershock distribution and even clone distribution just shows the directivity or northerly dipping Samos, I don't know, Icarius fault towards north. So I will stop here. Maybe we can open discussions. And unfortunately, our paper is still under review, and I cannot show more than this one. Thank you very much. Okay. I don't know whether we've been going too much. Are you still with me?
Yes.
Yeah, I can receive some questions if only the other participants earlier in the morning, they could hear us. But this is the first time my paper under review is over 5 months. This is a word that I don't understand. 5 months. Yeah, so maybe I should keep some others' papers on my desk 5 months, not answering. It's a well-respected journal, but I will wait a bit. Thank you very much. Jury, if only Professor Gallowich was here, because I read his papers and your papers, and we are using this Chinese group's approach in 3D dynamic motion modeling, not yours or Ampere's or Madariaga's type. So this is in the 3D, we can do it in 3D, but it's very difficult for gene region, for instance, for we experience same problem in Hierapetra in Crete too, with all these Boccini et al., so Thomas Meyers and Dirk Becker's 1D model or 2D 3 model for the velocities. It's almost impossible to model Greek three-component strong ground motion recordings for Samos earthquake in Ikaria, Nakos, whatever, to the north Mytilene because of the velocity structure problems. But the rest of the data sets, when we exclude those SH funds, because I've been discussing with Yuji Yagi and a few other global seismologists, and we excluded those 3 or 4 stations, we were able to model strong motions, close stations. They are under 150 kilometers away from the epicenter. So within first 100 kilometers, we have more than 20 stations recomponent. If you like, I can show you again those slides. And with the dynamic motion modeling and with the kinematic ones independently and also simultaneously. But not these two existing Greek stations. I don't know, I double checked their data quality again and again. We couldn't model, but we had a model about 60–70%. We can match their data, but not the entire data set. So, thank you. There's still more to be done. This is a challenge, and we should go for new techniques. So maybe I can receive questions or invite Oğuz and Ercan and others to join the discussion. So we also suffered a lot with the expensive computing times. Sometimes we have 8 times a day electricity shortcut in Istanbul. And today we were very afraid that we are going to have electricity shortcut. But anyhow, so we are doing our best. So Jerry or Thanasis, do you have any questions or comments?
May I have a direct question to your talk, please? Because it was very extensive, so probably I was unable to catch everything. But you spoke about pre-constraining of your dynamic inversion by
dynamic modeling. In dynamic inversion, we did it to inversion because we couldn't find proper velocity model. It did do forward modeling in the dynamic one. But from our preferred kinematic solution fault, we distributed those finite fault slip distribution as stress field, and then we inverted for the dynamic slip And as I showed,
so you pre-calculated stresses based on kinematic slip inversion?
Yes, that's the way we did it. It's not a inversion in that sense, but we are working on it. But provided that we have a velocity model, because on the other hand, as Thanasis already published, we have a 1 Hertz and 30 second GPS and GNSS data sets, high rate, and we also have the strong motion ones. We can make a joint inversion. So we did try those again for those GPS GNSS data sets in Greek islands with a joint dynamic inversion. We couldn't model. So I don't know the reason. The only problem we can come up with is the velocity model, that we are not able to model global stations and model, or like I don't know, full wave inversion velocity models or PREM models, ISP models, or other 1D models are not able to model the simultaneous inversion. Maybe there's something we should discuss about the near field GNSS data sets and strong motion data set and regional or teleseismic broadband data sets we are not able to capture all the image in one simulation, but we are getting there. So although my results are over 90% match, but so I'm not quite satisfied yet. But we are able to model the tsunami wave heights, even the physical oceanography and hydraulics is very important in Greek islands. We have many traps and so on. So we are separately writing the tsunami paper, although there are a couple of already available published, but they are not in final details. Yes, Thanasis, do you happen to have? Or Jerry, do you have any?
Yeah. No, I have a comment that I really liked your talk. I'm really surprised by these reviewers. I don't know what's going on with these people.
Well, the editor-in-chief and the managing editor says COVID-19 issues, so referees are slow, they are asking extension time, and so on and so on. If I see some of my stuff is being published somewhere else, then I will sue the journal. International courts.
You remember there was an issue last year with another person.
Yeah.
I don't want to mention anymore.
I don't know. I mean, to be honest, I personally, last month, reviewed 20 papers from Science Citation Index, well-respected one, the best in geophysics, and also proposals, tenure track appointments, and so on.
Yeah, I believe you, Tunçay. So your talk was really great. You covered a lot of aspects from seismology. I liked the fact that your results were consistent on the deep angle, 35 degrees.
Yes.
So I think this is important because we somehow we obtain similar results for Kos. For the Kos earthquake deep angle, the fault there, and a few other cases. So it looks like some or most of these faults that generate the large earthquakes are mature in the sense that they are quite old faults, older than 1 million years, maybe 1.5, 2 million years old faults. So they have rotated as they accommodate the strain. They localize strain and they release strain during earthquakes. They also rotate. And this is important because we see that in several cases, when you look at the moment tensor solutions from teleseismic data and from regional data, we have differences there which are significant over 10, 15, 20 degrees in the deep angle. So I like this result. I think this is quite important.
Thank you very much for this point, Thanasis, because that brings this Professor Laurent Jolivet's talk at the beginning this afternoon, because he was showing some of those field evidence of same mechanism being working on Gulf of Gökova and Kos area towards the Menderes Alaşehir Graben and the Samos Peninsula and reaching to the Ikaria part. So it explains well of his observations as well our results. But by the way, I must tell you, I am also working another alternative paper on the Bodrum Kos earthquake with additional seismological data set that I have been able to get from some other additional strong motion and other data sets. So on top of what you have published already, so I will have some more results to present in the future. But I am in a hell amount of busy times, writing many papers simultaneously. So I will either confirm or criticize your results, but I enjoyed your paper very much. It's in pure and applied geophysics. So we work on that one too.
Okay, thank you very much, Tuncay. That's all from me. I'd like to congratulate you and all the team in ITU and the engineers. In the morning, we had a great day, summarizing all the aspects of this earthquake. Really very good examples between Greece and Turkey and globally.
Yeah, and also I must tell the jury and you, because we both work on the East Anatolian Fault earthquake and the strike slip months. I am applying exactly the same techniques, except we were lucky in the Samos case, in the Dilek Peninsula, in the Kuşadası area, we have more than 23 component strong ground motion data sets, very close by, very nicely recorded the earthquakes, so we were able to model. In the Eastern Anatolia, we were not lucky that much, but in both cases, back projection plus finite fault kinematic inversions based on hybrid back projection methods, helping us a lot to map the radiation pattern of the rupture and slip evolution in time. So this was the case. We proved that our tools are capable of producing it, and it was also independent, the jury and Gallovich's papers using their own methods, and it proved and come to the same, similar, maybe 99%, exactly the same conclusion. So this is giving us the power of the theories behind and the hand. But I with my group of students, I think, analyzed more than 1,000 broadband stations globally. It's huge amount of time to get every second of data sets in a limited resources here. But of course, I'm looking forward for collaborative works in some other events in the future with Jiri and Thanasis, you and any other interested, provided that we have enough life to live, because we are imprisoned in this apartment blocks due to the COVID. I am too afraid to go out of Istanbul because it's more than 18 million people living, its streets are crowded. Wherever you go, you have trying to hide yourself from any other humankind behind you and so on. This is life. Thank you very much.
Okay, Tuncay,
yes.
I guess the time is running out, and it's been such a fruitful multidisciplinary online event. I would like to thank everyone. And also I'm sure that this recorded broadcast will be watched many, many times later on, and will be one of the major digital documents of Samos earthquake. So by this way, I would like to thank our Disaster Management Institute Director, Professor Yüksel, for bringing us together. And if he has some rush to finalize the session.
Yes.
Yeah.
Also, I would like to present my deep sincere to all presenters and contributors to this event. Thank you for your valuable contributions, and see you next time for a similar event in the future. Thank you very much.
Thank you.
I would like also to thank you for
Thank you very much.
Thank you.
Thanks for organizing.
Thanks for joining.
Thank you very much for your patience all day.
Yeah.
And Jiri and Thanasis, 11 hours sitting on the chair.
One great feature was that there was many young people present. Yes. This is important.
Well, we can't follow who watched in YouTube, but we can follow in the Zoom. But in YouTube is a cyberspace. Maybe they were doing something else. Thank you very much. Kalinita. Kalinita, Thanasis.
Good night. Yes, thanks.
Good night. Good night.
Have a nice evening. Bye.
Okay. Bye-bye.